So hello everyone, we'll start in 3 minutes.
Good morning. So shall I start?
Okay. So hello everyone. I'm glad to start our computer vision track. So we have approximately 25 minutes for each presenter, something like 20 minutes for presentation and 5 minutes for questions. And I'm glad that we have the first speaker today, Konstantin Lamotin, who present a paper automated image and video quality assessment for computational video editing. So, Konstantin, you are welcome.
Thank you. I'm going to talk about the approach to complex video and image quality assessment for automatic video editing. Let's take a look at these two pictures from the TID dataset. Both of them have the distortions with the similar severity, but it's obvious that the left one is more attractive and clear, and it has a twice higher subjective rating score, mean opinion score. So we can draw a conclusion that that image quality assessment is just more than collecting image statistics, and it should be based on some scene analysis. When we take a look at the picture, we don't see a matrix of numbers. We see a scene with objects. So the image assessment should include some more deep scene analysis. For this purpose, we developed this algorithm. It's based on some parallel and sequential steps. So it can be easily tuned. Some steps can be easily included or excluded from this algorithm. And if we throw away these guys, we can assess images. These steps use some features specific for video. These steps allow us to build up some general subjective score for a video clip. Why it's crucial? Because we don't want to assess just objective quality. We want to assess the perception of the video. So this approach is quite generic, so we can use it both for video and for images. And it can be easily implemented in parallel, so it can be paralleled over the data, as it doesn't use some dynamic info, and over the steps. Now I'm going to take some time to speak about image quality assessment, as it's a very important step in our study. Image quality assessment methods can be easily improved to fit our goals. First, we need some good performance, and we need really good quality on subjective score analysis. So as a baseline, we selected the deep image quality assessor. It's pretty new state-of-the-art model based on the deep CNN. It's trained in 2 steps. The first step is a hidden layer pre-training. They're pre-trained to generate some objective error map between the normalized source and the normalized distorted images. And the second step is a fine-tuning with subjective score predictor. The network is trained to generate one number is a subjective score, mean opinion score. All this data is provided by the dataset, and as most of the image quality assessment methods, it requires some pre-processing or image normalization. It includes grayscale conversion and low-pass filtering. So images have to be pre-processed before we can predict the score. Also, it's a blind image quality assessment. That means that we don't have information about the source image, about the original image, a non-distorted image on the stage of application when the network is trained. We had 3 hypotheses about how to improve the quality and speed of the DIQA. First one is to just sample some patches uniformly from the image. It's inspired by the assumption that it's pretty big and wrong assumption that we have the majority of information, the majority of scene objects concentrated in the center. So we just take some patches with it's pretty little that data in comparison with the original image. So, and then we assign some weights to these patches. For example, we can take these patches from this house and assign them weights like 2, 1, 1, 1, 1, 1. And then we'll assume that the twice more information is included here more than here. The next hypothesis we tested is taking patches not from the not from the entire image, but from the specific area. The area is defined by the object detector model. It's pretty fast because it's mobile net and compact. So the whole process is pretty fast. And the last one does not affect performance at all, but it can perform the quality. We intended to include an additional pre-training step with a distortion type classifier. In the original model, we had one pre-training step and one fine-tuning step. So we added one more pre-training step with distortion type classifier. This information is provided by the dataset, so we can try to train the model to predict what kind of distortion is present on this picture. The assumption is that the feature selector will train some useful features that will help the score regressor to reveal the connection between the subjective score and between the distortion type. We evaluated the proposed models on these 3 datasets. It should be said that the distortion type classifier hardly depends on the distortion types in the dataset. So the more distortion types you have, then the lesser quality is. So let's take a look at some objective results. So in the image quality assessment task, it's common to use Spearman and Pearson correlation to measure the similarity between the predicted score and the original score. Here we can see that the content-based patching strategy showed the best results on testing on 2 datasets, and it showed the second speed in among all the models. We tested speed on videos from the live video quality challenge videos, just to measure performance, not the quality. More that the content-based patching strategy has one good feature that it uses object detection, and it's pretty close to the entire framework idea. So this step can be shared with the other. So we decided that the content-based patching strategy suits our goals pretty well. So to conclude, we managed to improve the speed and quality of the baseline method by a quarter. Of course, proposed enhancement can be used together, it can be combined. Now let's get back to our framework. Now I'm gonna just dive into the details. The first step is a transition detection. It's about detecting shot boundaries. Shot is a sequence of frames, usually demonstrating one scene between transitions, maybe hard cuts or just flow. Then we can run our complex assessment algorithm in parallel. It's frame quality assessment as a static image. We use baseline DIQA with object detection and patching. Then we perform shot type classification. We can determine the scale of the shot frame wise, from extreme close up to extreme wide shot. Also, we assign some weights to the scales because we want close up shots to have high quality. It's kind of introducing higher requirements for quality. Then using good old learning books for filmmaking, we assign some heuristic scores for transitions. For example, when after close-up shot comes medium shot, it's not so good transition as long shot after close-up shot. It's just rules of thumb, so it actually depends on the filmmaking school. And then we detect objects. In this study, we detect faces, but generally it can be any other object set depending on the subject area. And after all the algorithms have finished, we compute final score. For now, it's some kind of linear combination like this. So it's pretty simple. Let's take a look at the example, how this framework works in application for video summarization. Yes, we can build a summary using this framework. The summary will be quality-based. On the first step, we compute scores, final scores for this, and all these steps for every frame. If we now try to cut it with threshold and select best frames, we will have pretty ragged summary, just a sequence of frames, not a video, because it's pretty unstable. So we have to smooth it somehow. Generally, any smoothing algorithm can be used for this purpose, but we used the Butterworth filter with degree 4. It just because we want it to be used. Now we can distinguish some scenes. It's presented like peaks here. And now we can build some threshold basing on the required duration of a summary. So if we want the summary to too long some, for example, half of the original video, so we'll take half of the best frames. And then we just select the segments with the highest quality and glue them up together in a single video. Now we can see the best and the worst frames from the 3 videos we downloaded to evaluate our approach. So it can be seen that the video that build up a summary, the frames that build up a summary are pretty clear and aesthetic and include generally more faces, more recognizable faces, and less distortions. It's true for general tests of our framework. So it can be used in filmmaking, it can be used in recommendation systems, and for massive photo shooting, like any birthday, holiday, vacation, or something when you got several thousands of pictures, several hours of videos. So it is. Thank you. Now I'm glad to ask your questions. To answer your questions, sorry.
Thank you for presentation. So does anyone have some questions, comments? Konstantin. So, okay, probably I have some questions. So when you speak about video editing, you assume video summarization or something else?
It's just an example of application of our framework. So
Do
I
you have
guess
some other ideas of how to use this for video editing, not video summarization, but
we can select the worst frames, not the best, and try to improve it. For example, we can run some fixing algorithms for something. For example, if we have some contrast issues, like just like here, we can try to detect it with a distortion type classifier, and try to fix it with some some mutation of exposition, for example.
okay, I see. So, other questions. They say that there is some question at YouTube, but I can't see it actually. So let me think. So any other comments probably? Okay, so so if there is no other questions, we can thank Konstantin for his talk and probably move to the next one. Yeah. So thank you.
Thank you.
The next speaker is Maxim Galyatkin, yes?
Yes.
Awesome.
Okay.
Let's wait for several minutes just to be sure that we're on schedule, okay? Yeah, you could leave your presentation open. It's not a problem. No. I just reported that there was some question at YouTube to the previous speaker. So if Konstantin is here, could you ask it? I can read it.
Yeah, sure.
Okay. So it's not trivial for me just to manage both Zoom and YouTube. So, okay, there is a question about your presentation and about two data sets regarding 2008 and 2013. Yes, 2 years. So what is the difference in the data sets, and how do you explain the difference in quality assessment values?
I guess the major difference is number of distortion types presented. So in the older data set, we had less distortion types presented, and we have high quality. So also in the new data set, the authors added some more original images and more distorted images. Just it's just larger than the old.
Okay, so thank you. Thank you for being here still. So yeah, and I believe right now we can move to the next talk today. So it's speaker is Maxim Galyatkin, and the title of presentation is Semi-Automatic Manga Colorization Using Conditional Adversarial Networks. So Maxim, you're welcome.
Okay. Good morning. Today I'm going to talk on manga colorization. The goal of manga colorization is to produce a colorized image given a black and white manga image with of manga page. So vast majority of manga are produced with black and white. So having a tool to simplify process of colorization would be nice and beneficial, but its problem are more complicated than a natural image colorization, because in case of natural image colorization, most of the deep learning approach consider color image in lab color space. L channel corresponds to color lightning, and AAB channels describes chromatic components. So we can treat grayscale image as L channel and predict A and B channels with with neural network. But manga images have specific structure. It consists of lines and screen tones. You can see them on the right. Screen tones is some periodic patterns that fill the objects to represent shadowing and help to distinguish between objects. However, color images doesn't have such a screen tones, so approach the similar approach as for natural image colorization is not appropriate. So second specific is that there is no open source dataset suitable for supervised learning. There are only few manga titles that have both color and black and white edition, but they even they have some differences that abstracts applying performing some pixel-wise colorization. So, and third specific is that manga image can be colorized in manga image have much more suitable colorization than natural image, because natural image should correspond to our general knowledge about the world. And manga image contains imaginary content, and then it can be colorized in any way. So fully automatic approach for colorization is not suitable. So we've collected a data set of manually colorized manga images. It in total it consists of 60,000 of images of manga pages, and to create an artificial data set for supervised learning, we performed the following steps. First of all, we denoised images with FFD-net. That's a simple convolutional feed-forward network that's trained for additional also noise removing, but our images mostly struggle from JPEG artifacts because they placed in the internet. But that network performs well with JPEG artifacts too. And the second step, we apply XDoc algorithm for line extraction. It allows to produce a binary image that looks in some way similar to black and white image. XDoc algorithm is just calculation of applying of two Gaussian filters, so it's relatively computationally efficient. So, in the third step, we just resize images in the way that smallest site is equal to 512, because we were limited with computational power. And we apply the same procedure for black and white images, because actually artificial images and black and white are quite different because of the screen tones too. And XDoc algorithm by itself doesn't remove any screen tones, but applying denoising blues image, but blues screen tones much more heavily than lines, and it helps to remove some kinds of screen tones on the during the applying XDoc algorithm. So we have this architecture. Our model to control polarization, we employ common technique called color hints. Users may pick some pixels and assign them some colors, and the objects that contains such pixels would be colored in the corresponding colors. In practice, it's just a tensor of the same spatial size that input image. So our model consists of three parts. It's a encoder, recorder, and local fixture extractor. Local fixture extractor is just some pre-trained deep neural net, and we take some intermediate integration from it as output, some feature map. In our case, we use Assessor ResNext 50, and that was pre-trained with line art images. In contrast, generator is quite shallow. It's used for color propagation from color hint, while local fixture extractor extracts some useful information from image. And decoder is used for image colorization. It consists of blocks that every block increase image spatial size twice. So it consists of sequence of a series next blocks with convolutional layer at the beginning and pixel shuffle layer at the end that actually increases the size of image. our network has two outputs to improve gradient propagation during training, because our network quite deep, so auxiliary output gives another path for gradient propagation. And we employ adversarial training, so we also have a discriminator for our network. It's just a convolutional net. You can see it's a architecture here. Okay. We use the following loss function. It's just a weighted sum of few losses. First of all, we calculate mean absolute error for the main and auxiliary outputs. Also, we calculate perceptual loss. That is just an MSE between some intermediate activations from the GG16 that was fed with output image. And also with adversarial loss, that is just cross entropy. And we use white color regularization. Our model tends to leave some objects uncolored if it fails to recognize it. And to avoid such a behavior, enforce model to color objects in some way, some color. We use this regularization in just an average of channel-wise squared sums of masked image. Masked corresponds to pixels of target color image that are not white. Okay. But unfortunately, our model distributions of artificially created images and preprocessed black and white images are different. So our model suffers from domain gap. That means that our model works better with artificially created images from color images than with black and white images. And to reduce domain gap, we apply fine-tuning with such images. We train model in a usual way, but every nth iteration, we fit model with preprocessed black and white image. And make a step of optimization algorithm with a small learning rate. We calculate gradient for the step with for discriminator with the same loss, and for the generator with only the adversarial loss. It helps to it allows us to perform to train network with images from desired distribution without any labeling, and but with information that discriminator learned during training. So we do it only for a small number of iterations, because later, if we increase number of iterations, output from black and white images will significantly degrade, because we train a model with only generator and no any pixel-wise loss. So as you can see in these images, first image is without white regularization and fine-tuning, second one without fine-tuning, first, and second with regularization and fine-tuning. As you can see, results are improved. So there is some examples of colorizations without color hint. You may notice that mostly colorizations are quite good for different images of different styles. Spaces between panels and speech bubbles are not colored if they doesn't have some very unusual shape. And character appearance corresponds between panels if the appearance and original image are similar. Okay, but our model fails to colorize small objects. It actually fills them with only one color. And as you may notice, our model is, that's usual for pix-to-pix colorizers, tend to prefer a few colors. In our case, it's gray and so light brown. So to fix colorization, we use color hints. In the left, you can see color hint, and the right, the result of colorization. As you can, we just choose the pixels and choose color for them. But you can notice that at every step, that colorization change color not only of the chosen objects, but for the neighbor objects too. So it requires more clicks to retain the achieved colorizations. It's more clearly seen on that image. A color hint consists of only of 2 pixels and character's body, but its color of the background also changes. You may notice that colors that our models show, such as character face, remain the same, but some unsure colorizations changes with color, with change of color hint. We performed an ablation study. To show that components of our method improve the result. We collected another data set of black and white monkeys and calculated Frechet inception distance between that set of images and some color images from our training set. And as you can see, every component improved model performance, except 5 steps. We show that extended fine tuning significantly decrease, not significantly, but decrease model performance. Step 4 means that we excuse me for a moment.
It seems that there is some problem with PC of the presenter. So let's wait for a couple of minutes if he can resolve it.
Okay, sorry, I had some technical troubles, but now
Okay.
I'm ready to go on.
Okay, but we have only 5 minutes, so you.
I am near the end, so I have to say that step 4 is using model output. Okay. We give model input image with anti-color hint and use its output for generation of color hint and fit our model with this color hint and again that image. So it's distributions of input with color hints in some sense removes closer to training distribution. So it's removes domain gap a little bit and improves model performance. So okay, let's skip future talk. Thank you for your attention.
Okay, thank you. So do we have some questions to Maxim? Anyone? So let me ask probably some questions. So as far as I know, there exist several papers devoted to manga colorization. So can you comment what is the difference with some of them, for example? So because I probably missed some literature study in your presentation.
Yes, most of these papers are use quite shallow networks. In our network, just have a lot of weights. So I didn't compare with them because our main contribution of our work is steps for reducing domain gap, and but performance of our model may be better than others because only of the size of the model. So it can show the effect of our approaches for reducing domain gap. So we didn't compare with them, but there are model with a lot of with as many parameters as us, and we performed comparison in paper with our model, and as a result, it's also suffer from domain gaps. So because of the because our training dataset are artificially created. So so the main goal of paper to show the effect of domain gap reduction approaches.
Okay, thanks. Other questions? And probably one other small question from me. So in your ablation study, you have some table, but there is no column for a metric. So what metric have you used here? I mean, these numbers.
Inception distance. Yes. Inception distance. It's a Frechet distance between distributions of. Okay, it's a Frechet distance between distributions of activations of some pre-trained inception network. And the lower the score, the better model. And the
okay, yeah, I see. The lower is the better. So thank you. Other questions? No, so let's thank Maxim for his presentation regarding some troubles with, I believe, with computer, but it's typical for online events. So thank you, and we can move to the next speakers. Yep. So I have Elena Yerecheva, and as far as I know, she wants to share some her speech of the speech of her colleague Ivan Drokin from YouTube. So right now she will share the screen and will show this speech. By the way, I can copy this the link to this YouTube here. So for someone who will be interested in taking a look at this presentation, you can take a look at this at YouTube. So Elena, could you share your screen?
Good day, guys. I'm trying, but I have some problem, I think.
Okay, so I can share my screen if there is, if you have some problem.
Let's try to do it by yourself.
Okay, nice. So let me share my screen. And where is it? So sorry. So
detection and chat it is come.
let me say, can you hear this presentation? Because for me, it's the first time when I share it. So
Start with the motivation of our work. The research made by our American colleagues turned out that in more than 70% of cases, it was possible to detect oncology at least a year before on the previous CT scan. The vast majority of lung cancer screening algorithms consist of 4 steps. First of all, it's an important step of target organ segmentation, where lung regions segmented, and this step allows us to reduce field of view for other steps in pipeline. Next one is the lung detection stage, and in this step, our aim is the recall maximization of nodal detection. This is followed by false positive detection step, and one more optional step is overall exam classification for any signs of lung cancer. During this work, we are focusing on false positive reduction step and investigating applicability of point cloud networks for this purpose. There is a short plan of our presentation. We will short introduce point cloud and point cloud networks. We will describe our point cloud sampling, experiment setup, and discuss results on lead IDRI and Luna 16 nodal detection track experiments, and we will cover about our evaluation study. So let's start. Point cloud data is a subset of Euclidean space, and it has the following 3 characteristics. Point cloud data is a collection, and it's not sensitive to the order of the data. The model for processing point cloud data needs to be invariant to a different arrangement of data. The author of the point net chosen to use a symmetric function to ensure the invariance of the arrangement. For instance, if a point cloud is an n by 3 matrix where n is a number of points, the network should fit n factorial permutation in order to be invariant. Geometrically, the order of the point cloud set does not matter. However, it does matter while representing them in a metric structure. Spatial relationship between points. An object is usually composed of a certain number of point clouds in a specific space, which means that there is a spatial relationship between these point clouds. In order to make effective use of this spatial relationship, Creatol proposed a way of concatenating local and global features to aggregate information. Transformation invariant. Target representation by the point cloud data should be invariant to certain spatial transformations, such as rotation and translation. There is present the architecture of dynamic graph convolutional network. The input is a collection of all point cloud data in a frame expressed as a two-dimensional tensor, where n represents the number n by 3, where n represents the number of point clouds and 3 represents its YZ coordinate. First, align the input by multiplying the transformation matrix learned by TNet to ensure the invariance of the model to specific spatial transformation. Then performing feature extraction on each point cloud data through multiple dense lawyer, use TNet to align the features. The output of edge count is calculated by aggregating the edge features associated with all the edges emanating from each connected vertex. Perform max Boolean operation on each dimension of the future to obtain the final global future. And last step for classification tasks. Global future are used to predict the final classification scores through multi-layer process. Let's talk about point cloud sampling. First, to clarify the problem. Patch classification refers to the classification of objects presented on this patch. The nodal is represented there or not. Common false positive detection includes piece of bronchus, blood vessels, fibrosis, and so on. And the task of separating these objects from the nodals, information about their shape is critical. As a result, coordinates are needed as data for representation. The coordinates contain information about the shape of the object represented on the patch. Speaking more formally, we propose to present object not as a three-dimensional image, but as a list of points with their own characteristics. The most obvious characteristic of a point is the coordinates x, y, and z. We can expand this list by adding additional information about the radiological density, Hounsfield units, and probability of the detector. This data is already used by the model as an input. An AIST sampling approach can involve a lot of important information and is highly application dependent. Since 2016, several studies have investigated point cloud analysis but still apply the uniform sampling for fixing the number of points. Such an approach does not preserve the finer details of data, which is important, for example, for segmentation tasks. Furthermore, it also ignores the existing strong dependency between the label of each point and its location in the point cloud. For the basis of our proposed point cloud sampling methods, we use the method described in AIST-2020. The authors propose a liquid-only uniform sampling mechanism that facilitates the network on a fixed size resampled point cloud, which contains different levels of spatial resolution, involving both local fine details and global shape structures. It's based on the Monte Carlo sampling technique and the radial basis function. Let X belong to an Euclidean space with 5 n dimensions and to be a full point cloud with attributes Hounsfield units and detector probability. If center belongs to X and is a randomly chosen point, geometrical similarity for spatial distance to the point center can then be merged with the weighted distance matrix. By resampling, we aim to choose a subset of X with m points where m less than n, then has a dense sampling around the X center and sparse sampling for other locations. Sigma is a parameter that controls the bandwidth compactness of the kernel and depends on candidate radius pair. By randomly drawing with the replacement the point x I from the set x, we accept to insert such a point into the target subset only if value of radial basis function greater than tau. The variable tau is a random number from uniform distribution with the unity interval according to the Monte Carlo technique. We introduced two major differences from this method. First, we changed the sigma parameter, and now it's adaptive. We choose sigma equal to half of a radius of candidate. Second, we introduced additional sampling for the nodular area. It should be pointed out that there is a problem of sampling small plural candidates with diameter less than 5 mm and overwhelming surrounding context. The probability of the candidate's point inclusion to the sample point cloud decreases with the reduction of the candidate size. To deal with this, we sample additionally and uniformly only from the area corresponding to the segmenting mask provided by the detector. Thus, we can guarantee the appearance of candidate points in the sampling point regardless of the candidate's location or size. There are several visualization examples of negative candidates. Red points is points marked by detector as nodular. In all these examples, we can see that marked parts of vessels or bronchs in lung tissues. And there are several examples of positive samples. As the previous red point marks marked by detector as a nodular, and in lower right corner you can see example of subpleural nodule with a lot of points near the target near the candidates, and this is case of overwhelming context for point cloud. Let's talk about our experiment setup. It's difficult to directly and objectively compare different cases. In 2011, an evaluation system was proposed for the automatic detection of nodules on CT imaged by Armata et al. A large dataset containing 888 CT scans with annotation for the open database is available from the NCA Cancer Imaging Archive. The dataset includes a description of the range of possible patients and disease manifestation, as well as the data labels, reception process, and an analysis of their ability to support the performance of range of methods. Since both of our point clouds, the sampling methods and false positive reduction model input strongly depend on segmentation not suitable for nodular candidates, we have used the either the dataset as a source for setting up training and testing data for the false positive reduction test. We have used Tiramisu based on DenseNet 121 as a detector for nodular candidates, as well as for training and test datasets for positive reduction test collection. Firstly, we split lead iterate dataset into train and test datasets with 75-25% ratio. For the creation of the false positive reduction train dataset, we applied four-fold cross-validation. We split the lead iterate train dataset into four subsets, trained the detector on 3 of these subsets, then inferred the detector on the remaining subset. The data received from the inference phase, including predicted segmentation masks and probabilities, is then appended to the training dataset for the false positive reduction task. We repeated this detector train infer loop 4 times, consistently considering each of the 4 folds from lead iterate as a subset to infer. To create the false positive test dataset, we trained the detector on the full lead iterate trained dataset, then inferred the detector on the lead iterate test dataset. The data received from the inference is then used as a test dataset for the false positive reduction task. The goal of the false positive reduction task is to recognize the true pulmonary nodules from a variety of candidates, which are identified at the first step of pulmonary nodulus candidate detection. Here we investigate false positive reduction performance separately from the detector result. We consider it the simplest and most common architecture of a detector model used if only as a sampler for creating the false positive reduction train dataset. Performance evaluating on the false positive reduction is deeply connected with and dependent on the performance of a detector. That is why we examine false positive reduction performance scoring only on an artificially received dataset. We achieved the best effort on score of 85.98 using the dynamic graph convolution network with applied augmentation to point cloud samples. This result will perform the best result for convolutional networks 77.26. As a baseline model, we select third-dimensional version of ResNet 18 as one of the most commonly used false positive reduction model in this field. As you can see from this result, point cloud networks significantly outperform convolutional networks for average number of false positive per scan in interval from 1/2 to 1. And this is a very important zone of false positive per scan metrics, as very valuable for radiologists. We added the four pictures dependent on the nodal size. The results show that in a case with large nodal, there is no performance degradation. Furthermore, PointNet-like models perform better in such cases compared to a convolutional networks approach. To show the effect of the selected sampling method on the performance of the model, we conducted additional experiment with the uniform method of sampling. The table shows significant increase of the FROC values for each false positive level in case with proposed sampling compared to uniform sampling. The RAO is presented as a benchmark. The generally accepted benchmark for the false positive reduction task is nodal detection. In nodal detection is the LUNA 16 false positive reduction track competition. We believe that the comparison of our results with the existing benchmarks is important for a more transparent reflection on the results obtained and the performance of the model. However, it's also necessary to know that, that we are unable to use the LUNA 16 false positive reduction track data as a benchmark for the point cloud-based model. This is because the data on this track does not have the necessary markup, but our false positive reduction model inputs strongly depend on segmentation maps suitable for nodal candidates. We are able to relay the entire pipeline on the LUNA 16 nodal detection track. We are aware of the heavy dependence of the full pipeline evaluation on the performance of the detector. False negatives cannot be recovered by the false positive reduction model. A weak detector can create many false negatives. Furthermore, we want to know that the study of the performance of the detector is beyond the scope of this work. The table shows that both the CNN baseline and PointNet approaches, in conjunction with a weak detector, have a performance comparable to the level of recent published results. And a few words about ablation study. As was appointment before, the most obvious characteristic of a point is the coordinate, if bigger than that. We can expand this list by adding information about the radiological density and probability of the detector. The results presented in the table confirm our assumption on the importance of Hounsfield units and probabilities from the detector in the context of solving the false positive reduction problem based on PointNet-like models and presenting samples in the point cloud. Results of such an experiment show that coordinate information for each point is essential for successful nodal and non-nodal classification. This result is consistent with our hypothesis and assumption. Thank you for your attention, and please don't hesitate to contact with us with any questions and comments about our work and presentation. Thank you very much, and goodbye. Have a good day.
So thanks. Some of our guests here want to ask something to one of the authors, Elena Yericheva.
Yes.
Yeah. Okay. So some questions, comments. Okay. As usual, I have some small questions. So you speak about reduction of false positives.
Hello everyone. कैसे बेटा आप लोग? मैं आपका अपना दीपक वशिष्ठ बहुत-बहुत स्वागत करता हूं आपका आज.
I'm sorry. Yeah, it's the second YouTube after your, I don't know why. So, okay, my question is, you speak about reduction of false positives, and what about false negatives in your
task of reduction of false negatives? It is not task in radiology, just because it's a question of economy of time of working while radiologist is working with describing an exam. It's because when our automatic CAD system provides some markups and labels for the further consideration by radiologists, it is not a sufficient problem not to provide just too much of false positive exams, just because the whole game of this work is to reduce the time of radiologist working while he is describing an exam. So there is only question to reduce a false positive.
Oh, okay. Okay, thanks. Other questions? So if there is no questions, let's thank Elena and her co-author for this presentation, and let's move to the last speaker.
Thank you very much, guys.
Yeah, thanks. So the next one is Piotr Gladirin, and you can try to share your presentation.
Yes, hello everybody. Can you see my screen?
Yeah, we can see you, we can hear you, so you can start.
Okay, thank you. So good morning, everybody. My name is Gladirin Petr. I am from ITMO University, St. Petersburg, and today I want to talk about our research with Valeria Volopa regarding identifying user interests and habits using object detection and semantic segmentation models. So that is outline of my talk. I will talk about the problem of identifying the habits of the users from social networks, what tasks should be solved to solve this main task and to reach this goal, how to train the model, and what problems will be faced to the researchers which want to solve this task. And in the end, I will show our experimental results on our collected data sets for identifying user habits, bad and good habits and interests. So the task of identifying user interests and habits from social networks are widely discussed in the literature. So in last years, social networks are rising, exponentially rising interest for collecting more users, collecting more data from users. So if we want to analyze the data from the users in different social networks, we can talk about multimodal data using texts, subscriptions of the users. So what communities are interested in specific user. There are social links which can be used to construct clusters of users according to their interests, and media data including images, audio and video data, and so on. So if we want to assign for a specific user some marker of interests in some activity on topic, so we want to know exactly what topic are interested in this user. So the main goal of our study is to determine the interests and personal characteristics of social network user based on profile images using methods for detecting and classifying objects in images. So this problem is widely discussed in the literature, but there are a lot of works discussing solving these problems from the beginning to the end. I mean that when we talk about the habits of the user, we first of all should know what objects on the image can identify some habits, some bad habits, good habits, and interests. So here I will discuss specific habits of the user, identifying some bad habits. I mean some alcohol, bars, cigarettes, smokes, and so on. Good habits which connected to some sports, some travels, and so on. And the third task is to identify the context of the image, which can help us to know where the users want to travel, where they usually are in their social life, and so on. There are a lot of applications of this task. There are recommendation systems, some social analysis, and the main is targeting advertising and improving the services of social networks. When we talk about solving this task, we want to collect enough data to train the object detection and segmentation models to be able to make sufficient quality results. So there are a lot of huge publicly available data with annotated images, such as COCO dataset, Pascal Vogue dataset, Open Images, ImageNet, and so on. There are thousands, hundreds of thousands, and millions images with hundreds of categories. But if we talk about specific categories which can be useful to determine user habits, for example, cigarettes, pack of cigarettes, sport gadgets, and so on, we will face the problem that these categories are poorly presented in such data, or even absent in publicly available data sets. So the solution of this problem is to collect the own data set to work with user habits. So this problem have been solved by us, and we have collected our own data set with more than 90,000 images in total. We used some categories from COCO Staff dataset, Open Images dataset, ImageNet, and we have self-annotated photos from Instagram, Flickr, Contact social networks, for specific categories in bad habits and sports group. So in this table, you can see specific classes of groups: bad habits, sport, and background. So straight text is the classes which we have got from publicly available dataset, and italic text is for self-collected categories and self-annotated images using annotate online application, and so link you can see on the slide. This task was solved, and we have collected quite a huge data set. So bad habits and sports were used to train object detection model, and background, which are connected with water, ground, sky, floor, walls, building, and so on, were used to identify the background of the image, which can help to mark user as travelers, for example. The second problem which we face too is that when working with different data sets, when we work with images from different data sets, these images have annotations in different formats. For example, Coco Stuff had encoded annotations in JSON, ImageNet annotations stored in XML, and Pascal Walk as well. Open Images annotations were stored in CSV. So in order to work with this collected data set, we have to develop a specific model to converted annotations for unified format. So again, this problem have been solved. We developed the method for converted annotations from different data set. Here you can see the theme of this method. So depending on the type of annotation, we use different models of our script and convert all annotations to PNG format, where each pixel color corresponds to the class of the object. So you can see here that we have used Coco Stuff API to make this available to work with Coco Stuff dataset and JSON format. And some third-party solutions such Walk to Coco and Open Images to Coco libraries, and self-written script to work with annotate online annotated images. After that, all the annotations with corresponding images in train and validation set are fed to data loader, where we make rescaling to 400 to 400 pixels format of the images, have made an augmentation of the all the images, and feed it to the model on which the model have trained, and evaluate the results as predictions. In predictions, I mean the annotations of the images with some probabilities. After that, after we have collected data set and developed the method of converted annotations, we had to choose the most appropriate object detection and segmentation model to use in our task. So we have tested different state-of-the-art architectures with different backbones. So here you can see the tests of different state-of-the-art models, such as Yellow, RetinaNet, Faster FCNN, and Cascadar RCNN with different backbones models. So the best choice for us was Cascada RCNN with ResNest backbone, which allow us to get the most the high quality result on COCO mini-while dataset. That us tests, experimental tests on different segmentation state-of-the-art model, and again you can see that the best result is available by DeepLab v3 plus segmentation model with exception as backbone. So we have choose Cascada RCNN and DeepLab v3 to work with habits dataset. So Cascada RCNN is multi-stage convolutional network which are based on faster RCNN architecture, and it is highly stable and prevent overfitting of locations of bounding boxes. So architecture of Cascada RCNN is one of the most stable in the task of object detection and location of bounding boxes of different objects. And DeepLab v3 plus is also state-of-the-art segmentation model, and it is divided into encoder-decoder architecture, where encoder is responsible for gradually reducing the size of the object maps and extracting objects from more deeper layers. And the decoder is responsible for restoring object details and spatial data. So as a result, we get a prediction as a map of the image which correspond to the area of specific objects. So here you can see our experimental results on collected habits dataset. To the left, you can see rock oak curves for bad habits, and to the right, you can see the rock oak for sport category for different classes in these groups. So you can see that depending on specific class, we get quite good results. For example, for manually collected and manually annotated images with classes, for example, hookah, bottle opener, smoke, and so on, the results in average are higher than using the classes from open source data sets. Here you can see the background group experimental results for segmentation model. So here you can see that AUK score also quite well, and depending on specific class, results are quite different, but are in average aligned around 77%. So here I present experimental results in average. So all three models Cascadeur RCNN for bad habits, Cascadeur RCNN for sport, and DeepLab V3 with exception for background. So the best accuracy in mean average precision was for bad habits category. It's around 86.6%. For sport category, it's around 84%, and for background, we got 78.4% in pixel accuracy metric. In order to compare our results with another model which trained on another data set, we have tested our Cascadeur RCNN models on MC Coco dataset, and we have compared the results for different classes, which you can see here on the slide, such as tennis rackets, sports balls, snowboard, wine glass, compared with our dataset. So we have trained Cascadeur RCNN on MC Coco and then trained on our dataset, and you can see here that being trained on specifically collected our dataset, the accuracy of model are higher in every case of detecting such specific classes. Here you can see the experimental result for object detection in bad habits and sport category. So here you can see cigarettes, wine glasses, hookah, smoke in the upper part of the image of the slide, and in the bottom you can see sportswear, tennis rackets, sport equipment, and so on. So such categories which we have collected by ourselves. And there is example of image segmentation for input image. We have a mapping for clouds, for sea, for sky, and for rocks here. So conclusion of our work is that we have developed a model that can be used to evaluate markers of interests of social media users based on image analysis. We have collected special data set which we want to update constantly, which are consist of more than 90,000 labeled images to identify habits of users. And one of the main development is development of method for converted annotations, which allows every researcher, on the other hand, to use a large data set of images to train their models, and on the other hand, to be able to add new classes of objects that are absent or poorly presented in such a data sets, which can be used to determine user characteristics. But I want to say that this method can be used not only for user habits as well. You can use it also for another tasks where you should add new categories and use state-of-the-art models trained on the large data set, such as ImageNet, Coco, and so on. So we want to use to make such a script open source, expand further defined characteristics of the person, his interest, and so on, and to collect more multimodal data in order to more efficiently get the user interest in some topics and their habits. So thank you for attention. Please ask questions if you have.
Yeah, thank you for your presentation. Does anyone have some questions and comments? Okay, some question from me. Have you tried your method for some profiles in Instagram or other social networks, like something like real detection of good and bad habits of some users or something like this?
So we have collected some small data set on Contact users. So we have collected some images from their personal pages and have tested this method, and we have some, from my point of view, good results, but we should further implement a method to determine the probabilities of applying some topic to the user. So if we have some set of the objects from the page, yeah, so we should know exactly how to interpret it correctly and to apply some topics, for example, smoker, alcoholic, and so on, to a specific user. So it's quite specific task, which should, from my point of view, should be solved with social analyzers, social network analyzers, and maybe psychologists and so on.
Okay, I see. And by the way, what is the motivation of this study? I mean, how do you want to use it? So, for example, you will apply it for some profile in Contact, and you detected that there are plenty of bad habits of particular users. So, what will be the next step?
So the main motivation is to make some targeting, yeah. So because we work with some business players, and they want to identify correctly the habits of the user, because if the user, for example, have a car or house, so it can be used to make personic advertising and so on, so to make targeting.
Okay, I see. Kofinansen of Bank of St. Petersburg.
Yes.
Nice. So, other questions? It seems that there is no question, so let's thank Peter for his presentation, and to this morning session of computer vision track is complete. So in 20 minutes we will have here plenary speech, and we continue computer vision track in 4 o'clock today. So I will be glad if you attend this track also. So thanks everyone for coming here, and see you today. Bye.
Hello, everyone. So this is the track A, where the next invited talk is scheduled. This is Dmitry Ignatov, who is speaking. So let me also share my screen. Not my screen, my video, sorry. And let me introduce our next speaker, Miguel Cousero from Loria, Nancy, France. Let me read out loud a short bio that we have. Miguel Cousero is a professor of computer science at University of Lorraine in Nancy and the head of the Orpailleur team, which literally means, as far as I remember, gold miner. Also a part of Loria, UMR 7503, which may be considered as a part of French Academy of Sciences, if I'm correct. The current research of Miguel focuses on knowledge discovery and multi-criteria decision-making, and recently with a particular emphasis on fair and explainable models, a current trend in ML and AI. He has co-authored more than 180 papers and book chapters. Miguel is also an elected member for the years 2019 and 12 of IEEE Computer Science Technical Committee on Multi-Valued Logic and a PC member of several conferences. He is also the local coordinator of the European Erasmus Mundus Master Program, LCT, Language and Communication Technologies, and is responsible for the second-year master's program on NLP at the University of Lorraine in France. The title of the talk is as follows: Making Models Fairer Through Explanations. As far as I understand, this is also a joint work with the team from University of Lorraine. So, Miguel, you are welcome. We are happy to host you here as an invited speaker.
Okay, so thank you very much for this kind words, and so it's a true pleasure, and I thank you as well for the organization of this event. It's kind of well, unfortunate situation that we are all experiencing, but on the other hand, we are also kind of experiencing nice things with this type of online event, so we can follow several, and this one has been particularly interesting. So I guess that with this, I should start sharing my screen, right?
Yeah, there should be a button somewhere on the bottom, like screen sharing or screen demonstration.
Okay, so I'm not very talented with this type of things, but it's kind of funny. I don't see any button for starting to share.
There should be the main window of your program, and if you swipe your mouse pointer over the screen, the panel at the bottom should appear, maybe something like this.
Yes. Yeah, but I cannot see the. I see the one participant can share at a time. Multiple participants can share simultaneously. Advanced sharing options.
Uh-huh.
So most likely I don't have the same, how could I do this? I could also connect via browser. I don't know if that makes it simpler.
Connect via browser. Yeah, it might be, maybe it's a better option now.
Yes, okay.
Maybe let's try.
Okay, so then I will do it. I'm terribly sorry for this. I wasn't expecting, this type of issues. And I will come back to you in a tiny little second. Okay. Sorry for this.
We will be waiting.
Yeah.
Oh, it perfectly.
Hello. So do you see my?
Yeah. Yeah, it perfectly fits the screen, and we can hear you.
The only problem is that I can't hear you very well. But anyways, so I don't know if you. Okay, so I am sharing. I can also put my face as well if you want to, or maybe it's not even necessary. But anyways, so I thank once again for the nice presentation. And without further ado, I will just continue with the talk. So as it was mentioned, so this is actually a joint work with two of my students and also Amedeo Napoli, so Guillermo Vaishnavi Bhargava, myself, and Amedeo Napoli. And basically, what we are going to talk is about. So it's a theme or a topic that it's quite on the nowadays concerns of several groups, in particular after the GDPR, the law on data protection, and which require exactly that artificial agents, they should be able to provide explanations, and also they should kind of make sure that the results or the decisions that they make, they are kind of fair. So as we see, we are dealing with notions that are fairly, that are rather subjective, such as that of fair, of what does it mean for a model or for an agent to be fair. And essentially here we are going to take the kind of the classical view on this matter, that it is that a fair model should be a model that to some extent takes into account salient groups, minorities, and kind of works against discrimination. Yeah. So by discrimination, we once again are going to take kind of the usual view that discrimination basically refers to unjust or prejudicial treatment of different categories of people, especially based on features such as race, age, or sex. And that is to say, this kind of salient features. Yeah. So as I have mentioned, this is particularly a serious topic if we are talking about decision-making processes, because usually they have a strong impact on humans. And of course, humans are well known to have both or to apply both an objective and a subjective reasoning. So many people have been working in order to kind of automating decisions in order exactly to take away this subjective aspect, which is very typical in humans. We are filled with biases that shouldn't exist when we are making decisions. Yeah. So these algorithmic decisions, they are supposed to be objective because they are based on data, and they are algorithmic processes. So there shouldn't be any bias, or they should be rather fair. But the truth is that they can also be prone to biases. And the common sources for this are either on the data collection phase, or then on a choice of algorithms, and therefore the models that they train. Yeah. So data collection in the sense that if your data is already biased, of course, the models that you will train using this data will also have this. Yeah. Now, this would not be a problem if there wasn't, or if these algorithms or this kind of artificial agents weren't being used and applied on critical aspects of or dealing with humans and society as a whole. So we now have several applications that deal with, for instance, the prediction of credit card defaulters, also making decisions on job applicants. One typical or one well-known example is that of Compass, and so that is to say, a system for predicting the critical criminal recidivism, that is to say, criminals that will commit again crimes. So trying to predict this, and here, for instance, what was observed was that the system that was being used in the US, which was called Compass, in fact, people noticed that there was a racial bias towards the Black community. Yeah. So essentially, the predictions, the rates in the predictions were basically the same, but the false positives were much higher for the Black community than for the white community. Yeah. So there are several of these kind of drawbacks, and some of which, or this kind of negative impacts that this algorithmic procedures may have, and of course this raises several concerns, and because this kind of unfair decision making, or this kind of unfair outcomes that can come from artificial agents, well, they not only affect the human rights, but they also kind of undermine the public trust in machine learning and artificial intelligence. Yeah. Okay. So now, concerning this, concerning the decision outcomes, of course, fairness again in this artificial setting can be defined with respect to, or can be assessed with respect to, essentially two different approaches to assess it. So one is by using certain fairness metrics. We are going to see several in the course of this presentation. Another one is, of course, to question whether the model relies on certain features, salient features, which are discriminatory. Typical examples, as I mentioned, are features such as race, age, or sex. Yeah. Now, there are two main approaches to dealing with this type of machine learning biases or unfairness. So the first one is, of course, to enforce certain fairness constraints. So you have this fairness matrix, and kind of you try to impose certain fairness constraints while training. So this is again an example that actually comes from this Compass data set. So here we are requiring that the false positives for the Blacks should be the same as, or in proportion comparable to, the false positive for the whites. Yeah. So of course this is for the feature race, but you could see many other fairness constraints that could be employed. But of course this has a drawback, which is that if you require so many constraints during training, then the training process will be very, very heavy. And then, of course, this has an explosion in complexity, but also it could very well happen that you are just overfitting your system, or then you are just you are picking certain, so you are doing what is called as fairness gerrymandering. Yeah. So these are the drawbacks. Now, another approach that you can have is, of course, to deal with the second type of fairness, which is process fairness, which is to exclude those features which are considered discriminatory. Yeah. So, for instance, in the case of Compass, basically you would exclude from your data set the information about the race. Yeah. Now, this is nice, and you could apply this all over, and basically your system would not be dependent on this sensitive feature. But the problem is that if you remove too many of these features, then what happens is that you experience a decrease in accuracy because your machine does not have enough information to learn. Yeah, so this is true. But as we are going to see, there are ways of dealing with this, and it's a little bit about these two types of problems that I'm going to focus. I won't have too much time to get into the first one, but I will present several things about fairness metrics. But I'm going to focus on the second one, which is process fairness. Yeah. So our goal was the original goal was really to kind of propose a human-centered approach to reduce a model's reliance on sensitive feature. And I will say, what do I mean by human-centered approach? And if, in fact, our proposal is basically a framework which consists of two parts. So the first part is just to assess whether a model is fair. And of course, assessing this is just to seeing whether it relies or its outcomes depend deeply on or strongly on sensitive features. And then, if the model is deemed to be fair, nothing to do. If it's deemed to be unfair, then trying to propose another model which resembles the original one, but which is much fairer. Yeah. Of course, all of this without compromising the model's accuracy. Yeah. So the idea for tackling the first one that we had was, or actually we are not the only ones using this idea, was to use kind of explainers in order to assess the model's dependence on sensitive features. Yeah, and of course we use explainers which are based on feature or that output feature importance, so that we could have an idea what is the model's dependence on sensitive feature. Yeah. So there are several examples that nowadays became quite well known. One is Lime. You also have a more recent one, which is SHAP, and you have different approaches which are based on gradient or in fact salient maps. But of course, this requires some further assumptions. Yeah. So in this work, or in the work that I'm going to present, because we have been playing with other explainers, I'm going to present you some results concerning LIME, which stands for Local Interpretable Model Agnostic Explanations, which, as the name says, it's kind of a local approach to providing explanations. Yeah. So I guess that most of you have at least heard about LIME. So LIME is a local method that essentially, so when you have, so it kind of explains the classification of instances, yeah? And essentially what it does, it kind of looks into kind of a neighborhood of the instance that you are trying to explain. And what it's going to do is to try to learn a simple model that then will allow to explain this classification. So the simple model that LIME learns is a linear model, and of course the linear model, and it learns this on a neighborhood of the instance that you are trying to explain. So the advantage is that the learning is quite fast, and also if you look at the structure of a linear model, essentially you have a weighted sum of variables, and of course these weights can be used as the contribution of a given feature to the output of the model. Yeah, so this is basically the idea behind LIME. So displayed in figure 1, I'm giving one example or one explanation for a prediction of a model. So here it's a local, it's an example taken from the adult data set that we are going to talk about a little bit later on. And then it makes a prediction. So essentially it tries to predict whether a given instance, in this case it's a human being, whether it's going to have a salary which exceeds or not 50K per year. So it's salary prediction. And this is basically the type of explanations that LIME produces. So you have different features such as capital gains, such as relationship, and then it kind of shows the contributions to each one of the classes. Yeah. Okay, but we will talk about examples a little bit later, and I will just keep on going. So the idea, as I said, was to use an explainer in order to assess the model fairness. And essentially, what we propose is a system that has as input three things. So a model, a data set, and the set of sensitive features. And this is why we refer to our approach as human-centered, because it's the human that still have a role to play in the system. And then as output, it will output the same model if it's deemed to be fair. Otherwise, it will output another model which is based on this one, but which is much more fair. And on top of it, which will not compromise too much the accuracy of your model. Okay, so what we proposed was to kind of use as explainer in this one. We do have other systems that use other type of explanations, but I will talk about this later. So in this one, we use line, and essentially it contains then the two components. So the first one is for providing global explanations, because line is still a local approach. And then having a kind of an ensemble approach, which I will explain, is based on feature dropout in order to kind of play a little bit with this or be able to handle this drop of accuracy, which is typical if you start to removing features. Yeah. So here I put one of the first repositories. So this was our original repository, but I will later on, especially in the article, we will provide other repositories. Okay, so going for the two components. So we have the line global, which is to provide line global explanations, and we have the other one, which is an ensemble approach. Okay, so going for the line global. So the idea was that, of course, this feature importance, or these explainers, which are based on feature importance, they can provide quite an insight into the dependence of models on certain features. Yeah. So this is why we started playing with line, but the problem is that line provides local explanations. That is to say, explanations for each one of the features, each one of the instances. Yeah. You give me an instance, and I explain the classification or the prediction for that instance by looking at the neighborhood. So this is problematic for us because we need kind of global explanations. And in order to do this, the idea was to use use sampling in order to kind of pick a couple of instances whose explanations to some extent have a good coverage on the whole data set, and they are sufficiently diverse in order to avoid redundancies. Yeah. So here in this preliminary study, we kind of basically use submodular pick with a configuration kind of out of the box, and then the output of the system is just a set of k most important features, but here instead of being local, it's kind of global. Okay, so these are the type of ranking of importance, or the feature importance that we are going to use. And once again, just as a preliminary work, we kind of used k equals to 10. Yeah. So then the rule would be that if among the top k features we find features that were given by a user that were considered to be sensitive, then the model is deemed to be unfair. Otherwise, it doesn't do anything. Yeah. And if it's considered unfair, then there is the second component that applies, which is we call it ensemble out. So how does ensemble out work? So essentially, the first component will output the k most important features, and if it happens that among these k most important features we detect sensitive features among this, then what the second component of limeout does is to train I+1 classifier. So if we had I of these features, if they were sensitive, then limeout will train I+1 classifiers by the so-called feature dropout, which is nothing else than basically train the model without taking into account the features. So it will train I models obtained by removing one of these features, and then it will still train an additional model, which is obtained by removing all of these sensitive features that were indicated by the first component, okay, by Lime Global, okay. And then as the output, we provide, or the system provides, an ensemble classifier, which once again in the preliminary experiment was very, very simple, and it's just an average of all the classifiers of these I+1 classifiers. Yeah. Okay, so then we tested our approach on kind of several data sets. So here I'm illustrating 3 of them. So one was the adult data set, which contains information on it's exactly the example that I mentioned about earlier on, which is a data set that contains information on U.S. citizens and their salaries. So here the goal, as I have also mentioned, was to predict whether the salary of the citizen is going to be more than 50K a year. And for this data set, we considered as the features that were considered as sensitive was sex, race, and marital status. Now, we also considered another data set. This time, this one you can find easily in the UCI repository, which is the German credit card score. So essentially, it contains applicant profiles, so containing demographic and socioeconomic information about applicants. And the goal here is to predict whether they are likely or unlikely to pay their credits. Yeah. So for this data set, kind of the sensitive features that were identified was they were status X, telephone, and foreign worker. Telephone, I guess that people could find this interesting, but the motivation was that an applicant is not or should not be forced to provide certain information such as telephone details, but I will discuss about this a little bit later on. And there is yet another data set. We experimented with several, but here I'm just mentioning these 3. So which is this law school admissions council. Yeah. So again, it contains, this time it's student profiles, demographic and socioeconomic information about students. And here the goal is to, or was to, predict whether a given law school students will pass the bar exams. Okay, so this data set also contains information about kind of the path of the students, so on other examinations. And here the kind of sensitive features that were identified were race and sex. Yeah. Now, as models, we have been playing with several models. So here I'm going to present some results concerning logistic regression, random forest, some boosting methods such as AdaBoost and bagging. And we also have played with neural nets. And but well, I will discuss about these results later on. Yeah. Okay. So just to illustrate how does Lime out work, so we are going to pick an example, which is random forest, which is applied on German credit card score. So on this data set. So again, the goal here was to predict whether a loan application can be approved. That is to say, whether the applicant is likely to pay his credit. So using random forest almost out of the box with the implementations that were given in scikit-learn, we were able to obtain kind of a fair enough result. So of course, since this data set is quite imbalanced, we had to apply some oversampling. We use the smooth technique, and also we had to implement some threshold tuning while training. But once again, we used kind of out of the box implementation on scikit-learn, and using this configuration, we were able to obtain an accuracy of 78, so 0.78, which is quite acceptable. But the question, of course, for us is always, whether this such a model, even though it has kind of acceptable accuracy results, whether the model is fair. Yeah. So for that, what we did, once again, we applied Lime out. So the first component of the Lime out is Lime global, just to assess the fairness of the model. So the results by Lime global, as we have said, is a list of the most important features. So in this case, the top 10 important features were the ones that are displayed, and we see that among these there are two of the sensitive features, namely foreign worker, which has the highest contribution, and also the telephone, which has a fair contribution. Yeah. So this means that Lime out will consider this model unfair because there are two sensitive features that played an important role in the outcomes of this model. So this means that the second component applies. Yeah. So in the second component, what happens is that we are going to train a pool of classifiers. So each classifier obtained by removing one of the sensitive features and then by removing all the sensitive features. So that is to say, we will have one model that is trained after removing the sensitive feature foreign worker, another model after removing the sensitive feature telephone, and then a third model which is obtained by, or which is trained by removing the two sensitive features. Yeah. Of course, what happens is that when we remove the two, we have a slight drop of accuracy, but this was already expected. And when we trained the ensemble, what we realized is that the accuracy raised again. So this is kind of a natural, because this was our intuition behind this this framework, was really to remove the features in order to kind of decrease the dependence of the model on sensitive feature. But then again, in order to prevent the accuracy drop, we applied an ensemble approach in order to make sure that the accuracy there was not such a big drawback in accuracy, yeah, the loss of accuracy. Okay, so then looking at the model and kind of checking whether the model is fairer, and this here, the kind of the idea or the notion of fairer was dependence on sensitive feature. So looking at the results that we obtained, so we clearly see, well, first of all, telephone no longer play a role or no longer appears in the top 10, and even the foreign worker that still appears in the top 10, we see that its importance or its contribution to the outputs of this classifier decreased drastically. So here divided by more than 6. Yeah, that is to say, if we take process fairness into account, then this model is indeed fairer, and the accuracy did not actually suffered any decrease. Yeah. Okay, so we did the same thing with different other examples. So here we see the results, for instance, for AdaBoost, and here there is an interesting thing, because the accuracy of the original model, actually it's a little slightly worse than the accuracy after removing two of the sensitive features. So these were the ones that appeared once again in the that is to say that the contributions of the features in the original model. So we see marital status and we see sex, which were considered as sensitive features. So when we apply Lime out to this model data set and also this set of sensitive features, we get an improvement. Once again, the sensitive features have a much less contribution, or then they just disappear as a whole. We did the same thing. A third example was to test what happened with bagging on the law school data set. And here, again, the accuracy of the original model suffered a little. So that is to say, the accuracy suffered a little bit when we remove the sensitive features that appeared in the top 10. And but then again, when we applied the second component of Lime out, that is to say, we applied this ensemble approach, the accuracy raised again. So that is to say, we get once again a fairer model, which on top of it is even more accurate. Yeah. Okay, so this were just playing with this kind of notion of fairness, which is based on reliance on sensitive feature. But of course, one could ask whether what happens with okay, so here it's just an overview also with other data sets. So we also consider this data set, which is which contains information of U.S. mortgages, which is Home Mortgage Disclosure Act, that try to prevent kind of some bad practices in loan attribution. And so here the goal was to predict whether loans were being high priced, and there was the sensitive features which we can all agree on. And then there was yet another data set which is very close to the German credit card, but this time concerning the Taiwanese credit card users. But essentially the goal were the same, checking or predicting whether payments will be, whether users will default on their payments, and the sensitive features are exactly the same. Yeah, so this is kind of an overview with different classifiers, but of course, and we observed always the same principle. We did the same thing also with neural nets, and we obtained more or less the same results. But of course, this is dealing or looking at fairness of models, model fairness as being the dependence on sensitive feature. Yeah, and we have seen already that there are other metrics that could be used. Yeah, and this is what I want to talk about in the remaining the remaining time. I think that I still have 20 minutes. Am I correct? Hello?
Hello. Yes, you are correct, but remember that we need some time for questions.
Yes. Okay, so I will try to kind of wrap up, because I just want to quickly go through some of the fairness metrics that are usually used in the literature. So the first one is a very simple one, which is demographic parity. So essentially you are requiring, okay, I don't explain what are the, okay, so you are basically having, the idea is that you have privileged groups, unprivileged groups, and you try to ensure that the proportion of positives in the unprivileged groups is rather, it's close to the one in the privileged groups. Yeah. So this is kind of a natural measure of fairness. Another one that is very used in the literature is the equal opportunity. That is to say that the true positives for the unprivileged groups is the same as or close to the one of the privileged groups. So this measure is usually referred to as equal opportunity. Also appears under the name disparate mistreatment. So for instance, the groups could be the blacks or the whites, or then it could be, for instance, US citizens or Europeans. The privilege is then to be defined. But there are several other metrics. So another one is the equal accuracy. So here, basically, we are requiring that the true positive and the true negatives for the unprivileged group should be in proportion, should be similar to that of the privileged group. We also have predictive equality. That is to say that the false positives for it's very similar to the one of the true positives, but the false positives for the unprivileged is kind of the same then for the privileged ones. And we still have another fifth, which is widely used measure, which is that of group fairness, in which we require that the proportion of positives for the privileged and the unprivileged should be more or less the same. Yeah, so these are 5 that we have considered, but there are still some others, but they are just variants of this. And essentially, looking at the results, essentially what we did was that we took the sensitive measures. We took several a large pool of classifiers, and what we used was taking the sensitive features as those that would determine the sensitive from the privileged from the unprivileged groups. Okay, so for instance here, what is indicated here is that, well, first of all, is for the disparate. I recall once again the name of this. So demographic parity, equal opportunity. Here, equal accuracy, predictive equality, and the last one is disparate impact. Yeah. So okay, basically what this says is that we are looking into the model, which is the AIST that took the foreign worker feature as being the one that will separate the privileged group from the unprivileged groups. Yeah. And then what we have is that the red balls are the results obtained by our ensemble approach, and the blue ones are the original results. Yeah. And then, of course, looking into these measures, we indicated as this kind of dashed line the optimal result, so to speak, the one that we should. So, for instance, the balls which are closer to the dashed lines are those that obtain the best results. Yeah. So as we can see, most of the results, they get improved when we apply our ensemble approach. That is to say that that our models, in fact, even with respect to all of this fairness matrix, there is this tendency that the results tend to improve. Yeah. Of course, there are some exceptions, and here we see that, for instance, for the foreign for this one here, the foreign working using bagging, it kind of the original obtains a better result, but in general we obtain better results using the ensemble than with this. Okay, so this kind of fact gets repeated and repeated. In fact, in this case, we see that there is no impact on the fairness metrics, because the original model has essentially with respect to this fairness metric has essentially the same results. Sometimes it improves, sometimes it gets, or in most cases it improves, but sometimes it reduces a bit. And then here we have an interesting thing, because in fact this for the LSAC, the models that we considered, for instance, the ADA for the sex feature, it was already fair, but for the other features it was a bit unfair, like here. But what we see is that our ensemble approach is capable of improving this each one of these metrics with respect to this data set. Yeah. Okay, so with this, in order to have time for questions at the end, so I will just move on to the final remarks, and then I leave for the questions things that I left unexplained. And I'm terribly sorry if I did so, but it's still quite bizarre to have this kind of online, even though it's very nice and I do like, but I don't see you, and that is a bit disturbing sometimes. Okay, but I move on to my final remarks. So just to say a few words about Limeout. And again, I say that we are working on different extensions. So, but what we managed with this Limeout was to show that we can use explanations, local explanations, transform it into global explanations in order to assess model fairness. We also showed that it is possible with an ensemble approach, which is basically obtained by first constructing a pool of classifiers using feature dropout, and then applying even a very simple ensemble approach is capable of providing models which are fairer, in the sense that they are less dependent on sensitive features, but also they have better outputs with respect to different fairness metrics. And it is possible to do so without compromising too much the accuracy. And again, this simple idea of feature dropout, in fact, this was inspired by what is being done concerning deep approaches in order to assess, in order to be able to assess the uncertainty of the outputs. So this kind of dropout, the idea comes exactly from that. And again, so the kind of the punchline is that this simple approach is capable of improving the model's outputs with respect to process fairness, but also with respect to other fairness metrics. And just a few words concerning what we are doing and what we expect to provide in a very short future is that, well, first of all, we are working on several extensions of this limeout, and these extensions come from the fact that we are using different explainers, and also we are playing with different data types. Also, another point that would deserve some improvements is that, well, in our assemble approach, as you saw, we used a very simple kind of straightforward rule of aggregation. So our aggregation is quite simple. It's just an average sum. And but of course, here we should take into account as well the contribution of each one of the features, and this should play a role in the weights that we give to the different classifiers that are in the pool of classifiers obtained by feature dropout. And of course, there is a lot of space for automation. And one of them is, of course, because our approach is human-centered, humans need to provide or to indicate what do they consider a sensitive feature. And of course, this is context-dependent and also it's task-dependent, because for some tasks, some features, for some data sets could be considered sensitive, but for some other task, it's not sensitive. So this, for the time being, we are still basing ourselves on the human intervention, but of course there could be space for automating this process of selecting the features which are considered sensitive, and in particular of choosing how many features should be taken into account when we provide the ranking of the most important features. Yeah. So with this, I think I kept myself on time, and I would like to thank you for the time that you devoted to my presentation. Yes. So спасибо за I don't know if I said it like I should.
Спасибо за внимание. So it sounds like спасибо за внимание. Thank you, Miguel, for this nice, interesting talk on fairness aspects in machine learning. Personally, I like this way of thinking on interpretable models, just because for us who are practitioners, interpretability makes much sense when we would like to know what are the most important features. But fairness is somewhat connected, but another aspect of the problem, and it brings other insights in understanding the data and the model behavior. So I like it very much. I also noticed that your work was based on LIME, which can be used, as far as I remember, both for local and global explanations. So since it's time for questions, maybe I can ask the first question. Do you consider also such techniques as Shapley values in your, how to say, future prospects, maybe?
Yes. In fact, we are already playing with SHAP, and we obtained similar results. Here, I just decided to focus on this. Actually, in the paper that will then appear for this volume, we focus again on LIME, but we already indicated the extensions, and also the repositories will contain these extensions to other type of explainers such as SHAP. Yeah, of course there are several others which are based on gradients, But here we need to require that the function that is learned by your algorithm, of course, this function should have the good characteristics such as differentiability and all of this. Yeah. So if you don't require this, then and if you are basing yourselves on this kind of feature importance, then I guess that SHAP and LIME would be the most indicated. Yeah. And in very few, so in this platform fix out that will be made available quite soon, you will find all these things. Yeah.
Okay. So let us provide the possibility to ask questions for our participants. I know that some of them are watching this video via live channel on YouTube, but those who are in Zoom, you are kindly invited to ask questions. So questions from the audience, please. If any.
There is Leonard.
So thank you, Miguel, for the nice presentations. So I have once, I don't know if it's a question or an observation. So the data that you are working with are real data, right?
Yes, and they are freely available.
Yes. So this means that on the training data, the decision was already made. But do you know if the decision was made using the this sensitive feature that you remove or not? Because at that time, we can think as if the data is already having a bias or not.
Yes, so that is one of the aspects. That's what happened with Compass, for instance, that there is a big due to unbalanced data and with the positives and the negatives, that you had this kind of thing. And this is why when we were doing our experiments, even though the data sets, they contain already these biases, but as you remember, wait a second, I'll put my slide. We applied this kind of oversampling in order to deal with this unbalanced thing. Yeah. So basically, this mode, what it does is that for the classes which are very they don't have they are very badly represented. Basically, it explodes this class in order to balance the data set. Yeah. So this is one of the ways in order to kind of make things a little bit fairer for all the classes. Yeah.
Okay. Thank you.
Do we have more questions, please? So one participant may ask more than one question since we have time.
Alexei, hello,
Okay,
Alexei.
probably. Oh, thank you very much for interesting talk.
Thank you.
Actually, I have two questions and sorry.
You are welcome.
Yeah, so and since I can ask two questions, so I would probably start from like I would ask both of them. And the first one is actually I was surprised that there is different metrics about fairness in a sense. Why? Because okay, as far as I understand, all this problem about fairness usually happens when there's a kind of punishment and a kind of bad behavior. Like, would it be like credit default or crimes or whatever? It seems to be more or less related to this kind of things. And in this case, it seems like, imagine we have population of, I don't know, cats and dogs. And population don't like when mouses are eaten. Then basically it seems that those cats that are not going to eat, it would be dishonest if all of them or large proportion of them are punished. Okay, but in contrast, it seems to be a bit strange to control for that few dogs are not punished while all cats are punished in a sense. So, I mean, if someone is going to be good, probably some dishonest behavior is possible. But if someone is going to be bad, why should we care about honest false positives, I guess?
Yes, so thank you very much, Alexei. So I will try to, if I quite understood your question. So first of all, from the beginning, indeed, this that we are doing actually applies to any setting. Yeah, you could be looking into, I don't know, allocation of resources or something like that. So if you are able to pose the problem in such a way that there is some kind of discrimination or unfair discrimination with respect to subpopulations, then you can use this this approach. And one thing that now I go back to the talk. So as you see, many of these, not all are about punishing the bad, and some of them are also kind of giving good rewards for the good. So this is why we picked, well, this is just a small selection of this fairness metrics, and this is just to kind of cover many of the aspects that you could see. So you could look into fairness in the individual setting, but you could also look at it in a kind of the group dimension, you know, like fairness as groups or fairness individual. Yeah. So here we try to represent several of these aspects that could be taken into account. So, and this is why we use this in order to cover as much as we can all sorts of fairness issues that you could see in data and in models. Yeah. I don't know if I answered your question, but so here we are not making any choices. We are not making any decisions. We are trying to be as neutral as we can, and this is why we considered so many different views on fairness. Yeah.
Okay, I see. So probably I just don't know some fairness, the tasks where fairness appear, and I just have in mind something like crimes or credit defaults. And that's why I'm thinking about only one possibility.
You know, this of fairness actually comes a lot, and I guess that there will be a talk about this. You know, if you are in a game theory perspective, this could be really like local games, or it could be, you know, there are several ways of looking at it and how to pose the fairness issue in a formal way. Yeah. One could be allocation of resources.
Yeah.
This can also raise some fairness issues. Yeah.
Okay. Thank you. And actually, if I can, the second question. With respect to your approach you propose, actually, I have kind of, it seems that when you use an ensemble approach, you basically average, so you have some dishonest model inside, and then you average this dishonest out in a sense, which means that you still have dishonest model, but it's a kind of
okay. So the idea here I can explain a little bit. So our original motivation was really process fairness, so which is really the dependence on sensitive features. So the idea of applying feature dropout was really to decrease the dependence of models on those sensitive features. Yeah. And then, but of course, when you do this, you decrease the accuracy. So this is why you apply the ensemble, because the good aspects of some models in this pool of models which are obtained in this way will be the good aspects of others. Okay, so this, like this, be able to kind of do a good compromise between dependence on a sensitive feature and the accuracy. Yeah. But this is a very naive approach, because it's just a weighted average where the weights are all the same. The contributions of each variable is not taken into account, but of course, this should be a true weighted aggregation process. Yeah. This was just to illustrate the feasibility of this this approach.
Yeah. and how much a model can be dishonest?
Sorry?
I mean, if it seems that the model is still a bit dishonest, what is how much we can do for a model to be dishonest?
That I have to confess that I didn't consider. This is something that is also to be taken into account in the future. So I think that we can play a little bit with these weights in order to control or to be able to reach optimal models. But you are right. This is something that we should, if we want to do kind of the analysis, the most deep analysis of the thing, we need to consider this type of questions. How far can how dishonest, how much dishonest the model can be? Yes.
Thank you.
Thank you very much, Miguel, for coming and delivering this very interesting talk. Just one comment from my side, since I am also part of formal concept analysis community. We already have such interesting notions as stability, but we still do not have fairness. Maybe it would be interesting to bring it to the FCA community if it is not yet done, and I'm not informed. And in that respect, it would sound like a slogan, égalité, stabilité, and so on. You know, it's a bit of fun. As for interpretability for concept learning, everyone is invited for the talk of Leonard Guida just after the lunch. So thank you very much, Miguel, and I'm pleased, well pleased that.
Okay, so thank you once again for this nice event, and I will participate, and I'm open to discussions later on. So please feel
Thank
free.
you. Yeah, we will let you know about the other feedback.
And actually, what you mentioned about the using FCA, I also have some interest in FCA, and I think it's a good idea, of course. And in particular, if you want to identify certain groups, and if you want to establish the issues, the fairness issues that should be taken into account, maybe a classification in the sense of FCA could be very, very useful.
Yeah. So Alexei is also doing some interesting stuff with interesting subgroups discovery, and he uses FCA, so we can collaborate and negotiate.
Yes, and collaborate. I would be most forward that. Yes.
Yeah. Thank you very much, and
okay.
Bye bye.
Bye bye.
See you. Bye.
dear all. I guess it's time to start the next session, and I'm happy to introduce the next invited talk given by Leonard Kuvida. Leonard holds a PhD from Technische University Dresden in algebra and logic, and his research interest includes formal concept analysis, data analysis, algebraic operators for knowledge discovery, explainable artificial intelligence, ordered structures, weak types of negation, and others. So now he teaches at Bern University of Applied Science, and I'm very interested in what is going to happen in the next talk. So Leonardo, please.
Thank you for the kind introductions, and thank you also for giving me the opportunity to share this work with you. So I'm going to start by sharing my screen. And if you don't see them, please let me know. So can you see my screen?
Yeah, the slides, we can see them.
Oh, okay, I think that's enough. Yeah. Okay, so then what I'm going to discuss with you is some idea about the interpretability in concept-based machine learning. So it's also a nice thing that my talk just happened to be after that of Miguel, because he has introduced most of the concept that we also need here. And the talk will be, they say the first part will be on the interpretability of the concept-based machine learning. And in the second part, then we are also going to stress in the interpretability, but this time looking at the stability of concept. So the third part, I will let you know later, so to keep you awake. Okay, so then let us start. So we have here two pictures. And the question is, which one should you adopt? The question is for you. Okay, it doesn't matter which ones you, maybe you have made your decision already, but the question is, how do you come to your decisions? So is it possible for you to explain your choice, or if you let the program do it for you, is it possible to explain the choice that's of the program? So then we have one thing here. This means we have to first to understand what these images are telling us, then extract some information from this, and use these information to classify these two photos. So this is what we will expect machine learning to do. But the main question is, after classifying, is it possible to explain why we come to a certain classifications? Okay, so then our goal is, for example, to try to give an interpretations of what leads to a special classifications. That's what we are going to discuss in the first part, which is this one. So the method that we are going to use is the ones that Sergey has discussed many times in the setting of formal concept analysis. That's the GSM method. And there are also some other methods for the let's say, for this classification, but we are not going to discuss this, the version space, we are not going to discuss that in this case, but there are many other methods. So for the interpretation, the interpretability, so what we are trying to do is, once you have make a classifications, then this classification is based on the attributes that you have in your model. The question is whether all the attributes play the same role, or are some attributes more important than the other in this process of the classifications. To discuss that, then maybe we should have a close look at what the GSM method is doing exactly. So the GSM method is named after John Stuart Mills, and it's an idea to let's say to go from the try to transform the inductive reasoning into deductive reasoning. So the idea behind is that if two or more instances of the phenomenon on the investigations share exactly one's common circumstance, then we believe that this actually is the cause of this phenomenon. So then we are going to try to solve, if you generate the rules and then you want to classify something, then you are going to look what are the common thing between what is not yet classified and what are already known to be classified. Okay, this is a bit how the idea behind the GSM methods, and this has been formalized in the FCA setting. And what we are going to discuss, because we are, let's say, from the FCA side, then to look a bit at the setting in the FCA. And we have said that, so we want to look at the setting of the GSM method in the FCA. And in the FCA, the basic, let's say the basic notions of the FCA is the notion of concept. And what is a concept? If the traditional philosopher, they look at it as something having an extent and an intent. So the intents will be all the attributes that describe the concept, and then the extent will be the object that belong to this concept. And in the FCA setting, we look at the GSM method as a kind of rule where you have the concept intents imply a class. So the concept intents, that's a set of attributes. So then we say that if an object satisfies this set of attributes, we will assign to this object this class. So maybe we will just give you a definition again of what we mean by implication, or what we mean by a rule. So then also in this case, so we have the concept intent, which is a set of attributes. We can look at it as a coalition. And the question is whether all these attributes are playing the same role, or if some are more important than the others. Then to assess the importance of the attributes, then we will borrow some notion from the game theory, and in these presentations, we are going to stress on the Shapley value. This is let's say a function that will help us, for example, to compute the importance of each individual in the coalitions, so that if we were to redistribute the gains, then we will do it in a fair way. So some notion from the FCA, that the setting, what we have is the starting point is a binary relations where you have a set G of object, and then M of attributes, and the binary relation E is just to tell you if an object has an attributes or not. To get the notion of intent and extent, then if you start with a set of objects, then you can look at all the attributes common to all these objects. This will be the A prime, and if you start with the set of attributes B, then you can look at all the objects that have all the attributes in B. So then you have these two derivation operator, and a concept is nothing else like than a pair AB, where A prime is B and B prime is A. And in this case, B is the intent and A is the extent. So then we are going to, for the case of the rule, we are going to concentrate on the intent. So that's just recalling what an implication is. Intuitively, we think that if H, which will be hypothesis here, imply M, so this means M will be the representing the class. So if we have something like this, then we believe that each object that has all the attributes in H should also have the attributes M. Okay, so now that we have defined the notion of intent, then we look at the GSM setting in the FCA. So what is the setting? So we start with a context, and there is a target attribute which is not in the context that we are working with, and this attribute will separate the set of objects in three groups. Then we will have the positive example. That are those objects that we know that they satisfy that they belong to the class. And then we have the negative example. These are also those that we know that they do not have the attribute V. These two parts, the positive and the negative, we will use that to form to get our training context. So this will be, we'll train the model on this, and the goal will be to use the train model to classify the object that are not yet the object that we don't know the type now. So for the notations, we just rewrite the three subcontexts that we have discussed before. So you have the positive, the negative, and the unknown part, and the training context, which is putting together the positive and the negative example and having these relations. So and the goal is to classify the object that's the object that we don't know the type now. This will be for the third context. If we pull all the three contexts together, then so we get what is called the classifications context. Okay, so this is the setting, but now we have to discuss how do we classify an object to belong to a class or not. So what are the rules? To do that, then we are going to generate the hypothesis, and we will call a subset H of attributes a positive hypothesis if it's an intent of the positive context, and this will be an intent of the positive context, and this intent should not contain the intent of any negative example. So this means we want to believe that all the objects there will have the will belong to the class, and so we don't want to have a counter example that will have an object which is satisfying all these attributes but is belonging to the class of object not satisfying V. So then in that case, we also have, in a similar way, the negative hypothesis. This will be the intent of the negative concept, but that do not contain the intent of any positive example. So once we have the hypothesis, positive and negative, then we can now use that to make our classifications. And so here we have an example of a context which is about classifying people who are according to the, let's say, the credit score, if they can get credit or not. And we have the attributes here. If the first thing that you notice is that the attributes are not binary, but then we can transform it to get a binary attributes. So then we will add a new line, which is a new column where we have MA and F and so on. Then we just discretize the attribute here. And using the new context, which is a binary, then we can construct the, let's say, the line diagram of our positive and negative context, and then we can see what will be our positive hypothesis and negative hypothesis. So on the line diagram that you have on the left, for example, that will be that of the positive context. Then we can look at the nodes A that we have here, and these nodes, the intent of this node is actually the upper, let's say we look at the upper parts, then we have the attribute A, F, M, E, and H, E. So this will be the intent that we have. And this will be a positive hypothesis in our case. And in this context here, we have exactly two positive hypotheses. This will be the ones with the node A and the other one with the node SS. In a similar way, we can compute the negative hypothesis. There will be the red node on the second line diagram. So the rules, we say that we will classify an object positively if the intent of this object contain a positive hypothesis and no negative hypothesis. So this means if we look at all the attributes satisfied by an object G, and if it contains a positive hypothesis and there is no contradictions, then we will assign it to the class. And the second case, if we look at all the attributes satisfied by the object G, and if this contains a negative hypothesis and there is no contradictions, then we will assign its, will classify it negatively. There is a third case where we say, okay, we are not able to make the classifications. For example, if you have, if the G prime contain both positive and negative hypothesis, then you have something which is contradictory. Or if it contains none of them, then we still have something which is undetermined. So we have the rules, and we can apply this on this our example of credit scoring. We have two positive hypotheses and three negative hypotheses, and we take, for example, the G9, G9. If we look at the object G9, and look at all the attributes satisfied by this object. Then we notice that it contains the positive hypothesis that's high HS, which is high salary, and no negative hypothesis. Then in that case, we will classify it positively. This means he will get the credit. So and the next object, which is tens, and then we can look at the common attributes. It does not contain neither positive nor negative hypothesis. Then in that case, we think that we are not able to classify, or this means this needs further considerations. We cannot just classify it with our training data that we had. In the same idea, then we can look at the rest, the G11s and 12, and then we make the decisions. So the attribute that we use to make this classification here are those in the intent of the object. And the question is whether some of the attributes were more important than the other. So that's what we should discuss. And to discuss that, we are now looking at the idea of the interpretable of the classification that we have done. Let us assume, for example, here you have a model that will predict the range for the flats, and you train a model, and then you get let's say that the average range will be like the average price will be like 300,000. So the range you assume that you have a model, and say if you train this model to predict the price of the apartments, then you get like 300,000, and you want to check what is the importance of the attribute according to the description that you have. Then maybe you have that there is a park nearby, or the apartment is in the first or second floor, and so on, or you are allowed to have an animal or not. The idea is that you try to look at what happens to the predictions if you remove one's attribute. So, for example, if you remove the cat, or if you add the cat, then you can now use that to see what is the influence of this single attribute. And you can do that because you have a coalition, and then you can also try to check what will be the prediction if I use this attribute or if I don't use this attribute. So that's the idea that we want to use, and we are going to borrow the idea from the game theory that is the Shapley value. And what is this actually? He tried to compute the expected. So he tried to use the expected value of the model predictions, considering so you have a subset S. This is like a coalitions, and then you concentrate on an attribute M, and then you try to see what's happened if M is in the coalition or if M is not in the coalition. Then you try to look at the difference in the expected predictions and take the average on all the subset of the coalitions. So the f of x with S with the S union M, that will be the coalition where M is part of it. And here we assume that S is not S is subsets of M that do not contain the attribute M. So if we compute that, we should look at the value, and the value give of a certain indications on the importance of each of the attributes. So to compute that, we need to define our fx. And in this case, because we want to classify our object, then we will take as the fx, which is here called the v. This we want v to have the value once if we classify. So if this helps us to classify it positively, and -1 if this is to classify negatively, and 0 if we are not able to classify. So then this v is our indication function that we have from the fx that we are using here. So okay, so we have our function, which is Vm of g, and the next thing is to compute this once we have done a classification. So how does it work? At least for the example that we had before, we can just do the computation as it is. Let's say just a naive way without thinking of how say optimal computation or not. We just compute the vector of each of the 4 attributes that we were trying to classify. So in the case of the object 9, we classify it positively, and it was containing only HS, the highest salary as positive hypothesis. In this case, if we compute the Shapley vector, then we see that only the attributes 9 has non-zero value, which is exactly 1. If we do that for the 10s that we're not able to classify, then we get actually 0 here everywhere. And for 11s that we classify negatively, so we here also get negative value almost everywhere. And at least here you see that the -2/3 is the, let's say, the largest in absolute value, meaning that this attribute there seem to be more playing an important role than the others. So then we can do that for all these. We have done these experiments, and what we notice is that if you compute the sum of all the Vm, so you fix the G, you will take all the attributes satisfied by G, then you compute the sum of this. This means that you add everything what is in the vector. Then you will get 1 if G is classified positively, -1 if it's classified negatively, and 0 if you cannot classify the object. So we have done this experiment also on the zoo data sets, and then we have some similar behavior. So the description of the zoo data sets, you can maybe read it later. So we have a data set where most of the attributes are Boolean, except 1 which is numeric, but we convert it into, let's say, we just use the nominal scale and transform it. So we compute the positive and the negative hypothesis. In this case, we have only 1, and we want to classify the object, let's say the animal, want to classify the dog. So what we see here, the classification, the target attribute here is mammal. So then we want to classify, see if we say we classify positively, this means that we believe that this is a mammal, and if we classify negatively, then we believe it's not. And it's possible that we also give up and say we are not able to classify. So in the case of the dog, then we look at all the attributes common to it, and the question is whether some of the attributes here are more important than the other. Then in that case, we compute the Shapley vector of this object, and we can represent it here in this lollipop diagram. And then what you notice is that 3 attributes are here, actually the ones who are playing a great role in these classifications. And these are the eggs, breads, and airborne. So although we have many attributes in this in the satisfied by the dog, so for classifying it as the non-mammal, we think that these 3 attributes are the one playing the important role. So then that's the first part, that we have an idea a bit what's how we can use the Shapley value to interpret the result of a classification. The second part is similar. We are still going to use the Shapley value, but this time is to look at the stability of the concept. So the stability was introduced by Sergey, and then the idea was that if we look at the intent of a concept, and maybe we remove some of the attributes, do we still generate with the rest of the attributes the concept that we have? So then we try to see the robustness of the concept. This could be on the object elections or attributes and so on. So then also in that case, we try to see if looking at the stability of a concept, some attribute will play as a role which is more important than the other. The idea is actually the same. What we need is just to so if we go back a bit, look at how the Shapley value was defined. So here, then what we need here is to define our new function fx. So how do we
I'm sorry, I cannot hear your voice. Leonard, are you here?
it seems there is a technical problem, so we'll try to solve it and hope that the talk will continue.
Dear colleagues, we asked the speaker to restart the presentation. It's somehow a technical problem on maybe on the speaker side, maybe on the Zoom channel. We'll try to fix it in a moment. It seems that now we can see your
You
slide.
can see the screen and you can also hear me.
Right, that's correct.
Okay. Sorry, I don't know what happened, but can you tell me where it stopped? It freeze from 20 something?
24.
24. Okay. So in the slide 24, it's was introducing the importance of attribute for the stability of the concept. And then we have defined the notion of stability as the proportions of subset generating the intents according to the number of, with respect to number of candidates. And then we said that what we need into input in the Shapley formula is to know what is our function fx, and in this case we take v to be 1 if y is a generator of p and 0 if not. So then we input it there and we can compute our vector. So there are, let's say from the computational point of view, there are some simplifications that can be done to get these computations. I will skip the simplifications. If you want to check it, then it is in one of our paper that we can provide, or that you can find it from the CLA. But we look at one example how this works. So we take a part of this context with the fluid context, and we are going to compute its concept lattice and then the stability of the concept, and try to look at the importance of the attribute. So what we consider here is just the positive part of this context. And compute the stability of this context. This is what you have in the second column, and then also computes the Shapley value for each of this concept. What you can see, for example, in the first case is that the attributes S, which is in the first concept, is having importance 0. And in almost all these cases, so then if you go back and look at this attribute, so we have this S, and he's in the concept that we got, he's actually not playing a role. So then computing this vector, we will be able to to access the importance of each of the attributes that we have in our intent. Okay, so this experiment has also been done on the Zo data set, and we can get what can we say? We can try to represent the with these diagrams the Shapley value of all the attributes that are in an intent, and then to see which one are more important than the other. So if you here we look at the first three most stable concepts. So the first one, which is G empty sets, so there is no need to show the vector because everywhere you have just 0. And the second, he classify all these attributes according to their importance, and then the question is probably, yeah, is it possible maybe to use that to remove some of the attributes, or if we want to reduce the number of attributes, maybe we can try to look at the importance of the attributes computed using the Shapley value, and then we can remove some of this. This is one thing. This means that we probably use the attribute in importance and make a kind of ranking. Here, notice that our ranking box is always a kind of local, but maybe we can think about something which would be like generalizing, so averaging, so that we have a ranking on the total, on the whole context. And in that case, we might find out that some of the attributes that we have is not quite important, and maybe we can't remove these attributes when we are working with too many attributes. So another option of reducing the number of attributes is to look at the similarity. And here the idea is that if we believe that two attributes are similar, then we can put these attributes together, and instead of having two columns in our data set, then we just have one column. But when you put two attributes together, then you have to decide how to assign the object to this attribute. This is what we're going to discuss a bit here. So in some cases, then you have, let's say, an ontology, or you have a taxonomy, and this taxonomy tells you that an object, you can have this taxonomy on object or on attributes, or saying, for example, that something belongs to another class and so on. And using that, then maybe we can stop somewhere, and instead of working with the large set of attributes, we reduce and take just part of it. The idea, if according to my present knowledge, the idea came first in the paper by Agravan, where they were trying to get generalized association rules. And what do they understand by generalized association rules? So if you look at this example, this is a database for transactions, and on the right you have a taxonomy. And if you concentrate and you want to find the rule only on the database on the left without using the taxonomy, then you probably miss some important rules. But if you take into account the taxonomy, then you can discover some of the rules that you were not able to find before. For example, that outwear will imply hiking boots, or that outerwear imply footwear. So that you can have this kind of rule that you were not able to see in the first, if you just work with the initial data set. But what you have here is that you try to discover some rule combines with, let's say, the general classes introduced by the taxonomy. But the problem that we wanted to solve was, if we have too many attributes, is it possible to reduce the number of attributes or not? That's actually the problem that we have. But here, in this case, it seems like we have increased the number of attributes by adding also those where we have the those from the taxonomy. Just some notation and definition what they understand by general association rule. This is just an implications with X and Y being actually from, so you will have the not only the item from the initial database, but also from the taxonomy. For the setting, so we just take as the item those that we have from the database, and then we are going to add also those from the taxonomy, and including to define the relations, the instance relations, we need the transitive closure of the taxonomy. And the object will be the set of transactions. So if you, to define the instant relations, you take a transactions, and then you want to connect it to an item, then you look if this item appear in these transactions. But if you take a general item, then you can say, okay, a transaction will support a general item if at least one object, if at least one item of this general item will appear in these transactions. So that will be the natural way to do that. And this is also what they have done in their paper. So, but what we have here is that they increase the number of attributes. And if you increase the number of attributes, then we also expect the number of concepts to increase. You can see it, for example, here, the first part from shirts to shoes, this will be the initial database that we have. And from outerwear to footwear, this will be the general, from the general item that we have. So if you look at the line diagrams, then it's clear that from the initial database, we have less cluster than in the second one. Then now the question becomes, shall we keep also the initial attributes in our database or not? If the goal is to reduce the number of attributes, then we should say that it's better to not keep this in the, so if the goal is to reduce the number of attributes, then we prefer here to just use the general attributes without using the initial attribute before. So then in our case, what we call a general attribute, this is nothing else as a subset of attributes that we have before that we put together. Intuitively, there are many possibilities to assign an object to the new attribute that we just created. So if we take, for example, the case of the database that we had before, then it's maybe easier to say, okay, if you generalize, then an object will satisfy the generalized attribute if it satisfies at least one of these generalized attributes. But there's also some other cases. For example, if you look at the, I don't know, the exam or thing, then it's also possible to require that the object will satisfy the generalized attributes if it satisfies, for example, all the attributes that you have in this setting. So how many time can I take? How more minutes can I take? Can you hear me?
Yes, yeah. I believe that's 7 minutes.
Okay.
So, otherwise, we can start a bit later in.
No, it's okay. I will just try to sell the idea of the generalizing attribute, and I will not show all the details. So for the what I was trying to say is that once you want to make the generalization, then you put a set of attributes together, and then you can say that an object will satisfy these attributes if at least if the object satisfies at least one of the attributes that belong to this class. This is one way to do that, as this has been done by the example before. Or the second one is to say that the object will satisfy a generalized attribute if it satisfies all the attributes there. This is the example of where you have an exam with many components, and then the student has to pass all the part of the exam. It's also possible that you have, let's say, a large module which is having many parts, but then what you require is just that the student should pass at least maybe 60% or 80% of the course forming the module. So then you have this possibility. And it's also possible to not just grouping the attributes, it's also possible to group the object. And this has been done by Susan Prediger. And then when you have the object, the attributes, you can also think about, okay, why just concentrating on object? Why just concentrating on attributes? Or maybe can we combine both together? Yes, there are different scenarios to combine this together. So the idea here is just that, okay, you have a group of objects and a group of attributes. And the question is, when should I relate these two groups? So the easiest way we say, okay, if it's possible to have a connection between one object and one attribute, then you believe that there is a connection between the two groups. This is one way to do that. Or you are more strict and say, okay, these two groups are connected if each object, let's say if all the objects in the group are connected to all the attributes in the group. And you can play with the quantificator by taking all exist and so on. You can play. Or the other possibility is to say that you just look at the proportions. Just say, for example, a certain proportion of the object in the group R should have at least a certain proportion of the attribute in the group B. So then there are many possibilities. Or you can look at the density of the group. So if you look at this part of the context where you have the object and this object is attribute, then you try to look at the density as say, okay, you want the density to be at least a certain, maybe 10%. So that's some possibility to do this kind of generalizations. What we have seen so far is that sometimes, even after doing these generalizations, it's not possible to say for 100% that the number of concepts that you extract from the context are not going to increase. And this is what is discussed in the rest of the slide that I have here. Let us just go to the skip this, and then I show you the let's say a bit the idea from the that we discussed here. So we have seen that if we use a Shapley value, we can assess the importance of attributes when we classify some object, or if when we look at the concept stability. But what we have done so far are to use the algorithm that exists, and we still have to check if we can do some improvement. There are some demos that are available. Then you can look at it for the thing that we have computed here. And we think that if you use the attribute importance, it's possible maybe to also apply it in attribute reductions. And we were planning to discuss the similarity for also to reduce the number of attributes. There are some kind of study about interpretability or explaining. So one thing that is in this paper of Cynthia is that we should actually stop explaining black box model if this can harm somebody. For example, you got from the Miguel using compass for judicial decision, or maybe to give the credit to somebody. And why? Because in most cases, explaining the black box model is not really the right thing that we should be doing. So what we should try to do is have to, from the beginning, have already an interpretable model. And in our case, for the concept classification with GSM and so on, these are not black box model because we have the rule in the form of intent imply attributes, and the intent is just already a conjunction of the attributes, and this is somehow explainable. Then the second thing that I want to mention here, we believe that if the model is explainable or interpretable, then this should increase the trust in accepting this model. But then there is a study from the psychology saying that actually it seems to be not the case. So then when people understand the rule, probably they are not, and if usually if the rules are quite simple, then they don't trust it anymore. So thank you for your attention, and yes, I will stop here.
Leonard, thank you very much for this interesting talk. I guess that many of us can have questions, and actually I have some of them, but unfortunately we are very limited in time. So if you don't mind, we should switch to the next session, and I would like to thank you for this very interesting talk, and probably I will have some questions by email.
Thank you very much.
Thank you.
Yeah, I'm sorry for the not be able to sketch to the timetable.
Thank you very much, Bob, Leonard, and Alexei, for managing the talk and the session. Unfortunately, we really have to go to the parallel session, track B, if the ones would like to listen to process mining, and those who would like to stay with data analysis track, they should keep this track, and Alexei will be there as well, I guess. Thank you.
Okay, so I guess we should start the data analysis track, and the first talk will be given on comparison of neural networks architectures for diacritics restoration. Actually, I'm not sure who is going to present. Is it Eduard Klyashinsky or Alessia Karpik? So
yes, it's me, Eduard.
Okay, so starting from the moment you can share the presentation, you can start.
Sorry, I can't, because it's blocked by the previous talk. Oh, yes. Thank you. So I hope it's visible.
Yeah, everything is fine.
Okay, then may I start? Thank you for staying on my talk. And what's the task statement in this project? Let us consider we have a text which was where diacritics was eliminated. It can be an old text when someone types on unusual keyboard which have just Latinic script without diacritics marks, something like Umlaut in German language and so on. So what this one person could make if this person cannot put diacritics mark. So this person can use a character without an diacritic mark, or use a combination of Latinic characters. In our project, we consider just one situation when this person used one character instead of one character with diacritic marks. So in such situation, we can state a problem. We should restore diacritics just in these positions where they should be. For example, if we have a French text with eliminated diacritic marks, we should restore them just in position marked on the right part of the slide. Different authors already tried to solve this problem, and as they reported, they solved it pretty good. But the first method which was used for this problem was using the dictionary. If we have a word, we can consult a dictionary if this word should be marked with diacritic mark. But as it was reported, for example, in this paper, there are some words which have difference just in diacritics, but have different meanings. So in such cases, we cannot use a dictionary. The second situation when we cannot use a dictionary, it's restoration of diacritics marks in named entities, because we don't have yet a full enough dictionary of named entities. So the second edition of the solution was conditional random fields, and the modern solution are deep neural networks such as recurrent or convolution networks. And authors of such papers reporting pretty high results of their works. But the main problem is that authors using word error rate or diacritics error rate, which are a kind of accuracy. But we are working with extremely disbalanced data. For example, for one French A like this, we have about 1,000 A's without diacritics. And it's well known that in such situation, accuracy works pretty bad. So we cannot use word error rate or diacritics error rate because we are measuring quite nothing in situation of disbalanced data. The second problem of the previous works was that they, as real data scientists, they're using train and test set, but they don't look at the dictionaries of train and test set. We have, for example, 1 million words, and we separate it as 70% to 30%. But the dictionaries of train and test set are extremely well, I have this word on the slide, intersected. It's about 80% of words from a train set which was presented in a test set. That means that we are testing quite the same data on which we have trained the system. So it's not so good. And that means that we should separate data into test and train set without intersections. No any word which should be put in the test set shouldn't be found in the train set. And as it was reported in the same paper, number 3, in case if we accurately separating train and test set, the rate of correctly restored diacritics is decreased from 85% down to maybe 15%. That means that actually neural networks not doing their best in any situations. So what we are proposing? We are proposing a new method. Actually, it's not new, it's common in data analytics. We want to use separate classifiers for different diacritics in a language. For example, a German language have 3 characters with diacritics marks. They are O, A, and U umlaut. So instead of using one classificator for all of these 3 characters, we want to use 3 classificators which are classifying their own character. For example, in this position, if it's A or A or A umlaut. So we took a news wire for listed languages. It was about up to 200 million of symbols in every data set. And we used 7 grams, which was aligned by symbols of beginning of or end of words symbols. Well, boundary symbols. And we used one-hot encodings and character encodings, where we're using just symbol code in the alphabet, in an alphabet in hand. We compared several architectures. Our non-neural network baseline was random forest. And we compared dense networks, convolutional networks, and recurrent networks, which architectures are listed on this slide. Any neural networks had a softmax output layer, and LSTM and CNN networks was compared on mixed dictionaries when we are separating any word without taking care about intersection of train and test sets, and when train and test set was accurately separated without intersection. So here is the results of experiments for Croatian language. We can see here results for precision and recall for every character, and we can compare them with without intersection and with intersection. So we can say that we can see that in case of we are correctly separated train and test set, results are slightly or much worse than in situation when we do not separate them correctly. One of the results of our research was that there is no silver bullet. There is no just one architecture for neural network that we can use for any language and for any character in any situation. For different characters of different language, we have different neural networks won the competition. Well, the situation for German language is brighter, I can say, because, for example, for umlaut, we have pretty good results, very high precision and average recall. But for example, for umlaut, results are extremely bad. However, when we don't separate the train test set, results are pretty good. So that means that we should separate them for correct results, but not for good results. So we compared several approaches for training neural nets with several architectures and don't found the silver bullet. We have compared our approach when we use, as I said, for German language, different three classifiers for any characters with a standard one when we used just one classifier for any characters. So the average precision for our approach was about 0.6, and for standard approach below 0.4. So we can state that our approach is better than common one, using just one classifier for one language, but not for one character of a language. And for any language we made a comparison, results for our approach was better. So
less than a minute left.
Oh, okay, I'm finishing. I have already told about silver bullet, and we cannot be sure that neural network trained on newswire will correctly work with proper names, and it actually makes a problem. We haven't provided comparison for names, actually names. So actually we have a lot to do in this project, and it's listed on this slide. I suppose it's all. Thank you. I'll be glad to answer your questions.
Thank you very much. Probably we have time for one small question if anyone wants to ask it. Okay, it seems that for the moment there is no question, and since we are limited in time, I also wouldn't ask for the moment. Thank you very much for interesting talk. And the next talk is on interpretation of 3D CNNs for brain MRI data classification. Who will be given? Okay, I don't know who will present.
I'm going to present this. Can you share the host, please? Okay, let's start.
Hello, all. It's as well me who will be presenting. So good afternoon, everyone. My name is Ekaterina Kondratьева, and here is my colleague, Maxime Khan. And we represent...
je suis en conférence, mais oui, c'est pour ton truc, n'est-ce pas?
Sorry, could you please move?
Est-ce que tu veux que je fasse quelque chose de particulier ou...
Thank you. So we represent an Adassi Neural Laboratory from Skoltech, and we work on interpretation of the neural network models. And today we will be talking about the interpretation of 3D CNN MRI-based classification models. The deep learning approaches in computer vision are proved to be more accurate in many image recognition applications, including the MRI data analysis, which typically implies 3D networks and 3D data analysis. However, the stable and reliable interpretation of the 3D CNNs is still a topic of the discussion. For example, here's a phrase from the paper exploring age and gender differences. The authors investigated the classification and regression models, conclude that even if the model has high prediction quality, the localized predictions of age and gender do not yield any easily interpretable insights into the workings of the neural network. And to explore the deep learning model interpretability, we have chosen a dataset satisfying the following criteria. It should be a large sample, consisted of healthy subjects, and it should be well studied to be able to compare the results of interpretation with the previous findings. So one of the most common and highly explored databases available in OpenAssess is a Human Connectome project. It's a large study of healthy subjects, and a conventional task which is extensively explored within this database is gender patterns recognition between men and women. The whole sample consists nearly of 500 adult men and women, so more than 1,000 in total. And we were exploring the gender patterns and building the classifier, the binary classifier, using two data types. The full-size T1 images, which just mean the 3D image as it is in a grayscale, and morphometry features, which implies the features explaining the brain structure with the numbers. The T1 images were pre-processed with the Human Connectome pipeline, including skull stripping, intensity, normalization, etc. And morphometry features were extracted with the free surfer tool, and they describing the subject brain within 900 features. And Maxime will continue and say more about the models and interpretation.
As baseline, we used popular machine learning algorithm on morphometry data for gender classification, namely XGBoost, K-nearest neighbors, and logistic regression. The result of tenfold cross-validation is on the slide. And as you can see, analysis of morphometry data can produce good classification accuracy and also can be easily interpreted. To analyze the MRI image, we used standard model architecture. The model consists of 3 hidden layers and a liner layer to produce a class score. Each hidden layer is composed of 3D convolutions, batch normalization, ReLU nonlinearity, and max pooling layer. The model architecture achieves tenfold cross-validation, accuracy of 0.92, which is comparable to the result of morphometry data. And to interpret the model result, we used the 3 methods that have proven themselves well for the analysis of 2D CNN models, and we were first, to our knowledge, to apply them for 3D CNN model. The first method is a meaningful perturbation. Interpret the model, assuming that it is a black box. The goal of the method is to perturb the smallest possible region of the MRI such that the model significantly change its output probability for image class, which means that it is the most informative part of the image for its class. And in this work, we perturbed the original image x sub 0 by replacing the corresponding region with the Gaussian blurring of the image. The mask value lie in the range from 0 to 1, thus the image remains unchanged in the mask area corresponding to 1. And the final mask is obtained by solving the optimization problem, the L1 norm, this optimization problem, and the L1 norm corresponds to search the smallest region of the image to perturb. Also, later, a much more computationally efficient method for interpreting the model is backpropagate up to the input image and obtain a gradient of the class score, which with respect to the input image. However, this method produces a very dense saliency map where every voxel has an influence on the class score. And we can get a more reliable map using the additional rule of gradient backpropagation through ReLU. We can set all negative value of a gradient here in the yellow window to 0 after backpropagation through ReLU nonlinearity. And we do so since we don't care if a pixel suppress a neuron somewhere along the path in the network. Next method is a GradCam, interprets the model assuming that the deep layers capture high-level visual object. In the last hidden layer, we expected future maps to capture high-level patterns, but responsible for class discrimination. And GradCam computes the gradient of the class score y power c with respect to the filter activation of the last convolutional layer f power k, and use average pooling of the gradient as the weight for each filter to produce an importance mask as a weighted sum of this activation. It should be noted that this method is the most computationally efficient of the presented, since it's backpropagate only to last convolutional layer compared to the guided backpropagation, and much more computationally efficient than meaningful perturbation, since meaningful perturbation is a optimization method which is very long. On this slide, you can see the importance mask obtained by each method, and we compare them in terms of dice coefficient, and high score of it confirm that all three methods highlight similar patterns, and we find meaningful region of interest. We recommend using the GradCam method of the network for the network interpretation as the fastest method of the presented. And now Kate will continue with the conclusion.
So, as Maxim just explained, we trained a 3D CNN model to find the difference between men and women. The model was performing closer to the state-of-the-art solution, and we applied 3 different methods of the deep learning interpretation for this task. All 3 methods showed similar attention maps in terms of dice. Yet, to compare these results of modern interpretation with the literature features and to the baseline model, that means the features which was important and scored as most on the baseline morphometry model, we have calculated the masks intersection with the human brain tom atlas. So we intended here not to explore the physiological meanings of our findings, but to find the coincidence with the literature. So we actually claim no insights on the gender recognition, unfortunately, yet our findings confirm previous studies, the ones marked in bold, and confirm findings from the baseline model. Apart from that, we show that some new findings was also discovered with these methods, that can be relevant to the gender patterns recognition from the medical perspective. And to conclude the overall study, we have extended the state-of-the-art model on the different MRI modality and confirmed previous findings on gender pattern recognition on this dataset and on others. Next, we apply interpretation methods on this 3D CNN model. It was 3 of them: meaningful perturbation, GradCam, and guided backprop. And we recommend you to start with the GradCam if you were exploring the same topic. We compare the obtained attention maps to previous findings and baseline morphometry models and show that the model attention is kept on the regions of interest and then can be something more to explore. And lastly, we provide the code for the MRI 3D CNN interpretation as an open source library on our GitHub. So please visit it. And thank you so much. If you're interested in the computer vision applied on MRI, please join our lab with this QR code. Thank you.
Thank you for interesting presentation. I guess we have time for 1 or 2 questions. So if there is someone who wants to start. Okay, probably I will start and probably someone else would join us. Actually, as far as I understand, you get the area of the brain which is related to difference between men and women.
Yeah.
Do you have ideas how this area can be used in future for future research of the brain or probably in some other topics?
Well, I'm not feeling like I'm expert in this, like it's more medical tasks. So we were, as a data scientist, we were exploring relevant medical tasks, but we are not experts in these regions. So we just, we were comparing the regions from literature and the ones we were finding. In parallel, we were learning some patterns of the brain. So I unfortunately cannot answer this question how maybe some medical or doctors, they maybe can find it relevant in future.
Okay, thank you.
But in opposite, we provide a toolbox and we show that some known methods can be used for MRI data interpretation with the deep learning. And to the best of our knowledge, we were at first showing how all of these 3 methods are working on the very, very general task. So maybe others could take our library and do some more insights on different tasks.
Okay, thank you. It seems that there is no other questions, so thank you, and let's prepare the next speakers to talk. So the next talk is about object attribute B-clustering for elimination of missing genotypes in ischemic stroke data. And I guess the person would present himself. There is also a number of persons who can present.
So we are waiting our speaker, Fuzi. Is it a light?
Dmitry, actually, he is not in the list of who is online now.
Oh, yeah, I see, but we checked it before. So he tells that he's in the meeting. Maybe he's in a different track, but it's strange.
Probably we can change to talks.
Yeah. Yeah, please, if it's possible, swap it. Otherwise, we'll lose the time.
Oh, Fujiteki Light has joined us.
Great. Great.
Hello, everybody.
Hello.
Hello.
Can you share the screen, please? Thank you.
Yeah, can you see, please?
Yes, we can see.
Hello?
Your screen.
Yeah. Okay. Thank you. Hello, everybody. Today we are going to present this accepted research paper about object attribute-B clustering for elimination of missing genotypes in alchemic stroke data. Assessing the pathogenicity of variant combinations in multiple genes was until now difficult. Researchers often look at genetic variations between individuals in a population to better understand phenotypic traits, such as human disease origin. One individual's genome can differ from that of the general population in numerous ways. One is single base changes, that is, single nucleotide polymorphisms. These unique differences can be used as markers in linkage and association studies that attempt to determine genes responsible for the disease. Genetic fine mapping for complex traits is still a great challenge for geneticists. The study has been associated with the development of high throughput genotyping technologies, particularly with massive parallel genotyping of SNPs by DNA microarrays. These DNA microarrays require many samples along with large and dense SNP marker sets that are apt to contain a significant number of missing data. In one experiment, it generates a highly incomplete SNP genotype data, and the incompleteness could be up to 90% of observations missing. DNA microarrays provide a rapid, high throughput and cost-effective tool for genome-wide analysis of genetic diversity. However, missing data happen. So missing genotypes can affect not only the statistical analysis, but also the efficacy of the application of machine learning classifiers to identify the risk genetic variants of common diseases and traits. So the classifiers can fail because of that missing values are non-randomly distributed. This problem occurs when genotypic data are collected from different experiments with different DNA microarrays, and each being characterized by its pattern of missing genotypes. Therefore, the missing data needs to be carefully estimated and processed without dropping too many SNPs that may contain crucial genetic information, and this is what our work is done for. So to overcome the problem of missing data, we use a well-developed notion of formal concepts that is almost equivalent to identifying groupings in a data set in terms of object attribute tables in formal concept analysis. FCA is a framework for data analysis based on the notion of concept. In FCA, concepts arise from data, which is given by a formal context. So this formal context is a very simple entity. So it is just two sets and the binary relation between them. Let us look at an example where we take an object set consisting of T2. T2 prime is the set of all attributes of T2. That is the set A, B, and C. This is called the object intent of T2. So an object intent is the set of all attributes this object has. We use here derivation operators to define formal concepts specified as a pair AB, where A is a set of objects, B is a set of attributes, and generally speaking, B is precisely the set of all attributes shared by all objects from A, and A is precisely the set of all objects that have all attributes from B. The clustering method is useful when trying to discover which of our patients have similar diseases. So it is an analytical technique, and clustering allows us to investigate our data and see if patients fall in natural classes or natural groupings within cohorts. From there, we can also look at the genes themselves, though, and we might ask which genes taken on functions or activities under certain conditions. So B-clustering is useful for both of those contexts. We will look at them in more details. To tackle the issue of missing genotypes data that we have described earlier, for a given data table A, we proposed a method that can simultaneously cluster rows and columns in a data matrix to find homogeneous submatrices which can overlap. Each of these submatrices is called a B-cluster, and the process of finding them is called B-clustering. Clustering in genotype data allows identifying sets of individuals sharing SNPs with missing genotypes. So a B-cluster arises when there is a strong relationship between a specific set of objects and a specific set of attributes in data matrix. A particular kind of B-cluster called a formal concept in formal concept analysis. Therefore, we name it concept-based B-cluster or object attribute B-cluster. For instance, for the purpose of this work, we propose the following FCA-based definition of a B-cluster, which is based on the relaxation of the definition of formal concepts by using object attribute B-clusters. If an object G has an attribute M in a binary relation I, their extent and intent within the same relation form a concept-based B-cluster where density is the ratio between all the possible relationships and those that actually exist. Basically, the difference between object attribute B-clusters and formal concepts is that in object attribute B-clusters, not all the cells which represents the relations that form a formal concept must be filled. For example, it is possible that some objects in the formal concept are not related with some of the attributes of the formal concept. By means of object attribute B-clusters, it is possible to generate broader concepts by sacrificing some density in these concepts. The algorithm is rather straightforward implementation by definition, which takes initial formal context and minimal density threshold as parameters and computes large dense B-clusters for each object attribute pair in relation I that have SNP missing values. For calculating B-clusters that fulfill a minimum density requirement, we need to perform several steps. The first step consists of applying the derivation operators to all objects in G and then to all attributes in M. Then all B-clusters are enumerated in a sequential manner, and only those that fulfill the minimum density requirements are retained, and the time complexity for generating all these object attribute B-clusters is polynomial. For the experiments, we collected a set of patients with the ischemic stroke and their clinical characterization that were made at the Pirogov Russian National Research Medical University. So the data set has a certain number of individuals or samples with a genetic portrait for each individual and a group symbol. There is a genetic portrait and the target marker. The feature space represents the genotypes determined at many SNPs all over the genome, whereas the target space takes values zeros and ones depending on whether a person has or has not a stroke. Each SMP is a vector which coordinates can take values from the set 0, 1, 2, and -1, where 0, 1, and 2 denote the genotypes and -1 is the missing value. Now, the genotypic data were obtained with DNA maker arrays, and the data set was compiled from several experiments where different types of maker arrays were applied. So not all genotypes are equally measured during the experiment. There is a certain instrumental error, and the quality of DNA can also affect the output of the experiment. In the resulting formal context, objects from G stand for individuals and attributes from M stand for SMPs. And the binary relation between them, between the two sets, means that individuals are described in terms of SMPs. It specifies which individuals of G has which SMPs of M. The data set has about 1,323 individuals and 85,000 SMPs. And the total number of SMPs with missing values represents about 0.5% of the whole data matrix. The following plot.
Sorry, less than 2 minutes left.
Okay. Okay, thank you. So the following plot shows how many individuals have exactly n missing genotypes per SMP in the data set. And as we can see, for example, many individuals have about 85%, 85 missing genotypes per SMP. So in order we can just go a bit fast, we would like just to mention the exact algorithm that we have done for the in our research about the algorithm that we in our algorithm we applied in our algorithm we used we developed an object attribute B clustering in two phases, that is B clusters generation, and after that density computation. So we used actually some pointers like those in C++ to sparse matrices in order to generate them within 2 seconds for the whole data set. And the density was computed with the help of using the number of NNZ method, like that for SciPy sparse matrices. And also we used parallel computing we used parallel computing in order to execute our code as faster as we can, as we have a large data set. For the first data set experiment, we used the machine learning algorithms before we applied machine learning algorithms before and after elimination of missing data. So we got before elimination of SMPs, we got like some overfitting in our algorithm, but whereas where we eliminated the missing values, we got like good results after applying the same machine learning algorithms.
I'm sorry, we are quite out of time.
Okay, we go to summary. Like we conclude our presentation by citing our finding. We proposed a new approach to process missing values in a large genotype data processed by DNA maker arrays. So the approach based on object attribute B clusters and the relaxation of that is the relaxation of formal concept definition. And the algorithm was also able to identify and eliminate large dense B clusters in large biological data sets that help removing overfitting and effects of data leaks on machine learning classifiers. So for future work, we aim to go further with this research to compare our results with existing algorithms, such as DB algorithm that is capable for analyzing very large data sets in a reasonable time. And we also aim to improve our algorithm's time complexity for generating large B clusters in a reasonable time with minimum software requirements. Yeah, and finally, we also have an intention to experiment on the second data set for imputing remained missing SMP values using the same techniques. Thank you so much for your attention.
Thank you. Unfortunately, we are out of time, so no question for this time. The next talk will be on commutes and contiguous simulating disease propagation on urban transportation networks. And the talk, I guess, will be given by Ho Cheung. I'm sorry if I'm wrongly pronouncing your name.
Us. Oh, yeah, my name, Ho Cheung. Can someone mute their mic? Thank you. And I'll share my screen. Where's the button? Okay, let's just do that. How's that? And I assume everyone can see and hear. Let's hide that. So let's get started. Yes, 25 slides, but a lot of these will be reference slides for if you have questions. Commutes and contagions, simulating disease propagation on urban transportation networks. So we had something more specific in mind. Obviously, it was COVID, and it was the New York City subway. But our research, we were able to generalize it to talk about diseases, like the flu is very close, and just diseases in general, and transportation networks, so airplanes, buses, railways. Our research applies to that too. So here's the table of contents, basically a pretty standard table of contents. So here's the basic why of why we did our research. And if you're a very naive person and you don't know how disease is spread or you haven't studied it, you might think, oh, well, New York or Moscow, there's it's infected. There's infected people there. And you might think that all places in the city are equally infected. Well, these maps show that it's not the case. Some areas, there's higher prevalence of disease in some areas than others. And in April, this is kind of like popular science, but someone did some quasi-research and looked at this and said, hey, this kind of lines up with the subway lines in New York City. Why is this the case? And we thought we would do some research into why this is the case too, and how epidemics spread along networks. Now, here's some prior research. So there's a lot of different prior research out there. This one in particular is the one I'm going to show today. It uses a very different methodology, but it has like the same kind of ideas that you'll see in this written text down here, which is that, the more time that people spend on these public transportation networks, the more likely it is for them to have the flu. And so here, they just kind of do some mathematical modeling to calculate this contact rate that people have. And on the right here, green and red, they are people from 2 different London boroughs, from 2 different places in London. And it shows that, well, people from the red borough, they have more contact on the subway. And it turns out that people from the red borough, they get the flu more often based on the data that they gathered. This is just a caveat slide saying that the research actually, didn't work so well with coronavirus, but it could have just been that London handled it relatively well. So that's just a caveat. Now, the methodology we picked for when we chose to study this problem is agent-based modeling. So here, if you're a computer scientist, you might, or like really, well, okay. You might understand this architecture. It's pretty simple. Here on the right here is basically our actual agent-based model. We built it on top of this software called Mesa in Python, and we used NetworkX to create our model of the network. And it's general for all types of transportation networks, like I mentioned. So, you might take your pre-processing, which is your, New York City subway data, or you might take your World Airlines or your trains in Madrid, whatever. You build the network, you tell it how to build the network, and you tell what the agents are, and you tell what they do. Now, if you're not familiar at all with agent-based modeling, the two important questions you really have to ask are, it's basically, you have these independent agents and they interact with each other based on this rule set inside an environment, which you also define. So the two things you have to really pay attention to is what are your agents, what rules are they following, and what is the environment. And, with computer science programming being the way it is right now, it's pretty, pretty standard, simple stuff. And for the more, visual people, this is kind of basically how, these models might look. You build a network, a grid, triangle, Moscow's metro, and you have your agents, which, it's hard to show, but, maybe the agents in all these cases are actually just these nodes on here represent the people. They're kind of like a population of those nodes. And that's kind of actually the kind of agents we'll use later for New York City too. So more visual representation. And here's another example, just to show that, what we did was robust. And so we used it actually to look at a bunch of other stuff, some other people in the group. This, it's not in the paper. It used to be in an appendix, but I cut it because it was too long. And basically it shows, that we can model a transportation network, the World Airlines, and we can model COVID spreading along. It's the motivation here specifically was, we saw someone else do it and we thought we could do it better. So our model in particular highlights the spread of COVID in China first, and then to other countries based on the port of entry. So not just randomly propagating throughout the world, kind of as a blob. And here's something else we used it for, Madrid's commuter trains. And the real reason we use this is because there's these central hubs in Madrid, in the Madrid commuter train network. And you can see that kind of through this map or this right here, that there's these very central hubs. Unlike maybe in some other more diffused transportation networks, here's the rule set we used for Madrid. And basically, we got these results that highlight, well, first, that rush hour is very, it's very risky for the spread of disease. And also, these central networks, you can see these numbers on the y-axis, they are kind of like more important. And also interesting, like a minor point, is that having a staggered time when everyone gets off work really helps reduce the rate of infection. This is an observation, not something we proved, but you can see here, especially for this station. Now, here is more slides that we can skip over, but basically, we pulled a lot of different data for New York City. We pulled a lot of different data for every model we use, but here's some of the idea, location data, demographic data, the people who did London did too. This is, some terminology. If you ask a question and use the wrong terminology, I'll go back to this slide. But, subway systems have their terminology. And more data. Okay, we'll stop on this slide briefly, just to say these are the rules we used, for how our agents work. And here are our agents down here. They're basically an extended version of an SEIR model, where if you know SEIR, it represents a closed population, which goes through the 4 stages: susceptible, exposed, infected, removed. And we opened it up basically because just to exposure from the outside, basically because how else is somewhere in some place in New York going to be infected, if not through the subway or through some other transportation network. And the environment, of course, as I mentioned, are these subway stations. and some model parameters. It's not too important, related to SCIR and some quarantine measures to help. Well, because there are quarantine measures in real life to help make our model. And so the first thing we did is we made our data match up with the New York City data. It's not too important, only to mention, of course, there's no actual SCIR data in real life. There's only case numbers. And so we matched them up. And then we took a look at, once these overall numbers matched the numbers for New York City, we took a look at how well our model matched for locations, for specific locations. So the most granular we can get are these zip codes, this mod ZCTA thing. And there are these little areas. And this middle and this right pictures are really the two things to compare, or maybe the left and the right. Left and middle are the same thing. And so it does a pretty good job where there is data. These light green regions, there's no subway stations. So we could have interpolated, but in this diagram, this picture here, we didn't. And here's the actual map for a more numerical result. And it's not great, but it's good. We have a lot of GIFs, but we'll skip that. But the main conclusion is, okay, there's some correlation, no smoking gun. And that's what we ended up submitting this paper as. And we have these thoughts about how to improve it. Some of these don't actually improve accuracy, but they make the model more simple and understandable sometimes, and they reduce overfitting is what they do, I would suppose. I mean, they reduce overfitting. And we think that, regardless of whether we do these changes or we made some of these changes or we didn't, we do think that it, accurately, the things we did for New York and Madrid especially demonstrate these 4 points here. And it's that subway routes, this is the main one we wanted to talk about. Subway routes are correlated to the prevalence of ILIs, and the further away from the center and the more, I would say, central, you might want to ask about that, your subway route is, the more likely, or the more people in that population that lives around that station is to get the flu. And the last slide is actually just references. So we can stop here on this acknowledgement slide. Some fellow researchers who didn't want to write the paper and some supervisors. Thank you for listening. Questions?
Thank you. I guess we have time for 1 or 2 questions. While someone prepares their own, I would ask a small one. Actually, are there any other models that they try to model more or less the same situation, and have you tried to compare this in some sense?
There are a lot of models that model a similar situation, and we didn't make any quantitative comparisons. And I'm just struggling to pick which one. There's actually a model that we mentioned in our research from like maybe 1990 or 2000, which just tried to model New York City, all types of transportation systems in New York City, and just made an agent-based model for the entire New York City. And in the paper, I believe we did compare like some numbers between the two. Like they thought that overall, or we talked about their numbers, where they said maybe 2% of New York City would get infected if there was a flu-like virus, and it ended up being maybe like, I don't know what the actual percentage was actually, but it was different, but not too different.
Okay, and are there any other questions? Okay, it seems for the moment there is no questions. Probably someone would contact you by mail or somehow. So thank you very much.
Thank you.
And let us start the next talk about Bitcoin abnormal transaction detection based on machine learning.
Sure.
Who is giving the next talk? Okay.
Hello.
Yeah, hello, we can see your presentation.
Okay. First of all, I want to express my thanks to Program Committee for the opportunity to present our work at this conference. I'm researcher at Leiden State University. I'm here to talk about the development of reliable abnormal Bitcoin transaction detection that may be involved in money laundering and illegal traffic of goods and services. I will tell you about a novel approach based on machine learning. Finally, I will show how it was possible to increase the reliability of the classification of abnormal Bitcoin transaction in comparison to the best known results with the elliptic dataset. Bitcoin is a cryptocurrency which consists of open source peer-to-peer digital currency. Money transactions don't require third-party side. The payer and payment receiver directly interact without using their real identities, and no personal information is transferred from one to the other. However, differently from a fully anonymous transaction, a complete transaction record of every Bitcoin transfer and every Bitcoin user's encrypted identity is made of the public ledger called the blockchain. For this reason, Bitcoin transactions are not completely anonymous. Therefore, Bitcoin payments have also become an attractive and frequently used means for collecting money for illegal activities of criminals. There is paradox. Anonymity makes it possible for criminals to hide, although open Bitcoin transaction database allows to perform forensic analysis. The objective of AML analytics is determining abnormal transaction, which may place the variable classification of minor illegal transaction in a massive, constantly increasing Bitcoin database. Manual or semi-automatic transaction analysis produce a high error rate, and it's very difficult. In 2019 year, IBM researcher collected the elliptic dataset for a classification of abnormal Bitcoin transaction. It's work Weber. The elliptic dataset is a subgraph of total Bitcoin transaction consisting of 200,000 nodes and 200,000 edges. Besides graph information, the elliptic dataset includes information about node class, legal, illegal, and unknown. A node is considered either legal or illegal if the current transaction was arranged by a legal part, broker boards, wallets, suppliers, miners, financial service providers, or illegal fraud, malicious software, terrorist groups, ransomware, pyramid investment schemes. Just 2% of nodes belong to illegal class. 21% belong to legal class, and 77% are other transaction unknown. The elliptic dataset includes information 166 node features. The first 94 features present local information about transaction, and remaining 72 features called aggregated features are obtained by aggregating transaction information. It was possible to perform almost complete de-anonymization of the elliptic dataset. Benzik from Clarity Group found the total number of inputs and another characteristics The first result is here in work Weber. This work is presented by IBM Research Workers Weber and Dominiconi at the seminar Knowledge Discovery and Data Mining conference. They shared results from a binary classification task predicting a Lichten transaction using variations of logistic regression, random forest, multi-perceptrons, and graph convolution networks. The results show the superiority of random forest model. In the elliptic dataset, we consider only transaction with a binary variable, illegal or legal. We are not considering unknown class of transaction. We can apply a semi-supervised machine learning approach to Bitcoin abnormal transaction detection using unknown transaction. We leave the execution of this idea as a future investigation. We presented abnormal Bitcoin transaction detection as a binary classification task which can be solved with the machine learning algorithm. The following algorithm of machine learning from scikit-learn, they are used for classify abnormal transaction. Some part of machine learning algorithm gave bad results, therefore further on the results of the following machine learning algorithm are not presented. Linear quadratic regression, linear and quadratic discriminant analysis, naive Bayesian classifier. We also use gradient boosting algorithm for classification, CatBoost, XGB, LightGBM. To estimate the reliability of our models, the following metrics are selected: accuracy, precision, recall, one score. One important observation took place concerning the data in the elliptic data set, which provides imbalance. When a certain class in the dataset is too small and the other class is broadly presented in the dataset. Therefore, we use also the index of balanced accuracy metric to estimate binary classification case with imbalance data. Then the dataset was randomly split into a test set and a training set in ratio 3:7 correspondingly. This table provides the results of classification with test set. The metrics precision, recall, one score are given only for illegal transactions as to estimate reliability of transaction detection is in the most case important to analyze errors. The best classification algorithm is CatBoost classifier with a one score equal to 791 and accuracy 978. However, the obtained results are slightly slower than the best result from Weber article, where random forest algorithm had one score equal to 796 and accuracy 978. If one score and accuracy is not an acceptable result for reliable detection of abnormal transaction, so the best CatBoost classifier model. Our experiments with the model involve testing different combination of related hyperparameters for find the optimal response with a given set of values. To automate the process of obtaining the best combination of hyperparameters, grid search tree algorithm from scikit-learn library is used for the best result. the hyperparameters yield the optimal response for a CatBoost model. Among we find out imbalance data in their elliptic dataset. Among the approaches to solve the imbalance problem is to apply various resampling strategies. There exist two ways to restore a class balance. In the first case, some examples major class are removed under sampling. In the other example of minor class are increased over sampling. Atomic links algorithm were selected to solve the imbalance problem. For all major records incoming in Tom links must be removed from the dataset. Tom links can be determined as on the slide. This table holds the result of...
sorry, less than 2 minutes left.
Okay, algorithm classification with test set. Tom links algorithm was implemented to classify a dataset, and it removed 300 legal transaction. The best classification algorithm is XGB classifier. Obtained metrics significantly outperform random forest algorithm used in the Weber article. F-score and accuracy are acceptable for reliable detection of abnormal transaction. Therefore, the conclusion comes that with Tom links resampling algorithm, it was possible to increase reliability of Bitcoin abnormal transaction classification. We also did experiment for testing different combination of related hyperparameters to find optimal response. Also, the accuracy and IBH scores in our experiment also validated through 10-fold cross-validation. For all 10 iterations, the values of evolution measures remain almost the same, indicating the stability of the models for Bitcoin abnormal transaction. And we say that the XGB classifier model performed better than all other models used in this study. In conclusion, we presented the model of Bitcoin abnormal transaction detection based on machine learning algorithm with atomic links resampling algorithm in imbalanced learning condition. We managed to increase reliability of Bitcoin abnormal transaction classification as compared to the best result from Weber works, the first work with the elliptic data set. The reliability of the proposed model for Bitcoin abnormal transaction detection based algorithm equals to 9921. The accuracy and IBA scores in experiment also validated through 10-fold cross-validation. The results show XGB classifier model perform better than all other models in use in this study for detecting abnormal Bitcoin transaction. Thank you for your attention.
Thank you. Unfortunately, we don't have time for questions. So, and now the next session, the next track is starting on computer vision. Thank you.
Thank you.
Okay. Thank you very much. My name is Ilya Makarov, and I will be co-chairing computer vision track for today. And I would like to ask to present their work named Efficient Group-Based Hashing Prediction and Images Using Facial Descriptors, authors Ilya Gavrikov and Andrei Savchenko. And I would like to remind that we have strict time limit, 10 minutes for presentation plus some time for questions. Please proceed with the shadow as follows.
Hello. Just a second. Can you see my presentation?
Yes, you could turn on full screen mode.
Yeah. Okay.
Yes, thank you. You may start.
So the topic is efficient group-based cohesion prediction name images using facial descriptors. Prediction of group-level emotion and cohesiveness is very useful for various companies in order to analyze employees' emotional state throughout the day and build a relationship between their emotional state and group cohesion. As the cohesiveness of a group is a crucial indicator of success of a group of people, the problem of predicting the perceived cohesiveness of a group of people in image becomes one of the main tasks in the emotion recognition in the wild challenge. So there are examples of pictures in dataset. The usage of CapsNet fitted for emotion recognition with 7 labels made it possible to obtain the baseline with mean squared error equal to 0.84 by feeding aggregated emotions into regression CNN. Analysis of faces, bodies, and the whole image lead to MSE equals to 0.56. And the first place in this challenge, where MSE equals 0.52 on validation set, was obtained by hybrid CNN with analysis of scene, faces, skeletons, and UV coordinates. Unfortunately, all these techniques are very slow and can be used in embedded solutions for video analytics. And we proposed a fast approach consisting of face detection by using MTCNN aggregation of facial features, age, gender, and embeddings extracted by multitask mobile net. Prediction of group cohesion and classification of emotional background using multi-output convolution neural network. Study on the dataset from challenge demonstrated that our approach achieved an improvement of quality and even to reduce the running time of an algorithm's work. In order to speed up the decision process, we propose to use the lightweight multitask mobile net. In addition to facial embeddings, it can predict age and gender of each person, so that we decided to use these features also. Next, it's necessary to aggregate facial features into a single descriptor of a photo. And then we compute the mean of L2 normalized features of individual faces. Our neural net consists of the fully connected lawyer with 600 neurons and relo activation, conv 1D, max pooling 1D, flattening, dense with 200 neurons, and 2 output lawyers, namely softmax with 3 neurons for emotion recognition, and 1 neuron by linear output for group cohesiveness prediction. Here you can see proposed pipeline of the model. We proposed a lightweight solution based on facial feature extraction with mobile net, and we propose to extend this network by computing the average of its outputs for all detected faces and feed the overall descriptor of a group of people into a simple multitask neural network for emotion recognition and cohesion prediction. Also, our approach has been implemented in a demo application that can simply predict group cohesiveness and emotions given an input photo or video from web camera. There are some examples of application work. In the first experiment, we used conventional ResNet 50 trained on VGFace2 dataset to extract facial features. We used ordinal regression methods from MORT package and CutBoost. Their hyperparameters have been tuned on the part of training set using cross-validation, particularly grid search. The results on validation set are shown in table. Here you can see that the lowest MSE is obtained for logistic squared error ordinal regression with regularization, which will be used in the next experiments to choose the best facial descriptor. We compared three CNNs for feature extraction, namely VGFace 16, that extracts 496 features, ResNet 50, and multi-output mobile net that extracts 124 features. The dimensionality Keras also MobileNet predicts age and gender. Keras framework with TensorFlow version 1.15 backend were used in all experiments. It is surprisingly that the lightweight descriptor MobileNet outperforms the DIQA CNNs. For example, VGFace2 that achieves the state-of-the-art results in face recognition. In order to speed up our decision, we examined the usage of principal component analysis and processed only a small number of first principal components. Here we compared our simple multitask neural network with one convolutional layer and engineered networks with 2 and 3 sequentially connected Conv1D layers. These models were fitted with batch size 32 during 100 epochs with early stop callback. Here's lowest MSE. MSEs are achieved by a network with one convolution layer. However, usage of all principal components in proposed approach leads to the lowest MSE for cohesion prediction that equals 0.63. It's lower than compared to an ensemble of several complex methods. We achieved MSE of cohesiveness prediction on a validation set is 0.21 low when compared to MSE 0.84, the baseline from the challenge. The proposed approach is implemented in publicly available demo application where we predict age and gender of each person and predict the cohesiveness and emotion of the whole group. It's rather fast, plus 10 FPS for at most 16 persons in a group using NVIDIA GPU. And our preliminary results demonstrated that our model can be used even at Android mobile device. Our approach is not obviously the best one, as our MSE validation set. However, the running time is much worse. In future work, it's necessary to examine state-of-the-art face detectors, for example, retina face instead of MTCNN, in order to locate more faces. However, it's still possible that better facial detectors won't lead to the better quality. And moreover, it's important to extract the faces from a group photo, which significantly influences the overall cohesiveness score. That's all. Thank you for listening.
So thank you for your presentation. Ilya, maybe I'll just start with my question. Could you say something about privacy of your research? I mean, for example, predicting emotions on some political meetings may lead to leak of privacy and may be misused. So is it possible to kind of switch your research from detecting people emotions to counting emotions without any personalized details about emotions on people in the crowd?
Yes, we trained this multitask neural network on data set that were presented in emotive challenge, and as I know, this data set is public. As for using in meetings, I think this solution can be implemented only for companies, and it will be used only by employees.
Okay, thank you very much. Any other questions from participants? Okay, let me just a moment check translation. So if no questions, again, let me thank you for your presentation, and we'll be moving to the next speakers. The next talk will be automatic grading of knee osteoarthritis from plain radiographs using densely connected convolutional networks. Authors Alexey Mikhailichenko and Yana Demyanenko. Correct me if I properly name your names, and please share your presentation if you are ready.
Hi everyone, are you hear me?
Yeah, we hear you well.
Fine. So let's start. I want to present you research about the automatic grading of osteoarthritis using densely connected networks. Osteoarthritis is one of the most common diseases of the musculoskeletal system. There is no effective treatment for osteoarthritis, so the only way to reduce social costs is early diagnosis when it's still possible to slow down the process of joint destruction. The main signs of osteoarthritis of the knee joint are joint space narrowing and the presence of osteophytes. There are various systems for assessing the progression of knee osteoarthritis. One of the standard is a Kellgren-Lawrence grading scale. There are 5 grades of osteoarthritis severity in the scale. We used the osteoarthritis initiative dataset. It's a standard dataset for research in this field. It contains an archive or clinical data from more than 4,000 patients. There you can see the distribution of joint area images by Kellgren-Lawrence grades. There are 2 steps in assessing knee osteoarthritis from raw X-ray images. Knee joint localization and classifying the detected knee joint into osteoarthritis grades. There are several methods for localizing the joint area. One of the simplest methods is the localization of the knee joint area by the mass center of the histogram, calculated by the sum of intensities of image rows. Such approaches are very strict on the quality of radiographs and have many limitations. Methods using various classifiers, for example, SVM or something like that, are more universal and accurate, but also have some problems. Solutions using deep learning have also been proposed. For example, here you can see trained from scratch a fully connectional network from one of the works. In our research, we used a single shot detector. This network composed of 2 parts: feature maps extraction from the input image and applying convolution filter to detect object. For feature extraction, we used fine-tuned mobile net. It achieved high accuracy comparable with the state-of-the-art approaches, while having significantly less number of parameters and high speed. You can see a few examples of detection knee joint with SSD. For the evaluation of results, we used intersection over union, which also is named Jacquard index, between the automatic detection and the manual annotation of each knee joint. The table shows the percentage of correctly detected knee joint based on the Jacquard index values greater than 0.25, 0.15, 0.50 and 0.75. So we can say that the SSD model achieved the results comparable with the current state of the art and a bit improve the accuracy in comparison with them. And now let's speak about the main task of this research, the classification of osteoarthritis. The first deep learning approach applied to osteoarthritis classification used a trend from scratch. CNN consists of 5 layers and 1 fully connected layer. So it's a very simple convolutional network. It achieves classification accuracy at about 61%. An interesting approach is based on the ensembling of 2 neural networks with 7 independent fully connected layers. To connect these convolutional and fully connected layers, authors utilize an average pooling layer after the convolutional block. This model reached an average multi-class accuracy of just over 66%. One more approach utilizes deep Siamese networks. They use the same symmetry in the image, and their model consists of 2 branches, each of which works with different parts of the knee joint. The classification accuracy is it's about 67%. Other research used other loss functions instead of cross-entropy loss for training, and networks of well-known architectures like ResNet, VGG, Inception, and like that. For example, in one of the works, VGG was trained with a special loss function and were achieved result of 69.7%. In our study, we investigate the use of networks from DenseNet family. We were interested in the claim that dense connections have a regularizing effect, which reduces overfitting on task with the smaller training datasets. It means that dense nets work well on small dataset, which is important in our case, if you remember a few first slides. We consider networks of different depths, both trained from scratch and pre-trained on the ImageNet, and evaluate different loss functions. Also, we used different ensembling methods. We use the most common ensemble approach, unweighted averaging. We picked the best models, summed their predictions, and propagated them through the softmax layer. We consider different sets of model as part of ensembles. The same network with different training checkpoints, the same network with different random seeds, and an ensemble of networks with different depths. In our case, it were DenseNet 121 and DenseNet 161 as the composition of their networks. And in the table, you can see the detailed classification metrics for all mentioned approaches. In this slide, information about DenseNet is given in the limited form and only for the best results at training with cross-entropy loss and ensembling of 3 models trained with different random seeds. More detailed information about other loss functions or other ensembling methods, which are a bit worse than current results presented in this slide, can be found in the article. Analysis of the confusion matrix and classification matrix for each class shows that the main misclassification occurs between neighboring classes. Moreover, the biggest error is noted for Kjellgren-Lorentz grade 1 due to the small variation between grade 0 and grade 1. This fact was also noted in previous works. The analysis of the saliency map for the final model shows that the main pixels that make the greatest contribution to decision making are found directly in the area of osteophytes and in the joint space. Of course, due to the high requirements for accuracy in the healthcare sector, the applying of fully automatic classification methods can be dangerous on this stage and with this accuracy. However, the described method can be used to help an expert to make a decision by providing additional information like probability distribution of osteoarthritis grades or tension map. And finally, this list is presented the main results of the research. One of them, the classification accuracy doesn't depend much on the accuracy of the joint area localization. It's a good news because it means that in future works we can skip this part and concentrate on the classification part. Other conclusions you can see on this slide. All source codes and trained models also are available on GitHub. You can try to reproduce results which mentioned in this slide. Thank you for your attention.
Yes, thank you for your presentation, Alexei. We are ahead of schedule, so let me just ask a little bit more questions on your work. So first of all, the idea that stack more layers does not work out, well, it's usually true for any kind of image classification problems, and it's quite obvious that it will be similar or close to similar results. So my question is, what are your ideas for future work of other architectures that may be used? And what's your opinion about that using GANs, which try to generate and simulate different augmentation of your images may really benefit the resulting accuracy for your case? That's the first question. And the second question is about, we're talking about medical data analysis and something about use of your model with regard to ethical in medicine. So could you also comment a little bit about this part of your work?
Okay, thank you. So what about future works? We plan to try different loss functions. We have a list of some loss functions which we didn't try still, and also it's of course trying to other models. I know one work which has better results than results in our work, but that results looks too good, so it need to be reproduced, checked, and reproduced. What about GANs? It's a good question. We used augmentation for our dataset, like random rotation for a small angle or horizontal flip, but I'm not sure that again can reproduce a real images of this osteoarthritis features, or I don't know, I'm not sure in the quality of this reproducing results.
Yeah, and I understand this part of the answer. So
because
maybe
it's very.
It's a question how you need to argument it, because even horizontal flip of knee image will not give you anything close to reality, as far as I understand.
Yes,
so
of
maybe
course.
some special distortions or noise analysis may benefit for you. But again, in general, as far as I understand from your talk, you have this kind of slide between two parts of the legs, in which, based on which you could detect whether whether the patient has disease or not. And maybe a GAN can learn generating this kind of images with focusing on parameters, how the distribution of the lengths in vertical plane with respect to properly cropped and rotate segment for which you make your attention map, for example, it may benefit.
Yes,
but still, it's very good comment that it's hard task to augment medical data.
Yes. So what about? Sorry, what was your
second question? Was about usual question about ethics of using AI in medicine and how your current results can be regarded with respect to this.
Oh, we used a public data set without any names or second names. It's just data of it was just example of radiographs with some descriptions like age or weight or something.
Yeah,
like
I understand that data are anonymized, but basically the question is how well your results to be included, for example, in medical practice. So could the doctor use your results of DenseNet to make a diagnosis or not? And how well is this 71% of accuracy with regard to real world application?
Okay, I got it. In current stage, it couldn't. It can't be used directly. Yes, of course. But if we, for example, I tried to train DenseNets not for 5 classes, only for 2 classes, non-osteoarthritis and osteoarthritis, and accuracy in this case were more than 90%. And it's pretty good results, but it can be used more as assisting system for expert to help to. I think you guys what
yeah, I
think
understand.
about.
And maybe the last question again, what is the difference between misclassifying different classes? I mean, again, from medical point of view, what is worse to classify longer stage of disease or earlier? I mean, just from real world situation, what's the main problem of improving accuracy when you are misleading some classes?
Actually, in this case, it's misclassification between grade 0 and grade 1 isn't matter because grade 0 and grade 1 is not osteoarthritis stage. So we can say that the man with grade 0 or grade 1 is doesn't have diseases, osteoarthritis. But
okay.
if we improve this part, it can be significantly improve all accuracy of method.
Yeah, I understand. Thank you very much for answering a lot of questions from my side. Any questions from participants who'd like also to dive into medical data analysis? Okay, if no questions, again, I would like to very much thank the speaker for the presentation and very fruitful discussion. Thank you very much. And
thank you
we are
very
going
much.
to the next presentation, which is named a novel approach to measurement of the transverse velocity of the large-scale objects. The authors are Ivan Goncharov, Alexey Mikhailichenko, and Anatoly Klyshenkov. And you may start your presentation.
Hello, can you hear me?
Hello, we hear you well.
Perfect. Yeah. May I start?
Yeah, you may start. We clearly see your presentation.
Perfect. Good day, everyone. Thanks for joining. I'm Ivan Goncharov, and on behalf of my colleagues, today I present a novel approach to measurement of the transverse velocity of the large-scale objects. And let's get started. First, let's consider our outline. In the introduction section, I'll tell you why we need to solve this problem at all. We'll discuss our motivation, limitations, and specifics. In the third section, we will briefly review the existing solution and move on to our approach, which also consists of several subpoints. Of course, we will discuss the results and talk about accuracy. As you can see on this slide, the method was developed for implementation in an existing system. You can read more about it in the link at the end of the presentation. But here it is worth mentioning only the specifics and limitations that are caused by this fact. They are as follows. The measuring device, in our case, it is a stereo camera, is located in the immediate vicinity of the object, 1 to 2 meters. The object moves strictly along the lane, which allows us to place the camera so that the subject will move strictly parallel to the baseline. In lace and therefore in the camera field of view, it is not more than one object, which is also a limitation of the environment. Given all the above, there are no suitable open data sets, but we had access to...
Не убрал. Оставьте, я уберу.
Okay. Given all the above, there are no suitable open data sets, but we had access to real-world data and tested the proposed solution for more than a year. The most important task for us was to calculate the speed of the object at each moment of time during the passage past the measuring system. And of course, we had the strictest requirements for the accuracy and the results obtained. This slide says this, but I'll repeat. The proposed solution operates at 250 frames per second, and the measurement error doesn't exceed 1.5%. We'll talk how we calculate accuracy at the end of the presentation, but for now we will move on to a brief overview of existing solution. Links to these works can also be found at the end of presentation. And on this slide, I'll briefly describe what the method proposed by the authors boils down to. As you can see, all methods are somehow reduced to one problem, the solutions of which I pointed out with an exclamation mark. It is the dependence of object speed on distance, and we have approached this problem comprehensively in a different way. Finally, let's move on to our method. As I said earlier, we use a stereo camera, and the next slide contains a visualization of the proposed approach. We have a stereo camera with parallel optical axis. Also, we have an object moving strictly parallel to the baseline. If we fix coordinates on the left frame of the stereo camera, let it be x, y, and we will continuously move the object parallel to the baseline until the same point that we have already fixed in real world will be in the same coordinates, x, y, but on the right frame. In this case, it will mean that we move the object by a distance equal to the baseline of the stereo camera. It's obvious that this fact will work at any distance from the stereo camera. And finally, to get the speed from this fact, you only need to know the time when we fixed the object in the first frame and when it appeared in the same coordinates on the second frame. It's better to move from theory to practice and demonstrate a more visual interpretation. We use two high-speed cameras as stereo camera and infrared illumination for operation in low natural light or maybe at night. As already mentioned, the stereo camera is located in the immediate vicinity of the object. An example of input data demonstrates how much. Of course, we use calibration and therefore rectification. We use standard stereo calibration algorithm available in the OpenCV library. And an important addition to it is the pre-filtering of calibration patterns. We found out that it is enough to leave the minimum possible number of normally distributed patterns on the frame to improve the quality of camera calibration by 20% according to the RMSE metric. Before discussing our matching function, it's worth paying your attention to some features of the input data. The camera angles of the subject are completely the same for left and right cameras due to their parallel arrangement in stereo pair. Position of the object can only be changed along the coordinate axis x for the image plane due to perpendicular arrangement of stereo pair relative to the lane. To determine the similarity of images with the difference model function, the formula of which is shown on this slide. It's obvious that the minimum of this function will correspond to the most similar frame. In confirmation of the above, on this slide, you can see the graph of this function and the comparison of frames. Reference that one on the top and corresponding to the minimum, the bottom one. The accuracy of the speed measurement is affected not only by the quality of the target search function, but also by the resolution of the proposed approach. In the proposed method, the speed is determined by the time the pixel coordinates of the object match on the left and right frames of the stereo camera. Since the frame rate is not infinite, the time obtained during stereo frame matching will be discrete. This directly affects the resolution of the method. Obviously, the resolution is inversely proportional to the discreteness. You can see as the speed increases, the discreteness of measurement increases, and therefore the resolution decreases. That fact clearly demonstrates the need to increase the frame rate. How? Binning and decimation operations are available in most machine vision cameras. It allows to increase FPS by reducing the frame size. Changing the frame size would mean having to recalibrate the camera. However, the camera matrix can be scaled in proportion to the change in frame size. This is a fairly simple arithmetic operation that follows from the properties of the camera matrix elements. You can find more details in our paper, but we will move to the results. On this slide, you can see several speed graphs of various objects as they pass by the measuring system. You can see how the resolution of the method changes with changing speed. The lower the speed, the smoother graph is, and the discrete become almost invisible. We didn't use the proposed method as a separate solution. As mentioned above, the proposed method is a part of system for non-contact measurement of large-sized object using laser triangulation. Therefore, the accuracy of the proposed method was checked by comparing the actual length of object and the results obtained. Of course, this doesn't directly indicate the accuracy of the speed measurement, but it provides indirect confirmation of the validity of the results, since many experiments were performed with different length and nature of movement. References. Thanks for your attention. Feel free to contact us and feel free to ask your questions.
Thank you, Ivan, for your presentation. It was very interesting. Maybe my first question will be regarding the following situation. So your camera, which moves the velocity, see objects from the outside. Am I correct? As kind of road cameras, for example, may be used in this scenario.
Can you repeat your question? I didn't clearly understand.
It's my question is camera is outside of the objects that you try to detect the velocity, or it is inside the object?
No, it is outside the object, of course. It is located on some kind of
a kind of road cameras which give us penalties if we exceed the velocity. And my question is the following. Have you seen any kind of self-supervised methods which does not require any kind of ground truth, for example, for depth estimation or for velocity estimation, but try to regularize their prediction from the consequent frames and somehow use it for benefiting the model, and for which you could use weak supervision if there are not so much open data sets?
We didn't ever try these methods because of one major thing. Any supervised or unsupervised methods, maybe deep methods, are not able to operate on such with such high frequency. In the beginning of my presentation, I mentioned that we need to know the object speed in every moment. So yes, it is very interesting for me, but it is not suitable for current task.
Okay, but this kind of methods can be interpolated. I mean, usually objects has no abnormal states in their movement, and for example, for stable movement, you could run some deep learning-based solution with some discretization, and after that interpolate the results, and you'll be pretty much close to the expected result. Is it not working for your case?
I think no. May I return to some previous slide? And here you can see how the speed changes during the passage. So I think it would be very hard to interpolate such kind of movement when the car is stopping now. It is not always like smooth movement in fixed speed. In this case, I think it will be a perfect one, but you can see how speed changes in 3 seconds maybe.
Mm-hmm. But could you maybe then clarify how it affects some decision making based on this velocity? So what is the main motivation that you need exact velocity value for each moment?
Our motivation is to measure the large-sized objects, and for this we need such frequency. I already mentioned that it is not separate solution, and if we worked on just speed estimation problem, it will be simpler than that one.
Yeah, I mean, because it's like if you get some penalty, for example, I don't know, for car moving on the road, yeah, and it's usually you could calculate the velocity change, for example, in some sliding window and compute some pooling strategy. I don't know, average or max value, or some quantile and so on. So you could just make some decision on partial information, and it just was interesting how it's affected in the complex systems that we are using. Again, thank you very much for answering my questions. Any questions from the participants? Okay, if no questions, I would like again thank the speaker. It was very interesting presentation and very actual problem. I would like to
thank you.
Thank you very much. I would like to ask the last presenters in our session with the talk on supervised training in denoising networks, the authors Alexey Kovalenko and Yana Demyanenko. So yeah, much appreciate for presenting your work as a conclusion to our session.
Okay, do you hear me?
Yeah, we hear you well.
Okay, and do you see presentation?
Yeah. Yes, thank you very much.
Okay.
You may start.
Okay. Dear participants of this conference, in presented work, we propose an approach of unsupervised training denoising neural networks. Any image captured by photosensor contains noise. We can represent image signal as a composition of a clear image and noise component which sampled from undefined distribution. This denoted by Formula 1 on the slide. And the noise problem can be defined with optimization solution of functional denoted by Formula 2. Convolutional neural networks can efficiently approximate of projection phi from Formula 2. But when we try a neural network, each process require labeled training data set. When for each noisy image, there are correspondent clear image. It is real problem because we can get an absolutely clear signal during making photos by photosensor. This problem could be solved by averaging of series with large count of images of fixed SEM. On figure 18, you can see example of series with corresponding color histograms on bottom. Researchers from NVIDIA proposed an approach for unsupervised training denoising models on data sets which contains clear samples. Let there be two images, A and B. These images contain common clear signal I and different noise components, alpha 1 and alpha 2. The main idea of this method is training a neural network predicted image A as the input with image B as output, and vice versa. Assuming that the noise was obtained randomly, the neural network isn't able to predict it. And therefore, during training, the neural network reconstructs the image with some losses. And this approach has disadvantage. If you use only a pair of images of one scene during training, result has large losses of the useful signal during neural network prediction.
on the other hand, we can obtain image series and averaging them and train network predictors as output mean image of series by supervised method. But even in this case, averaged image still contains noise component. You can see it on figure 3. We propose novel approach which solved this problem. This approach combines a theoretical background of noise-to-noise work and supervised training method. You can see on figure 4, you can see train samples building scheme. We take series of images with the same stem, and instead of averaging all images, we select one image from series and then average the series without this image. And next we train neural network predict average series by with input selected image as an input signal. In this case, the noising net learn approximate a clear signal with additional features which extracted with network due to theory from noise to noise work. Analyzing of noise image Fourier spectrum, you can see that the noise component locate in the high frequency component of image signal. On the slide, you can see from left to right. You can see original part of image, third dimensional Fourier spectrum of a grayscale image, and next you can see rendering of a Butterworth filter. Next you can see low frequency component of the image which obtained by Butterworth filter, and in the end you can see high frequency component of the image with noise component. Taking into account such a distribution of noise component, we implement our architecture with the separation of input signal to high frequency and low frequency signals with Butterworth filter. Separate signal component has processed with blocks of convolutional layers. In the scheme, the scheme of this architecture you can see on figure 6. Next, this high-level features are concatenated to one tensor and processed by third-dimensional convolutional layer. We choose third-dimensional convolutional layer because this allows trying this layer to extract common features between independent channels. Then these features processed by finished block. We collected data set with 125 images, and we train a model by another training approach for results evaluation. On the figure, on the slide, you can see visual compression of results. Under the cursor, you can see averaging image with series. Next, you can see input noise signal. Next, you can see results of noise to noise approach, and you can see that this image are blurred. Next, under the cursor, you can see results of noise to self approach. Next, noise to void approach. And this approach took good results. So, and for compression, we take classic noise cancelling approach. It is non-local means denoising from OpenCV library. And next, you can see results of deep image prior work. Each work based on variational autoencoders. And in the end, you can see results of our work. And you can see the minimum loss of a useful signal. And below is the table, you can see comparing approach with peak signal to noise ratio metric. And on the slide, you can see a link to GitHub repo with implementation. Also, the link is available by follow QR code. Thank you for your attention.
Thank you for your presentation. Maybe my first question will be regarding your architecture. So you mentioned that you use 3D convolutions, and they're usually hard to train and require significant computational resources. So could you maybe clarify what was used from hardware for training the network, and do you maybe have some troubles when learning the network from this architecture?
So, can you repeat please the question, and what problem we faced when we train this architecture?
Yeah, so regarding using 3D convolutions, because they are usually hard to train and require significant computational resources for training.
No, no, we haven't a problem with training this layer because no, each block contains one layer. Is this one layer has small count of features and not overfitting on our task, and we achieve good results.
Mm-hmm.
And we can change this convolution layer to set of third-dimensional layers, but in this case, classic convolutional layers don't extract features between channels.
Mm-hmm, mm-hmm. I understand. Okay, thank you very much for answering my questions. Any questions from participants? Okay, if no questions, I would like to thank the speaker again and
thank you.
Giving the word to the chair of Computer Vision Track, Andrei Savchenko. Andrei, your
Yeah. Thanks for leading the session, and thanks everyone for visiting it. It seems that we completed our CV track at AIST, and we will be really glad. We are very glad for all authors. We encourage them to prepare new papers for the next edition of AIST, and thanks everyone for being here in this Friday evening. So thanks, and let's see you offline at the next edition of AIST. I hope so. So what's next about?
We have 5 minutes break before
before invited to talk. So thanks everyone. Let's have a break.
Dear colleagues, shall we start?
Yes, but I don't see anybody for the moment except the white screen. Hello, can you hear me?
Yes, we can.
Yeah.
Yes, everybody can hear you.
Okay. Dear colleagues, let's start now. My name is Olesya Koltsova, and I'm the head of Laboratory for Social and Cognitive Informatics in St. Petersburg. And I'd like to introduce our guest speaker today, Professor Santa Fortunata. Santa Fortunata holds a PhD in physics, and that tells us a lot about his vision of network science and computational social science. He has also worked in a number of European universities in the field of complex systems until he moved to the United States, to Indiana University, where he has Network Science Institute. It's a research unit affiliated with a larger Center of Complex Networks and Systems Research. And it is actually a very interesting place to be, with a lot of outstanding scholars there. Santa Fortunata is known, first of all, for his works in community detection in graphs, in particular for his idea of resolution limit, which also stems from physics. And today he's going to talk about consensus clustering in graphs. And this consensus, although Santa Fortunato tells us he is interested in computational social science, this consensus is not about the consensus we usually mean in social science. This is actually about the stability of graph partitions across different runs of the same algorithm on the same data. And this is a very natural problem to be addressed in physics, but it is much more seldom acknowledged and addressed outside physics as a discipline. And so there are many unresolved issues here, particularly in the sphere of clustering and graph partitioning. So I find that this is a very important topic, and I'm sure that we will hear a very exciting presentation. So Santa, the floor is yours.
Thanks a lot, Alessia. Thanks, and nice to see you after a while, you and I see Sergey and others. And thanks also, Dima, for inviting me over Messenger, actually, a few months ago. I didn't know about this event. So can you hear me well?
Yes, we can.
Yeah, so let me share the screen and say a few things about this topic you just announced. So let me also go. Okay, can you see the first slide?
Yes.
Okay, so like Alessia said, somehow, I mean, I spend a lot of time dealing with this topic of finding partitions in graphs. And today's topic is not about specific algorithm to find those partitions, but it's about checking the stability of partitions. So basically dealing with noise. So let me say a few things. First of all, I mean, I want to acknowledge the collaboration with my PhD student, Aditya Tandon, who is the main driver of this paper that you see. They're going to discuss a bit more in detail in a few minutes. So this is a talk about community structure, which regardless of the discipline you're coming from, is really a transversal topic, because when you want to simplify the structure of a network, you often break it down into pieces, and you want to know how to do it fast and well. And today, of course, I will focus about specific things. So community structure is basically a modular organization of a network, like in a very schematic example that I'm showing here, in which you have somehow, in this case, these three groups of nodes, which are tightly connected to each other, but sparsely connected between each other. So how to find those things and why this is important? This is, based on the numbers, really, the single most popular topic within network science. So most of the highly cited papers in this topic are about that, because it's an important methodology that is it's used in many different domains dealing with networks.
So the reason why it's useful or even important to do this operation, so to break the system into pieces, is we want to know how it is organized. It's like identifying the organs in a human body. You want to identify the features of the nodes because you assume that groups of nodes are indicate that the nodes have similarity, so that they may share some features that can be revealed by the topological organization. You may also classify the nodes based on their position on the classes. Once you have a partition like this one that you see here, you can, within each cluster, distinguish nodes which are somehow fully embedded within their clusters, like the ones, their cluster, with which the ones that I'm circling here in red, or nodes which are connected also to nodes of the other classes, so-called gatekeepers, which are the ones that allow you somehow to move from one piece of the systems to another. But it is a difficult problem. It is an ill-defined problem first, which is why so many people are still working on it. You know, it's an unsupervised classification problem. You don't know exactly what you're looking for. You may have ideas. There are different ways to conceptualize it. But there is also an agreement about some of the main guidelines. So basically what we would like to do here, this is the adjacency matrix of this network. Here is 15 by 15. There are 15 nodes here, where the ones indicate that there is a link between nodes with those labels, and empty space much better than zeros, because otherwise this table would be, this matrix would be dominated by zeros, indicate that there are no links between them. So if you take a look at this matrix, you don't seem to recognize any structure, nothing that can make you think that the system has a model organization, which is clearly displayed by this diagram. But if you rearrange the labels of the nodes here in the order of the modules, putting first the red, then the blue, then the yellow, but you can of course proceed in any order, the very same matrix takes an approximately block diagonal form, which shows you indeed that there are groups of nodes which like each other more than they like the other nodes. So basically, graph clustering or community detection or community discovering means basically going from here to here. And there are many different ways to do it. I'm not going to discuss about the specific ways to do that. I'm going to discuss about the fact that most of these methods, if not all of them, are stochastic in nature, which means basically that they may produce different answers if you change the random seed that you choose to run those algorithms, because very often you have to choose random numbers when you run a Monte Carlo, when you optimize a function. So, and when we deal with measurement errors, what you have a bunch of measurements that to make a sense of this collection of measurements. Instead of picking one of them, you just make some average and then compute something like, some estimate of the error, I don't know, for instance, variance standard deviation. So this is what you do with numbers. So what happens with partitions? I mean, this is the famous Zachary Karate Club. It's a very well-known social network, small one, 34 nodes, 78 edges, which is being used widely to test clustering algorithms and also for other things. It's a very nice story to tell. This is this club, then it splits in two parts. The two parts are indicated by the squares and the circles here. And the goal is basically to see, is my clustering algorithm good enough to separate the squares from the circles? Is it able to recognize that indeed there are two groups here, even though of course the system is connected? So some of them can do it. Actually, many methods now can do this work very well. But you see, I just apply here InfoMap, which is a very, very well-known algorithm introduced in 2008 by Roswell and Bergstrom. I run it once, I get this partition indicated by the color in 3 groups. I run it again, and I get this other partition in 4 groups. So which one shall I pick? How can I somehow make sense of this slightly different results? So sometimes it can also be very different. This is a small system, so you have also less entropy, right? Less variability in the possible outcomes. But if you have a much larger system, you can also see more differences. So, So this is what we're going to do here. So how do you basically average partitions? Many methods, like many clustering methods, are stochastic, so they're non-deterministic. You run it multiple times. You may also end up getting often the same answer, but you will also get some answers which are not aligned with the main answer. And of course, this seems to be some kind of strange questions I'm asking, even ill-defined question within an ill-defined problem, because many methods which are stochastic are based on the optimization of a quality function. So if I have a bunch of partitions, I have a number attached to that, which is the value of the quality function for the specific partition. So if I believe my method, I should just get the one with the largest value of the score. So even if I get many answers for my method, in principle, there is an ideal solution or a best solution, which is the one with the largest score. So in a sense, it means that this all premise that I'm making about averaging partition is kind of senseless, because in many cases, I do have a way to single out a partition from this ensemble of results that I get based on the score of the quality function attached to the partition. Not all methods work like that, but in many methods, the most popular ones do, including Infomap, that I just mentioned earlier. What I'm going to show you here is that you can actually use also the suboptimal partitions that you can get by running the procedure multiple times on the same data set, and obtain actually more precise, more robust results by doing that. This is an idea that dates back to a paper in 2002 by computer scientists, as you see, Journal of Machine Learning Research, Strel and Ghosh. It was originally introduced for data clustering, so clustering of objects or data points. But it's a thing, I mean, it deals with partitions. So of course, as long as you have partition, it doesn't really matter if it's partition of points, of items, generic items of nodes of the graph, is the same thing. So the idea is searching for the partition which is the most similar on average to the input partition. This is called median or consensus partition. So you have a bunch of partitions, so divisions of your network into groups, and you find this median partition. It's a well, I mean, once you define what similarity means, how to compute the similarity between two partitions, which you can do with standard measures like normalized mutual information, variation of information, and others. This is a very well-defined problem, because you have a measure and you explore the space of partition and you find the one which is most similar, which has the largest average similarity with each of the input partitions. However, it is a difficult combinatorial optimization task. The space of partitions grow faster than exponentially with the number of nodes. So it's not obvious how to do this exploration in a precise way. So, but you can, of course, use approximations. And the approximation that has been used most often, it's the one that I'm going to use and introduce to you later, I mean soon, in fact, is a greedy solution that adopts what is called a consensus or co-clustering matrix. I'll be calling it mostly consensus matrix, but co-occurrence, co-clustering, consensus, again, given how many different communities deal with clustering, often you may find that the same thing is called in many different ways, across communities. So I'm going to call it consensus matrix. How does that work? The consensus what is a consensus matrix first? So a consensus matrix is a matrix whose entry Dij tells you the frequency that the nodes I and j are in the same cluster in the input partition. So you have, say, 100 input partitions, and you check in each of them if I and j are in the same cluster or not. If they are in the same cluster, you mark 1 if you want. If you're not, you mark 0. Then you sum all the ones, you divide by 100 in this case, because you have 100 partitions. So this is a consensus. So basically it tells you how frequently, what is the probability that two nodes are in the same cluster in those input partitions. And this is the basic idea underlying the procedure that we presented in 2012, in fact, and we refined last year in this paper that I introduced at the beginning of the presentation, is that you find the cluster. So basically, once you have a consensus matrix, you consider this as a network matrix. So as a new network, if you want. Of course, it's weighted because the elements are numbers between 0 and 1, this frequency that I mentioned. But a lot of methods can be applied also on weighted graphs very easily. So you cluster the new matrix, you get another set of input partition for the next step of the iteration of the routine. You combine those partitions in a new consensus matrix, and you repeat the procedures until the final consensus matrix you find is block diagonal. Basically, it has it is composed of disconnected cliques, indicating basically that you end up with the same set of partition. At the end, you have a set of partition which are all identical. So this is procedure which is guaranteed to converge. You always get to that result, and that's your result. And then that will be your approximation to the median or consensus partition. So this is the whole idea. So you have a bunch of input partitions, you create a consensus matrix, you apply your method again on the consensus matrix, treating it as a weighted matrix of a network. You get another set of partitions, you create a new consensus matrix, and you do the same thing until basically at the end, all partitions are the same. So this is the main idea I'm going to sell you today. And what I'm going to tell you next is how to do it in practice, how to make it faster, and what kind of results you can get. So this is more detail what we did in that paper in 2012, which is actually very popular now. A lot of people, especially in network neuroscience, are using that idea. So you start from a network, G, with n nodes and m edges, and you pick a clustering technique. It doesn't even matter which one you take, as long as it can be applied on weighted graphs as well. I mean, weighted or unweighted. So you start from the input partition, you apply your technique A on G np times, where np is the number of input partitions you want to find. You usually get different results. You construct your consensus matrix the way I told you. So basically check how many partitions for I and J, for two nodes I and J, in how many partitions these two nodes are in the same cluster. And you divide by np. Then you, I mean, by doing that, of course, you may end up dealing with a progressively denser matrix, which of course, makes calculations slower. So to make this matrix sparse again, you set a threshold, which is pretty much the only parameter of this procedure, tau, and you set to 0 all the elements below the threshold. So now you have a sparse consensus matrix. You treat it as a weighted matrix of a graph, of a weighted graph, and you reapply your technique A again, np times on that technique. That gives you a new set of partitions. You can construct another consensus matrix following the instructions of point 2 and 3 to sparsify it until you get this block diagonal matrix. This is a simple example that tells you what this thing can do. Very simple. So you have this graph with 7 nodes. You have a natural partition here in a group of 3 and a group of 4, and you have 4 different partitions for that. 2 of them are the appropriate ones. 2 of them seem to be wrong, right? Because there are these new green nodes, which is basically it's a 3 partition. Number 3 is 3 partition. Number 4 is also 3 partition. So they seem to be very noisy compared to the ground truth, if you want, which is this. If you create a consensus matrix out of these 4 by doing that game that I told you, you get this thing here, which is now, as you see, a weighted matrix, as indicated by the thickness of the lines, which tells you, how big the frequency, how often these 2 nodes, for instance, in this case, appear in the same cluster. So you see, for instance, these 2 nodes are always together, are always blue, you see, in all 4 partitions, which means that gives you a frequency, the highest possible frequency of 1, which is this one, and that's why I'm using the thickest line here. Same goes for these 2 nodes, whereas the other ones are not always co-clustered in all input partitions. So we see what happens basically. At the end of this first round, you end up having a weighted graph, which is clearly more modular than the initial one, because now the edges connecting the 2 groups that you're expected to find are much weaker than the other ones. If you repeat the procedure, eventually these 2 things will disappear, and you end up with the 2 different groups in this case. And that's the principle of this whole procedure. So you see, even though there were 2 answers which were correct and 2 answers which were clearly wrong, the procedure still gives you something which enables you to detect the 2 groups more easily than operating on the original graph. So to check if this trick allows you to find clusters more easily than by working on the original graph, we used our benchmark graph, the LFR bench, what is now called the LFR benchmark, that you can find on my website under resources. It was introduced in this paper, which is super cited now. You see it here, a figure representing the benchmark. It's basically an artificial network with built-in communities. So in which you know basically which are the objects that you have to find. As you can see here, they're indicated by the colors. And the characteristic of this benchmark is that it's meant to be more realistic than the benchmarks that people have been using before. We introduced this one, in that clusters have different sizes and nodes have different degrees. In fact, they are both power law distributed. So you see from the size of the nodes, which is proportional to the number of neighbors, to their degree, that there is a broad distribution in both things. And also you see there are small groups, there are large groups. This is more a proxy of what you could think a real networks look like. So then there is a mixing parameter mu, which tells you how blended these different pieces are. If they are well separated, mu is low. If they are kind of mixed with each other, very well mixed, so harder to find, mu is large, and mu goes between 0 and 1. So when mu is close to 0, these groups are very well separated and very easy to find for most algorithms. When mu starts to approach 1, then everything is mixed and it's going to be different. At some point, there are no clusters anymore, so no good methods can realistically find them. So we use this thing and we produce diagrams like this one. So mu, this parameter that tells you how separated the clusters are, is on the x-axis. On the y-axis, you have the score that tells you how similar your result is to the planned partition, to the natural partition of the system. So we're using normalized mutual information for that. When it is 1, it means that the partitions are exactly identical. When it is close to 0, it means that they are very different. They are basically, you don't do it no better than random, like comparing to random partitions. So obviously, what happens, as I said, when mu is low, here, for instance, this is Louvain, the Louvain algorithm that now a lot of people are using. Each panel here corresponds to different algorithm indicated by the label propagation method, simulated annealing still modularity optimization, like Louvain is based on the optimization of the same quality function, and also this method is based on the optimization, is a grid optimization of modularity. So these three methods are different ways to optimize the same thing, where this one is an entirely different method. We wanted just to see, how effective this procedure is independently of the specific clustering technique you're using. So you see at the beginning, when mu is close to 0, groups are very well separated, easy to find, and basically what you find is similar. It's pretty much the same thing as you just find the right partition. The two different colors here indicate the original results. So basically what you get if you compare the partitions that you find by applying the method on the graph with the natural partition, whereas the red dots indicate the consensus partition that is found through the procedure I just told you. So as you see, the consensus partition is generally better. I mean, you see the signal, somehow the quality of the performance decay later than the performance of the original algorithm applied directly on the data. This is for 1,000 nodes, this is for 5,000 nodes, and you see nothing really changes. Interestingly, for 5,000 especially, you see here that this method, the Crozeta, which is really which has really lousy performance on our benchmarks, you can see by how poor the performance is, it basically goes down right away. These are the black things, the black dots, both for 1,000 and even more for 10,000. You see instead how much better the performance it is once you average the partitions with consensus clustering. So there is a huge gap here. There is even a big gap. So basically here, can you see the difference? That basically in this range of mu, you even find the exactly the right partition, even though the method itself is unable to find a good partition. So this is actually the reason why, even though pretty much nobody uses this method anymore, I mean, it helps me to illustrate the potential of this technique. It can really find the signal even when the partitions are very noisy and very far away, I mean, apparently far away from the ground truth. Okay, so basically this is the same exercise we're gonna do. Oh, sorry. Okay. But there is a problem with the initial technique that we proposed in 2012, which is time complexity. If you think about what I told you about how you construct a consensus matrix, if you have a large cluster in one of the input partitions, any pair of nodes in the cluster will give you a score of 1 because they are co-clustered. But that means you have to compute, basically, to consider all pairs of nodes. So if you have clusters which are very large in that partition, which can be the case often, just to compute and to construct the consensus matrix can take a time which is close to n squared, which obviously kills somehow makes the analysis of large networks really problematic, if not impossible. This is the reason why last year we published another paper where we showed how you can alleviate this problem by simplifying the calculation of the consensus matrix. And the trick is that instead of computing the frequency of co-clustering of any two nodes in the network, regardless of whether they are connected or not, you just focus only on the pairs of nodes which are connected, pairs of neighbors. And since you usually deal with a sparse matrix, there are not many pairs of neighbors with respect to all possible pairs of nodes you can have on the network. So this is what we did, what we proposed last year in that paper that I advertised at the beginning of the presentation. So you start again with a network G with n nodes, m links, and a clustering method A. You derive the input partitions by applying that method n p times. So this is all the same as before. You construct a consensus matrix, but this time, instead of considering all pairs of nodes, you consider only the pairs of nodes which are neighbors in the original graph. So you only sample basically the consensus clustering, the consensus matrix only based on that. So basically that gives you a matrix which has the same number of elements. Well, actually, you cannot have more elements than the original adjacency matrix of your network, because some of these elements may be 0, because some of these neighbors may never be co-classified. You still do thresholding, just like in the case before. You just set to 0 all the elements below a certain threshold. We show that also in this case, even though we have a sparse matrix already, that this procedure helps basically to get rid of the pairs of nodes which are just weakly co-clustered. And then we add an additional step. It seems to be helping if you use specific algorithm to find your a partition, which consists of closing triads. So basically we add m additional entries. M is just a number of edges, so it's not really parameters, because we found that that's enough to improve the results significantly. Once you have the consensus matrix that you get before, which is sparse, you add an additional up to m additional entries by closing triads. So if you have a triad there in the consensus matrix, you just close it by computing the frequency of co-clustering of the two nodes that close the triads. And yeah, and then you do, let me do this. How is I promise to? What happens if I do this? Okay. But then you don't see me. Let me see, show active speaker video, yeah. Item, yeah. Okay, so I can put it any height. Right, I can put it here. Sorry about that. So, so now you have your consensus matrix and you do the same thing as before. You apply your clustering method, the same one that you used at the beginning, again on this new matrix. You get another NP partition and you repeat the cycle. So the procedure is the same. The only thing is we just sample the consensus matrix to make it sparser and therefore to kill the complexity of the procedure, which could become heavy. Sorry, heavy if you do it, if you just do it the old way, basically by sampling the full consensus matrix, by computing the full consensus matrix. So the question is that this is a more noisy procedure than the original one. It doesn't generally converge to a single matrix, to a single set of partitions. So basically to a block diagonal consensus matrix at the end. And you don't even want to wait very long for convergence, because otherwise all the time that you saved by sparsifying the consensus matrix basically is lost by waiting too long to get the result. So what we did is to to introduce a stopping criterion for this procedure. And what we did is this. So our stopping criterion is that the convergence, you reach convergence, so you stop the procedure when you finally get a consensus matrix that has less than 2% of entries which are neither 0 nor 1. Because usually have 1, at the end you expect to have only 1s and 0s, which basically means if you get to a partition consensus matrix which has only entries which are 1s and 0s, it means basically that all partitions are identical. It's the same thing. So two nodes are either always co-cluster or never co-cluster, which is exactly the same thing as saying that the partitions are identical. So you never get to the situation here, but as long as you have a few elements which are different from 1s and 0, you can stop the procedure and see what happens. And instead of, that also means that the partition that you get at the end is not only 1, you can have, again, NP different partitions, but they are very similar to each other, as I'm going to show next, much more similar to each other than the original partitions. So then, I mean, this choice of 2% looks arbitrary. In many ways it is, but we found that it's a good compromise between trying to have sufficiently stable partitions at the end and not waste too much time waiting for convergence. In fact, we found that if you take any value between 2% and 10% of the elements as a stopping criterion, the results are essentially the same. But if you take 10%, it's still, you accept more noise in your results. So we try to reduce the noise at the same time, guarantee convergence. So for instance, if you take 1%, you get pretty much the same result, but it takes longer to converge. So it's a trade-off. But overall, it's not the proper parameter because the results are fairly much the same. Really depends, if you want to invest more in precisions and less, in saving computer time or vice versa. So let me show you why it's important to have triadic closure, which seems annoying. It's a detail that you didn't have in the original procedure, but this is the reason why eventually we did that. This is a Louvain algorithm. So this is the technique that you're using to derive the initial partitions and all the other partitions every time we apply it on the matrix. This is the normalized mutual information. This is again a test on our benchmark, so you know what the clusters are. And this is the number of additional edges that you're introducing in the system to close the triads. So you see that, so these two lines indicate what is the NMI, so basically the similarity between the partition found by the original algorithm on the network, on our benchmark, and the natural partition of the benchmark, whereas the magenta line here indicates the value of the NMI of the similarity if you apply the full consensus procedure I told you before. So here you see that, and the blue line instead is how the performance of the fast procedure I told you varies if you close these triads. So you see, if you close at the beginning, actually it's not great for this specific method. In fact, it's even worse than the original one. But if you add the triads, if you start to close the triads to, the way I told you, you take a point, you check its neighbors, and if the two neighbors have a 0 element of the consensus matrix, you then compute how many times these two nodes have been co-clustered, and you add another entry to your consensus matrix. If you do that, after about m additions, you see that basically the performance stabilizes, so you don't need to add more than m new elements, the consensus matrix, by doing this triadic closure operation, and the final result is better than even the original slow consensus procedure. So this is why we do this triadic closure thing. If you didn't do triadic closure, if you use the Louvain algorithm, which is super fast, it has a lot of issues, but it is very fast. You can actually even underperform the original application of the algorithm on the data. So this tells you basically how stable the partitions are if you, before you apply the procedure and after you apply the procedure. So this brown line indicates the similarity between any two partitions that, in this case, the Louvain algorithm finds for different values of mu in our benchmarks. So you take mu, so you have basically a set of benchmarks, you find a bunch of partitions, usually 20 partitions, you compute the pairwise similarity, you take any pair of partitions, you compute the mutual information, in this case, normalized mutual information between any two of them, and then you average, and that gives you the brown line. And then you do our fast consensus clustering procedure, you get the output partitions of this procedure, and you do exactly the same thing. And you see actually that in this case, even after you get past the threshold of mu, after which clusters are undetectable, because basically they are so mixed with each other that there is no community structure anymore, the output partition of the consensus clustering procedure is pretty much consistent with each other, just because it's designed to give you an homogeneous result. Of course, it's a random result, and which you can verify in other ways, but they are very homogeneous. And these are the results that you get now. So now basically you see 3 lines instead of 2 when you really consider the performance of 3 different methods. This is a Clossin-Newman-Moore method. That method was giving those crappy results that you may remember. This is the fast-Louvain method, and this is a label propagation. So then you can use different clustering algorithms. If you have other ideas, you can change the clustering algorithm, do the exactly same thing, because this procedure that I introduced is really independent of the specific clustering technique that you find. Of course, we couldn't test them all. For this paper, we just tested these 3. In fact, we also tested InfoMap, but the results are not shown. So you see that basically the blue line, which is the one of the consensus clustering procedure, is either the same as the red line. There is an exception in the case of the Clossin-Newman-Moore. Like I say, it's a method nobody really uses anymore. However, remember that now this thing runs much faster, and I'm going to go to that next, than the original consensus technique. But you still see that there is a big gap between the quality of the partition that you find with our consensus clustering procedure and the ones that you can get by applying directly the algorithm without averaging the partition. Especially if you go to larger network size. But this is 1,000 nodes, this is 10,000 nodes. And you see actually in this case, the performance is really poor of the original method. The performance of consensus, of the fast consensus, is similar in this area to the one of full consensus, but it's definitely way better than this very poor performance that you get from the original application. Whereas in the other cases, the performance is still pretty much the same as the one of the much lower initial clustering consensus clustering procedure. Okay, this is just a way that a plot that we added just to show that with this fast consensus procedure now we can really take large networks. This is just for example, but it runs really in a very short time. This is a network with 100,000 nodes and 1 million links, and for this one we can get the performance diagram that you see, and you see actually that with the procedure, with our fast consensus procedure, we can get better than the original one, because the performance dies out later. But with the full consensus procedure, it would be impossible. It will not be possible to get these results in a short time. Excuse me. And this is a diagram that shows, the difference between the complexity of the full procedure, which is this magenta line, and the fast consensus clustering procedure that I just introduced. So the complexity is approximately as a power law dependence on the number of nodes, which is n. It's close to quadratic in the case of the original procedure, and is basically linear in the case of the fast clustering procedure, that consensus clustering procedure that I mentioned. I want to emphasize that this 1.2 instead of 1 is because of the implementation we use for Louvain, which should be linear, which for some reasons is a little bit super linear, because by default, by the way, we implement our fast consensus clustering techniques, the procedure itself is linear. So that most of the time is spent in applying the clustering algorithm on the network, and after that on the consensus matrix to get the result. So you see here how far we can go. We can go up to 1 million nodes, which will be completely unreachable by this one. This is actually the reason why we did that, to get pretty much the same results and better results than the direct application of the methods or the clustering method of your choice on the data at a much lower price, computational price. Okay, so I don't know how much time I have. Alessia, could you tell me?
Well, actually, a few minutes, perhaps, if we want to leave.
Sure. A couple of minutes. Okay, then
about 5 minutes, right?
Yeah. Okay, so let me skip this part, which was about showing that you can apply consensus clustering not necessarily on a static graph. You can use it also for dynamic graph, basically to put together partitions that you find at different time snapshots of your system. And I gave a couple of examples. So let me go directly to the conclusion, because I would like to advertise a couple of things. So the basic message is that there is noise when you apply any clustering, most clustering methods, most clustering techniques on any network. So how to deal with noise? The easiest thing it would be just to pick the partition which appears to be best according to the optimization procedure, optimization criterion that you're following, because most clustering techniques are based on the optimization of some function. But I showed you that you can do better by using also the suboptimal partition, by combining them in a consensus matrix and clustering the consensus matrix instead. And what I showed you today is that the original technique could have bad complexity, that could approach quadratic if you're unlucky and you have some big clusters in your partition, big somehow of a size comparable to the size of the whole system. But it is possible to do much better by creating a consensus matrix which is sampled, just considering the scores on pairs of neighbors instead of any two nodes. This brings down the complexity to linear for the fast consensus procedure. And basically, in that case, the actual complexity of the full routine is the complexity of the clustering technique that you're using. So nowadays, there are techniques which are basically linear, and that allows you to analyze networks with millions, tens of millions of nodes. If you use one of those techniques, also this fast consensus clustering procedure is going to be linear. So because it's, the way you construct the consensus matrix is linear, everything else is linear. So this is a way to save time and to be able to apply this technique on very large networks. Okay, sorry. The code is actually in this GitHub. We are just actually turning it from network X to iGraph because it's much faster that way. So if you use the one which is already there, it's not going to be so impressive. I mean, we're going to put soon in GitHub a faster version of that. I mean, it's the same algorithm, just implemented in iGraph using iGraph libraries. Just let me make sure that you get the take-home message, because you're going to forget the details. So you don't have to expect miracles from this technique. It's not like a God-given thing, because it also depends on the quality of the input partitions, because what it does is some sort of average of those partitions. So there are three different scenarios that you may face in this situation. If the input partitions are very similar to each other, the technique also returns very similar partitions. It's like when you average numbers which are very close to each other, right? Then you can almost take any one of them. So you don't gain much by doing that. If the partitions are very different, then you can expect something intermediate which has no meaning. And there are actually now recent work, discussions about, you can get different partitions just because there are different solutions. Like for instance, you may have a hierarchical structure, then you have partitions with big blocks, partitions with small blocks, and both of them, and all of them are significant. But it may also mean that basically there is no community structure, just because you get different things. It's like getting a random partition every time. The best domain, best regime where consensus clustering is most likely to give you a result is the one in which you have some variability in the input partition, but not too much. And what that means, it's just, can be quantified, but I just leave it like this for you to remember. So just let me quickly remind you that for those of you who are not familiar with graph clustering, I recommend you to read my original survey, which is like 100 pages, a big one. I'm actually writing a book now. I've been working on it for years. Hopefully next year I will finish, which is even much bigger than that, because of course, after 10 years, there are many things here which are obsolete, but there are also many popular algorithms that people are using today, which are described in the original review. I did a more recent review more lately. This is actually one of the best known, most cited papers in network science. More recently, I published another review with my former student, colleagues, which is supposed to be more on the principles and less on the description of the algorithm and where we are, after some years, where we are going. more like, in this direction. So in this respect, is complementary to the other one, and more, of course, up to date. And the last couple of things I want to say, we published a book that came out at the beginning of this year, a first course in network science, a textbook in this discipline, which is supposed to be the most accessible textbook in network science. It's really undergraduate level. It's for our undergraduate students. It's an hands-on approach. We have a lot of exercises, also a lot of code exercises in Python. So we also teach how to program in Python if you do that. The approach is software-based, and it's based on NetworkX, using a NetworkX libraries because NetworkX library, because it has a lot of built-in functions which just compute directly a lot of things which have to do with networks. But in general, you can also then move to different platforms after that. At least, I also learned Python this way. I was a very old-fashioned Fortran programmer before then. We also make available the solutions to all exercises, including the one in code. So we also give you the notebook, so you don't even have to solve these things on your own. If you want to give this exercise to your students, if you are an instructor and you buy the book, you can have access to the solutions and to a complete set of slides, both in PowerPoint and in Keynote, which basically have all the contents of the course, all the figures of the course from the beginning to the end. So this is really meant to be for people who do not have, students who do not have a strong technical background. There is very, very little math. Few formulas included in gray boxes that you can skip without sacrificing the understanding, and I hope you're gonna like that. And there are also free tutorials that you can perhaps also go through at any time. You find them on GitHub, one for each chapter. This is, for instance, the one of chapter 7, which is the last chapter of the book, and the one about dynamics on networks. And this is, for instance, a part about the SIS model, since we're talking about epidemic spreading a lot in this year. So you can also see how we can implement it. And last couple of advertisement, we are organizing Networks 2021, which is possibly the largest ever meeting in network, because it's a merger of Sunbelt, the Sunbelt Conference and NetSci Conference. Supposed to be next July in Washington. We're working on a hybrid model because we don't know if we are still out of the woods next summer, if people can travel, So we are preparing something which is partly online and partly in person. We may have to switch it to online only at some point if we see that we're still in the best situation. But I encourage everybody to participate because this is going to be really, it's a unique event. So it's probably going to have the largest number ever attendees of any network meeting so far. And finally, I want to focus your attention on this program supported by the NSF, National Science Foundation here in the States, which is the first international mobility program between the US and Europe about the topic of multi-layer network science. So in fact, the bulk of the program is, and most of the money, that almost $2 million basically for this program, consists in supporting sponsoring visits of researchers, young researchers, postdocs, young faculty, PhD student from the US to Europe to work with somebody on multi-layer network science. For obvious reasons, because of COVID, we cannot have mobility right now. We have to start the program, but we're organizing event. We have a webinar series. This is actually a snapshot of the website. These are the main people involved. I'm a PI of this program together with Alessandro Vespignani, and people at the bottom are the 4 representatives of 4 European institutions, but they are not the only ones. This is an inclusive program. We have a big mailing list. If you're interested in this topic, if you work on multi-level network science, you can join. You can get our updates, be involved in many different ways. And with that, I'm ready to take your questions if you have any. Thank you.
And thank you, Santa. Yes, and the floor is open for questions and comments.
Okay, may I ask a question?
Yeah, sure.
Okay.
Thank you very much for your talk. I have basically 2 questions. So first of all, you talked about improvement and approximation of your own methods for consensus-based clustering, but my question may be relevant to modern advances in network science related to graph embeddings and the existence of models that now take into account cluster structure and could build graph embedding together with community structure, leading to very simple application in which clustering is made based on k-means or dbScan in embedding space. Could you shed the light what's the future of such methods, and can the current community detection methods can be incorporated in graph embedding based models? And
this is,
second,
yeah. Oh, sorry. Okay, so I'll let you ask you the second question.
Okay,
anyway,
and the second question is regarding the last slides about mobility and so on. So basically, people in Russia are very interested in the question whether there will be open remote opportunities to collaborate. Because as you know, it's like many people are not ready to go on kind of PhD postdoc positions if they already has some kind of job right now. But people are waiting for open and remote positions for collaboration, because I consider for the past half a year, everybody know how to use Zoom, Overleaf, and so on to work together. And that's my second question. So your opinion and the current situation, what's going on? Thank you very much.
Thanks a lot. I mean, these are really great questions. I mean, I don't know how much time we have, but this really could be a long discussion. So, but to your first, the technical one about the talk, this is a great question. It's the same question that I asked myself last year. We just published a paper, actually published, we put it online. So I can send you the reference to that if you give me your email, or perhaps I can also put it in the Zoom chat for everyone to share. Just about that. I mean, do we gain anything if you use, I don't know, not2vec, deep walk, or these very recent graph embedding techniques, and then turn the problem from a graph clustering problem into a data clustering problem using, like you said, DB-scan, k-means, and so on? So the answer is no. I mean, meaning that these methods seem to underperform some of those that I mentioned before, which are even non-parametric, whereas, as you know, not2vec has 7 parameters, deep walk has 5 parameters, so there are things. So just because, but we published the work because I was personally curious. I would say, oh, maybe now finally we can, we can simplify things, which does not mean that the idea is wrong. It means that I ended the conclusion part of that paper by encouraging people like you who are familiar with these things, the deep learning techniques and so on, to create new embeddings which are focused on modular structure. So, I mean, of course, random walk is also one way. I mean, the info map that I mentioned before is based on random walk and is very effective, at least on our benchmark. And we use our benchmark, which of course does not mean that this is the universe, But I mean, the performance can get to levels which are comparable, but it really strongly depends on the choice of the parameters. And we couldn't find a single set of parameters. Actually, I would have loved to say, look, I mean, if you want to apply not2vec instead, and then of course use k-means afterwards, then you can use this set of parameters instead of the ones that are recommended by the developer for, I don't know, no classifications or link prediction. And we couldn't do that because depending on the value of mu, this level of embed of mixture between the classes, we will find that the optimal set of parameters was really changing considerably. And on top of that, and that's a more general question, it could be actually undermining this whole thing. Consider that k-means is a quadratic complexity most of the time. So even if you can get a very good separation of the data points, you may also lose your edge. And of course, not2vec can do it very fast, and all these techniques are super fast in doing the embedding. But the embedding is not the end of it. After the embedding, you have to separate the points. And right now, the best techniques to separate points in space are, I mean, I don't know, you just go to classic ones, they are super linear. And the current world we live in, if you want to analyze networks with millions and millions of nodes and want to separate them in a reasonably short time before you finish your PhD specifically, you should really go to linear complexity. So if you do science which is super fast to do embedding, a science which is super slow to do the separation, it's not a good trade-off. So this is where we are now. And I'm more than happy to share with you the link to the archive paper, which is still under review for PRE, that basically, summarizes the results of this analysis. The second question, of course, is more political, somehow about the situation. It's true, we're learning to live in this virtual world. Actually, I'm just sitting on my dining table. You see also this is actually one of the pictures of our book. So, and we're getting used to that in a sense. It incentivizes collaboration. We're getting used to that. Specifically, our program, you can subscribe to the program. You can add, add your name to the mailing list. It's open to everybody if you're interested. It's more, I mean, we couldn't do something for the whole on network science because instead of 2 million, we would have needed like $20 million for that. Because it's so big. So we had to focus a little bit, and we decided to focus on multi-layer network science because in the last few years, this is a big paradigm. A lot of people are working on that from different disciplines. So we focus on this one. So if you have any interest in that, or if you plan at some point, not necessarily your main interest, if this is one of the things that you like to do or to explore at some point, just subscribe to our mailing list and you get updates. We have an initial set of partners that are supposed to exchange research personnel, and most of the money of the grant goes in supporting the travel and to give them a stipend to pay their bills. When you move to the state for a few months, it's usually a semester. The idea was a semester long exchange, so that you can create this dense network of collaboration. But in principle, everybody's invited, and you also live in Europe. So and then specifically, if you mention, I don't know, the potential of collaborating with me or with some of the great people we have here, we can also have separate conversation on that. You can tell me what you do and so on. Are you a PhD student?
I'm currently a very late PhD student at University of Ljubljana on graph embeddings and the application of learning on graphs. But basically, I'm mostly a researcher at High School of Economics here and several other research institutes. So just an interesting question, because again, we are sitting at home and what can be done. It's like we're researchers and we're researching.
Especially we should really search for each other.
Table, with small blocks visualization behind you. So it's quite interesting to see the experience. Thank you very much for answering the question.
Thanks to you.
Okay, colleagues, although officially we're supposed to finish, but because we started later, I think we have a full right for a few more questions.
Santa, I have one question. May I ask you?
Oh, sure. Nice to see you, Sergey.
Nice to see you. Thank you. First of all, thank you for your presentation. My question is following. Do you think about the application of deformant entropy of just the information measure to get the correct number of parameters mu? For example, you transform your frequency into probability, and then you can calculate, just go through the matrix, you can calculate the information weight of current solution. And if you change the mu as a parameter, as a deformation parameter of such entropy, then you can get the good results just to choose these parameters. For example, we had the same situation in topic modeling. We had the problem with the numbers of the topics, which is influenced as a parameter for deformations. Do you think in the direction of the deformant entropy?
You know what? This is a great idea. So you expect to get an email from me one of these days. Somehow we talk this through. I'm thinking this is really very promising. I mean, just in general, the idea that, of course, I mean, obviously, this probability depends on the method that you're applying. But if you have a sufficiently high number of partitions, then you can really interpret it as a probability that two nodes end up in the same cluster, which is essentially the whole principle of this approach. And right. So basically, you can compute the entropy of that ensemble of partition, and it's a function of mu. You can also see if there is, because it's a smoother function instead of applying again a cluster, a technique and so on. This is a great idea. I'll look into that. So, and of course, in this case, since it comes from you, if you're gonna do anything about that, you're gonna be involved. Thank you.
Okay, I can write in email to you just to explain my idea.
Please do that. And if you have a reference to what is it, like LDA? I don't know if we're referring to that when you mentioned topic modeling.
Yeah, it's already published in several conferences, so I just give the reference.
Yeah, please. Thanks. I mean, I'm really interested in that. I mean, potentially. I mean, right now it looks like a great idea, but of course I need some time to process it.
Yeah, okay. Thank you.
Thank you. I think we can take one more question. Okay. If there are no more questions, I think we should thank Santa Fortunato for this most interesting talk this Friday evening, and thank you everybody for staying.
Yeah, thanks a lot. Thanks. Okay, I don't know how it works in online things. Thanks a lot, guys. See you soon.
See you.
Yeah.
Thank you.
Thank you very much, Santa, for accepting the invitation.
Sure.
I like these topics very much, both the clustering of graphs, social networks, and consensus clustering.
Yeah. Thanks for reaching out, the way you did. So I almost forgot about this because it was like in the spring, when we were in isolation.
Yeah.
Contact. So, but I was happy that I could do it this time.
Yeah, but we suddenly popped up.
Yeah, right. We suddenly popped up.
Thank you.
Thanks a lot, guys. Hold on, and we get out of this one day. See you.
Yeah, hopefully.
Bye. Let me stop sharing, actually. Bye.
Dear colleagues, now it seems that it's time for our virtual poster session. If the presenters are here, we can start with the first poster presentation, machine learning methods for demographic data analysis. Since we asked about pre-recording of videos, so if the author thinks that the video is well recorded, we can use the videos and then ask questions after that.
Okay, so I'm now sharing the screen and starting the video. You cannot hear it, right?
Probably not. It's not streamlined.
Me neither. And events that already happened. Can you hear it now?
Yeah, but there is an echo.
Anybody here?
If Anna is here, is it possible to present it personally?
Good day. My name is Anna Muratova, and the theme of our work is machine learning methods for demographic data analysis. I will present the results of the analysis of demographic sequences obtained using various methods, such as decision trees, variants of custom kernel in the same methods, and neural networks, recurrent neural network, and convolutional neural network. The comparison of the accuracy of these methods will be presented. The study of demographic sequences using data mining methods allows to extract more information, identify and interpret interesting dependencies in the data. Demographers investigate the relationship between events and identify frequently accurate sequences of events in the life trajectory of people. This helps to understand how the demographic behavior of different generations in different countries has changed, and also it allows you to track changes in how people prioritize family and work, and also to compare the stages of growing up of men and women. One of the common demographer's tasks is to predict next event in person's life, taking into account all of the features and events that have already happened. Another task is to determine the dependence of events or the gender attribute. Data for the work is obtained from the Scientific Laboratory of Social Demographic Policy at High School of Economics, and it contains results of about 6,000 people, including 3,000 men and women. There are features of people, gender, generation, type of education, location, religion, and frequency of church attendance. Also, in the database, for each person, the dates of birth and the dates of significant events in their lives are indicated, such as partner, marriage, breakup, divorce, education, work, separation from parents, and birth of a child. The first method that I used is decision trees with events encoding. To compare the accuracy of different decision trees, 3 types of event encoding were used: binary, time, and pairwise. And also different types of these encodings together. First encoding is binary. This value 1 if event has happened in person's life, and 0 if event hasn't happened yet. Time encoding with age in months of when the event happened, and pairwise encoding with pairs of events to mark type of mutual dependency. Simple as use that first event happened before second, or second event hasn't happened yet. Go more means otherwise. Equal if two events happened at the same time, and n if both events haven't happened yet. In this table, represented comparison of classification accuracy of different encoding schemes for gender prediction. It can be seen that time-based encoding is better than binary and pairwise. Also, adding this encoding to time-based encoding slightly lower the accuracy. The best accuracy is obtained for all of the three encodings together with accuracy of 0.69. Let's consider this decision tree. Here is the part of big decision tree with the highest probability. It can be seen that if the marriage was before 20 years or 247 months, then with the probability of 77%, it is woman. This table represented some other patterns from this decision tree. For example, if first job was after 21 and marriage after 29 years old, then with probability of 70%, these events more likely would happen for men. And if the job was from 18 to 20, marriage from 20 to 22, breakup after 27, and divorce after 30, then these events are more likely for women. In this table, represented comparison of classification accuracy of different encoding schemes for the next one prediction. It can be seen that the best classification accuracy of 0.88 is obtained with binary encoding scheme. Also, added a pairwise encoding to time-based encoding, as well as added binary encoding to pairwise encoding, slightly improve their own accuracy results. Time-based encoding scheme here is the worst in accuracy. Let's look at the decision tree for binary encoding since it gives the best accuracy. In this decision tree, the best predicted next events are colored in red and orange, and they have the high probability. For example, following the best in the tree, if event education didn't happen yet and event work already happened, then with probability of 98%, the next event will be education. If the event education already happened, but event child didn't happen yet, then with probability of 79%, the next event will be marriage. If event education and work didn't happen yet, and education type is general, then with probability of 74%, the next event will be education. In this table, represented some other patterns from this decision tree. For example, if event education, separation from parents, and childbirth already happened, then the probability of 98%, the next event will be job. The next method is SVM with special kernel function. Since demographers are interested in sequences of events without continuity, the following similarity measures without discontinuities will derive common prefixes or common subsequences and longest common subsequence. Common prefixes similarity measure is equal to the length of the longest common sequence prefix divided by the length of the longest sequence. Longest common subsequence similarity measure is equal to the length of the longest common subsequence divided by the length of the longest sequence. And our common subsequences similarity measure is equal to the sum of the numbers of common subsequences of S and T without discontinuities of length curve for all of the common subsequences. Then the sum is multiplied by 2 and divided by L multiplied by alpha fund, where L is the maximum length of the sequences. Let's consider special covariance in the SLAM method. We will combine two methods of classification by sequences using special kernel functions based on sequence similarity measures without continuity, common prefix, or common subsequences, and longest common subsequences. And by features using the SLAM method with default parameters. This can be done using the probabilities of referring to a session class calculated by the SLAM method. Having obtained the probability table for each method, we can classify based on the weighted sum of the probabilities of the two methods. Since the methods give different classification accuracies, the final probability of assigning an object to a class is calculated by the following formula. Results of classification by sequences, by features, and by weighted sum of probabilities of sequences and features for gender and experiment prediction are presented in the table. From the table, we can see that the highest accuracy for the gender prediction is 0.67, which is obtained with custom kernel function called prefix using weighted sum of probability. Weighted sum of probabilities for the case of maximum prediction gives lower results due to the small accuracy of classification by features. The best result for this case is obtained with custom kernel function or common sequences for sequences only with accuracy of 0.91. Another possible method of classification by sequences is by transforming each sequence to the feature. After that, existing methods of classification by features could be used. There are about 6,000 sequences in a data set, where 1,228 sequences are unique. Let's consider the sequences as a feature, taking 1,228 different values. So each sequence will be assigned a specific number. Since the table presented classification by features and sequences, transform into features for gender and experiment prediction. For both cases, we obtained approximately the same accuracy of 0.71 for the partners with strong men and women, and accuracy of 0.77 for the experiment prediction. Now let's look at the neural network model. Classification was performed using the neural network from Keras and TensorFlow software. Keras is used to describe the structure of a neural network as an add-on over the TensorFlow software, which performs the simulation of the neural network. The simulation was performed on the GPU. Recurrent neural network allows us to review regularities in sequences. Three types of recurrent pairs were compared in Keras: simple RNN, GRU, and LSTM. GRU and LSTM, in comparison with simple RNN, have more complex algorithms for detecting regularities. However, on sequences in demographic data, because of their small length, LSTM and GRU didn't show any advantage in classification over simple RNN. At the same time, the simulation time for GRU and LSTM was several times longer. Therefore, for classification by sequences together with features for gender and excellent prediction, only simple RNN algorithm was used. The result is shown in the table. Accuracy of 0.75 was obtained for the gender prediction, and accuracy of 0.93 for the excellent prediction. These accuracy results are higher than the previous methods, decision tree and SAM. Also, we use convolutional layers for sequences. Several years ago, recurrent neural networks were profitable for sequences. But in the last years, convolutional networks become much more used for sequences. The most important reason for that is parallelism for convolutional model training. Recurrent networks are sequential by nature, and usually they need much more time for training. Convolutional networks got better results than recurrent neural networks and in less time. In this table, we can see that for gender prediction, the convolutional network model got test accuracy of 0.78, and for the next event prediction, it got test accuracy of 0.96. This table shows a comparison of the accuracy of all classification methods we used before: decision trees, as well as custom kernels and neural networks. From the table, it can be seen that the highest classification accuracy in both cases, gender prediction and next event prediction, is obtained with convolutional neural networks, which means that it is an optimal method for this task. Also, accuracy for prediction of next event in person's life is higher in all of the methods than the accuracy of gender prediction. That's it. Thank you.
We can thank the speaker, and if Anna is here, it's time.
Is Anna here?
Yeah, it's time for questions.
Hello, everybody. I'm here and I can ask questions, but there's noise from neighbors.
Excuse me, I can't hear you well.
There's a noise from neighbors. I'm so sorry.
There are any questions? If we have no more questions, we can go to the next speaker, poster presenter. If the poster presenter is here, it would be good to have a talk.
Yes, I'm here.
Yeah.
Is it okay to use no camera?
Yeah.
Okay. One moment. Okay, can you see the display?
Yes, I can clearly see it. Hope the other listeners.
Okay, then let's go. Good evening, ladies and gentlemen. I'm glad to present my research about in which I try to identify some characteristics of the wood trade network and to see several measurements in a temporal manner. So actually, there are not so many articles which try to breach economic methodology and graph analysis approach. So all literature can be divided into three parts. So the first part is about overall characteristics of a network. Usually such articles are printed in journals of physics. The next is about network effects in economy. Usually it is about spillovers, externalities in economy, and so on. And the third one is more about modeling of network evolution, but usually it is based upon game theory because you have like several actors and you need to model their interactions. Thus, in this research, I try to combine or try to apply graph methodology to some economic data with some prior economic analysis. And my two main hypotheses are that the first, as time went on, trade developed and became more sophisticated. And the second is that the higher goods complexity, the more stable the trade is. So what about the data? The data was taken from the project of the Observatory of Economic Complexity by Cesar Hidalgo. It is a project carried out by MIT. And they have data about international trade for some period of time. So I have chosen the period from 2003 to 2017. And I have taken codes from custom nomenclature devoted to the wood and divided it into three groups. So the primary products for raw wood, second group for processed wood or for intermediary products, and the third group for wooden goods or like ready products, for example, furniture. And I have measured several indicators. So the first one is the average price. We assume that the higher the number of hops need to be made, the less trade partners have an average country. Then the density. The higher density, the more complex is a network. Third, the number of strongly connected components. So the higher the number of such components, the more fragmented network is. The fourth, reciprocity. So the higher the reciprocity, the fairer and more competitive are economic relationships. And finally, I've looked at the number of communities detected by label propagation algorithm. So on this data, I have built a directed graph. Some kind for 1 year it is presented on the slide, so you can see that the node is the country, the edge is the amount of export, and arrows it shows the direction. So we can see that the main like inputters are China, Germany, India, and they're in the middle, and then there is a huge periphery consisted of African and Latin American countries. And the main problem with this graph is that the edges are highly unbalanced. So for example, the
amount of trade of China is uncomparable with any African country. So let's jump into indicators. So on the slide, you can see the dynamics for the average shortest path for each group. So all in all, overall, you can see that the trends is decreasing, either because new players enter the market or current expertise expand their network of partners. However, for finished products, the endpoint is on the same level as the beginning. We can also note that all graphs experienced drops in 2013, maybe due to the financial crisis. So we can assume that exporters try to get rid of intermediaries in supply chain. And also, the more technologically complex product is, the less distance is between two nodes. So it means like fewer intermediaries in a network or in supply chain. The next is density. For all lines, all trends are increasing, which means that the networks like develop and they have more partners. But also you can see peaks in 2008 and 2014 years of crises. So we can assume that during the crisis, experts try to scale up the portfolio of partners to be less vulnerable. We can also mention that density for finished products is twice bigger than for raw wood. So for average exporter of finished products, it has twice more partners than exporter of raw wood. So he has a better choice with whom to deal with. The most unclearly interpretable results have been received for the number of strong components. The curves are fluctuating, but for example, for finished products, we can state the decreasing trend. While for the processed wood group, it remained approximately on the same level. Raw wood expertise have more strong components, so we can say that their network is more fragmented. And actually it is quite expectable because the raw material is usually exported to the nearest countries, and if you can export it to the like faraway countries, the cost can be very considerable. About reciprocity. So it is the most mildly changed graphs. You can state only some increase in trend for the raw wood. And at the same time, reciprocity for the raw wood is the lowest. And we can suggest that in this market, economic relationships are more likely to be one-sided. So we can't say that the trade is like bilateral. And finally, the number of communities in the networks, it is the most fluctuating graph. You can see that for the raw wood, the figures are bigger than for another two groups, and it is in line with the number of strong components. And we can like prove that the network of the raw wood is much more fragmented than for finished products. And at the same time, for the finished products, we can assume that the graph have a cyclical nature because we have peaks in 2003 and 2012 and slopes in the middle like 2008. So maybe the trade with finished products is closely connected to economic cycles and swings of importers' purchasing power. So to wrap it up, what we have got is, as time goes by, the network becomes more complex, developed, and dense due to the measurement of density. That the higher technological complexity, the wider the portfolio of partners, and the less trade is affected by crisis due to like reciprocity measures and number of components. And the network of technological advanced goods is less fragmented due to the dynamics of communities we have identified. So we can state that the two hypotheses stated identified in the beginning has been proven. And also I have the final slide about like further research, and if we don't have much questions, we can discuss these topics, because this is how I'd like to develop this research. The first direction is about robustness check. It is in economic interpretation, it is more about sanctions. So if we can, which node we can block to have the lowest effect on the whole network, or the highest effect on the network. The second, it is link prediction, but in economic networks, especially international trade, the decisions are closely linked to political decisions, and political decisions are very difficult to prognose. That is why I quite doubt whether these predictions can be robust. And the final is about community detection with additional features. In this, I meant like to get some graph embeddings and to add some more features about like attributes of the countries, and try to cast it by, for example, k-means. But at the same time, I don't have like very, all in all, it is like about 200 nodes, and it is, I doubt whether it will be enough for getting embeddings and to getting like robust results. So thank you for your attention. I'm very glad to answer to your questions if you have ones, and if you have any like propositions, you can text me in my Telegram. Thank you, Andrei, for an interesting poster presentation. So I can see that you addressed the reviewers' comments to quite extent, and you have interesting directions further research. Okay, maybe there are questions from other participants. Okay, just a comment. Okay.
Maybe just a question. So you have said thank you for the presentation. So you have done that for the wood, and do you think that for other products this will be a similar? You have a similar result? I don't know, for rice or other product. I don't know.
Yeah, thank you for that question. Of course, the results will differ, be different in the different like products. And as far as I remember, there was a group project on Stanford course like CS190W, as far as I remember, and they have modeled the trade for rice, corn, and something like that. It is not very similar to my research, but they have done, I think, they have modeled what it will be in if there will be lack of water, and there will be not enough like corn for one country, where this country will be able to trade. And as far as I remember, the characteristics of the network differs from this wood. And also you can see that even the subgroups of the wood, like primary, intermediary, and final products, they also have like different characteristics. So this is what you should take into account if you try to model it, and especially if you try to interpret the results.
And if you look at the other, I don't know, other product like diamonds or I don't know, aluminiums, maybe this could have similar configurations.
Maybe for diamonds, yes, except for the number of exporters, because obviously there are less less country who produce diamonds, and not so many countries that export final products, as far as I can judge. But it is very difficult to prognose each indicator for any product, so one just need to take data and analyze. But maybe for the export of the resources, it should have some common patterns.
Okay, thank you.
Thank you. And do we have the next speaker?
The video again, and I'm going to share the screen.
Okay, we have a video since we asked for a video. Unfortunately, we can't hear it, I believe.
Okay, and let's do something. And now, still no?
No, I think. Is it possible to send the link?
Yeah, let's send the link.
It's about 5 minutes only, so let's go back in 5.
I've just sent the link to the chat.
Yeah, but maybe the better idea is to ask whether we have someone for the 4th poster, the information analytical bots detection system based on the assembly of classifiers.
Hello, everybody. My name is Artem Menesov. I'm here. I'm present. May I share?
Yeah, certainly. You're welcome.
Okay, let's start. My name is Artem Menesov. I am lecturer of Military Space Academia, named by Alexander Fedorovich Можайский, and the theme of my report is the informational analytical bots detection system based on the assembly of classifiers. Currently, the using of bots after accounts in social networks, which are managed with special programs, but masked as ordinary users, has seriously results. For example, bots were used to influence political elections, distort information on the internet, and manipulate prices on the stock exchange. Many research teams concerned with the detection of such account included machine learning methods. The plan of my reporting, I'm sorry, consists of 4 steps. The aim of our research and develop is reducing the risk of spreading disinformation and other negative information among the social networks with bots. The system architecture, our application are developed as a client-server app. The main functions of our app are to provide a decentralized management system, provide access to resources from all devices, to evaluate the informational situation, to identify bots among following of social networks,
to interactively display on maps and graphs and other dashboards the result, generate reporting and informational documents, and to provide API to third-party services. Currently, our system was developed with Django framework, allow to collect and process data from Twitter users, accounts, and groups. Also, we integrate warehousing with special database extender for PostgreSQL object relation database. An element of the scientific novelty of the developed model to detection bots in social networks is a combination of a number of future Twitter account feature and additional account feature, such as the thematic relationship of accounts, activity, anonymity, and data inconsistency. Our approach is taking into account the growing trends of using one set of bots to achieve different informational goals. The developed model is focused on the use of ensemble of classifiers. Ensemble are well known for the effect of improving the accuracy and our approach consists in performing the following action. Step 1, develop of some separate models. Step 2, train each model separately. Step 3, combine models and improving the values in the final classifier. And stage 4, determining the state of social network accounts. The class value, bot or valid users of social network is chosen by opposing the models to each other, taking into account the weights. Note that the possibility of such a choice different between the method for combining solution based on multi-type generation from other approaches. For example, from methods in which the final solutions is always chosen from the set of solutions proposed by the basic classifiers. Our approach assemble of models can be more easily trained on small data sets and will improve the bot detection performance compared to any single models. So in this slide present results of our model in comparing with other methods. The comparison should be carried out under equal condition using the same methodology. We collected the trained and validate data set from user of Twitter social network from African politics account. The use of social networks bot attract public attention in South Africa when Bill Pottinger used social media to spread negative content. Open API allow to connect additional specialized models, such as the electronic services allow different players and partners to join and stimulate the development of our project. Distribute access to the app is provided to all consumers. Fully automated assessment of the informational situation strong focuses on personal data privacy and providing accurate information. So thank you very much for listening. My email in slide. I'm finished, ready answer for questions.
Thank you very much for presenting of the results. Do we have any question here, especially from NLP community members?
I have one question.
Yes, please.
Artyom, thank you for the report. Have you seen yesterday all the similar presentation about bot detection, but the author also used embeddings from networks? Have you tried some of these approaches, or maybe have you studied them?
I'm sorry. Thank you for your questions. My answer is focuses for scientific novelty of our approach. We combination a number of future of our future of Twitter account future and addition futures consist of thematic relationship, activity, anonymity, and data inconsistency.
Oh, I can see the author of the yesterday's report in the participants, so maybe he can add something.
Artyom, hello. And yeah, yesterday at the very end of the social network section, we had a report about bot detection using social network embeddings. And maybe it will be interesting for you to combine different approaches, our results and yours, and see what will happen. So I think we should just change contexts and have a discussion outside the conference.
Yes, my email in last slide. I saw your reporting. Maybe our relationship after conference. Yes, of course. Thanks.
Thank you.
Thank you. I think we have only one poster left, which we skipped previously. You can just follow the link in your Zoom chat and you will see 5 minutes long talk. If Nikolai is here, he can chance to answer the questions. If not, or else simply can watch the video for the closing part of AIST for this year. Thank you. The poster session is now closed since the last poster video is ended. You could have a chance to see it on your own.
Could you see the slides now? Somebody can see the slides?
Yes.
Yes.
Yeah, you can see it?
Yeah. Everything's
Okay, great. Okay, so thank you for those who survived the day-to-day. And this is the last session of AIST conference. And I just will have a brief presentation about base papers selected in each of the tracks and a few more practical things. But before I do this, I just would like to thank again all people who made this conference happen and who made the technical and scientific part of the conference. On the side of Skoltech, we had an amazing team which was led by Irina Nikishina, and she made possible all of these YouTube and Zoom translations, but we also got help from some other colleagues who have to find money to make the conference happen, to make conference free, so you don't need to pay even to register and things like that. So this is very important. Also, I would like to thank all the program committee and especially Dmitry Ignatov and Andrei Kutuzov, Andrei Savchenko, who were always basically ready and up to answer questions and issues, which were many, obviously, as we never organized the conference in this way. So without all of these people, this just wouldn't happen. Finally, I just would like to say that I'm happy to see the number of quality papers in various sections. So NLP section is constantly very large, attracts many interesting papers. So, but other sections as well, they attracted quite a few interesting works, and those which we found, namely area chairs found most interesting in their respective sections, I will just list. So in the natural language processing, the base paper works come to Yulia, Anastasia, and Olga. On the work on two topics, make a metaphor, topic modeling for metaphor identification and analysis in Russian. And this is an interesting combination of linguistic research questions about some fundamental linguistic concept of metaphor based on some advanced technical models of NLP, namely topic modeling here. So I congratulate the authors and go to the next section, which is computer vision. And here the award goes to Ivan Dworkin and Elena Vicheva on the work entitled Deep Learning on Point Clouds for False Positive Reduction at Nodule Detection in Jet CT Scans. And so the authors propose novel representation of scan data and point-based architecture for reduction of false positives in medical classification. So basically, this is a real-world application of computer vision to just computer tomography scans, and that paper got very strong feedback of reviewers, and the authors chairs of the section select this paper with this honorable mention. In the social network analysis, the best paper goes to Ilya Karpov and Ekaterina Glaskova on bot detection using attribute graph embeddings and bipartite networks. So the authors introduce a unique open data set of bot accounts from a Russian social network that have been selected according to a rigorous definition. They also show that bots differ in their level of complexity and what different machine learning approaches are needed to detect these different types. The proposed algorithm demonstrates very high quality. This is a summary provided by chairs and essentially, yes, in this approach, the authors tackle a very important problem of detection bots using modern machine learning approaches, such as embeddings of symbolic structures using graph embedding methods. The best paper award on data analysis machine learning goes to Ivan, Alexei, Nikita, Andrei, and Evgeny. This is a group of authors from Skoltech, and they work entitled Gradient-based adversarial attacks on categorical sequence models via traversing an embedded world. The authors show the importance of threatens bio trust and deploying models for validation of categorical sequences, which might lead to money transaction, medical fraud, and the spread of fictional attacks. So basically, this work is proposing methods which can perform adversarial attacks, and they study attacks on sequence classifiers. And sequence classifiers are omnipresent in natural language processing, but also in financial data and basically many other applications. And basically, authors showed very strong results with respect to common baselines and improved performance with respect to state of the art in this task. In the theoretical machine learning, the best paper goes to Konstantin Kalipkin for fast approximation algorithms for stepping special families of line segments with equal disks. And in this paper, novel polynomial time constant factor approximation algorithms for several geometric settings of the well-known heating set combinatorial optimization problem are proposed. So this is a theoretical work, and I would like to point that we are very happy that we are having both experimental branch of data mining, but also some small section on theoretical approaches. And finally, in the process mining, the base paper goes to Julia, Khalil, and Irina for the work entitled Checking Conformance between battery nets and event logs. And basically, this paper describes a new algorithm for analysis of battery nets and event logs. All right, so this is about the base paper reports. I would applause now, but it would make sense in the Zoom time. However, I virtually applause and congratulate all the speakers. And then I would like to attract your attention to the fact that we have also a new YouTube channel where all the streams of all tracks will be available just right after the end of the session. But we will also upload selected videos there, and you will be able to enjoy and some of the talks maybe which you missed or which you would like to listen again. And I would like also to ask you to provide some feedback to us about the conference. What did you like? What you would like to improve? It's very important for us because this year the conference went online, but also you can, of course, comment on usual parts such as reviewing and the way we handle deadlines or something like this. Anything you find relevant, please drop us a line and submit it to this forum. So I think this is the end. I thank everybody who participated, who submitted the paper to the conference. And I personally think that it was a really interesting event, very dense event. And yeah, I hope you liked it. So, thank you. Oh.
Okay, thank you everyone. I think it was a nice experience, although a bit probably not as pleasant as it could be if it were live, but much more pleasant than could be expected given the circumstances. So thank you everyone.
Yes, yes. This year was all not very expected. It was not. It was full of things which we didn't expect really. So yeah, but yeah, thanks, and I'm really glad to see that it happened, and yeah. Also, in some sense, the fact that we had and managed to have very nice invited speakers. Usually it's a very long process to invite people, make the visas, make them come to the conference, and that might be a nice bonus of making it virtual. Right? At least this. All right, so thank you again, and yeah, hopefully see you later. Bye.